Morning, my name is Connie Arts and I have the honor to chair the first session on stellar astrophysics. Woo! And we'll get kick-started with Dan Hey from the University of Hawaii, who has received a completely impossible task to summarize astroseismology of 6-year TESS in 20 minutes. Please, Dan, take it away.
Thanks, Connie. All right. Hey, everyone. I'm Dan Hey. I'm a postdoc from the University of Hawaii at Manoa. And like Connie says, I have the impossible task of summarizing some of the great science that has come out of TESS over the past 6 years. So I'm going to start off with this plot, which I stole from Tara Featheroff's poster 2.11, which you should go check out. I saw it yesterday and I thought it was really nice because basically she searched through all of TESS first 2 cycles and has gone the variability period, plotted it versus the luminosity, and colored it by temperature. And the point I want to make with this plot is that you can't really download any TESS light curve without seeing some kind of variability, whether it be eclipses or transits or pulsations or something like that, right? So I've highlighted a few of the different things that you see here. So you get the high mass oscillators. So these are actual astroseismic pulsations. You get red giant pulsations. You get contact binaries and M dwarfs, and that big blob is just like everything else. So for those in the audience who don't know what astroseismology is, I have a little crash course, which hopefully won't take too long over the next 5 minutes. So astroseismology is a science of studying the internal structure of stars through their pulsations. So on the left here, I've got an astroseismic HR diagram. It's just a regular HR diagram, but we've colored them by the different types of pulsating stars. And on the right is just a typical, one solar mass star that I've labeled. And you've got your convective zone, you've got your radiative zone, and you've got your stellar core, like usual. The cool thing is that if you have a convective envelope in these stars, it drives this kind of turbulent convection on the surface. So it shakes these stars around. And as it shakes them, it generates sound waves that propagate through the inside of the star. And we classify these sound waves according to whether they're damped by either pressure, which we call P modes, or gravity, which we call G modes. So I've got this, how it works, which is great. So the red and the orange are P modes, which propagate close to the surface of the star. And the green thing is a G mode, which propagates kind of confined within the core of the star. All right. So in practice, what we usually see are just P modes, except in some special situations where you get like coupling between the P and G modes. So cast your mind back to high school physics and think of spherical harmonics. So of course, if you have a sphere, like a star, potentially a sphere, and you perturb the surface, you can describe those perturbations in terms of spherical harmonics. So you have your simplest pulsators, the radial pulsators. Those are just L equals 0 modes. And these are things that just contract and expand radially like that, right? That's just L equals 0. Then you've got your L equals 1 modes. So those are things where like the top of the star contracts while the bottom half expands and vice versa. And you've got L equals 2 and 3 and so on. So I've animated the L equals 2 mode here. And you can see as the star expands and contracts, you get these kind of constant nodal lines across the surface. So there's 2 nodal lines, so it's an L equals 2 mode. And you can see as the star oscillates upwards, it's red and blue shifted, right? If you're observing it, the surface of the star distorts towards you and away from you, which you can actually measure using radial velocity variations. But it also changes the temperature of the star, and so it changes the luminosity of the star. So you can measure these astroseismic pulsations in 2 ways, either through radial velocities or through photometry. And in practice, stars don't just oscillate in one kind of angular degree L, it oscillates in some kind of net combination of multiple oscillations simultaneously. And I've shown a kind of heavily emphasized version of this in this animation. So we couldn't be in a better auditorium for this because we have this beautiful pipe organ up here. So if you forget anything I just said about spherical harmonics, the only takeaway I want from this crash course is basically stars are very similar to bells or pipe organs. So if you have a small star, it's like a small bell. It has a high frequency and a low amplitude, right? And on the other end of the scale, you have a very large bell. You hit it, it makes a very deep sound, so it's a very low frequency, and it's a very high amplitude sound, right? So stars, I'm kind of glossing over a bit of stuff, but that's kind of how it works in astroseismology. So now I'm going to get into some actual test data. So I'm going to talk about solar-like oscillators first, and these are things which oscillate like our sun. That should hopefully go without saying, but I don't mean it's like a temperature and luminosity like our sun. I mean that it has a similar pulsation characteristics to our own sun, which also oscillates. So if we go back to our HR diagram, our astroseismic HR diagram, I've highlighted the solar-like and the red giant stars, and these are driven by that kind of turbulent convection I was talking about just then. So what you do is you take a light curve along these stars. So this is 16 sig A observed by Kepler. And then you take the Fourier transform of that light curve. So you calculate it in Fourier space and you get out this beautiful spectrum. So the x-axis is in microhertz. And if you don't normally think in microhertz, that's like, I think that's an 8-minute period or something like that. But straight away, you can see these beautiful pulsation modes of different angular degrees L. And you can also notice that these pulsations are kind of excited in this like Gaussian shape. And this Gaussian shape we characterize by this thing called nu max, which tells us about the mass, the radius, and the temperature of the star, which is great. So like straight away, if you see these pulsations and you can fit like a Gaussian envelope to it, you can learn a lot about the star already. And if we zoom in a bit, hopefully, yep, if we zoom in a bit, then you can see I've labeled some of these different modes. So you've got your 0, 2, and 1 mode. And the separation between modes of equal angular degree, so the separation between L equals 0, it gives you the large separation delta nu, which gives you the density of the star. And then this tiny separation between 0 and 2 is the small separation, which tells you things about the age and the internal structure of the star. So I showed you Kepler data first, because now I want to show you TESS data. And if you look at a TESS light curve in the continuous viewing zone, what's really amazing is that TESS is almost starting to look as good as Kepler is for astroseismology. So if you looked at this and you looked at the previous one, hopefully you cannot see much of a difference. So we can do all these same kinds of astroseismic analyses using TESS data if your star is in the continuous viewing zone. Because the more data you have, the better you resolve the modes. So this was a situation with TESS this is a situation with solar-like oscillators prior to 2016, so before TESS launched. And these are all the stars that have observed solar-like oscillations. So you see most of what we get are kind of like distant and faint stars observed by Kepler. And then we have a few bright nearby stars observed with ground-based photometry. And there's a kind of dearth of stars at intermediate distances and radii. And this is a situation with TESS. So TESS has really filled in this kind of beautiful, beautiful spot in this distance radius diagram with all this new information. And the point I want to make is that the 20-second data is really enabling these kinds of astroseismic analyses. So I've taken some stuff from Dan Huber's work on gamma pav and zeta tuck. And in the top, you can see the 2-minute cadence data, and that is kind of hard to see oscillations, right? Like maybe you can squint, and maybe you can see something. But on the bottom is the 20-second cadence data, and here you can see that you really get these beautiful oscillations out. So if you're studying a transit or an exoplanet or something, go and look at the 20-second cadence data, because maybe you can see these oscillations and you can analyze your star in better detail. And on the right, I just have the same for Lambda Sur. And Dan Huber's going to talk more about this on Friday. And I think Lauren Harrington has a nice poster on this as well. So another point I want to make with the TESS 20-second data is that it's uniquely suited to detecting oscillations in bright, high-frequency stars. So this is a probability map I made of the probability of detecting oscillations in the 2-minute data on the left, in the 20-second data in the middle. And you can see that they kind of look very similar. But because of the improved noise properties of the 20-second cadence data, if you take the probability difference between them on the right, you see that there's this kind of like island of bright, high-frequency stars that TESS is uniquely suited to observe in. So if you take this section and you look at some of the stars in it, This is Sigma Draconis, which is some great work being done by Mark Hahn, and he has a great poster on it as well. And if you remember that the higher the frequency of your star, the lower the amplitude. So this is an extremely high frequency, low amplitude K-dwarf, and it's the first that's been observed by TESS. I think there's one other K-dwarf that's been observed by Kepler, with which we have oscillations, which is really amazing. So what we did was we took this 20-second cadence photometry of like 13 months, and then we measured high precision radial velocities using the Keck Planet Finder. So we're using KPF for astroseismology, not planets. And we get this extra kind of radial velocity light curve, I guess, RB curve. And if you plot the power spectrum of it, then you see we get this RV power spectrum, which is great. You see the oscillation modes, and you get the TESS photometry power spectrum. So you see essentially the same thing in both photometry and radial velocity. And the point I want to make here is that the amplitude of these modes is incredibly small. So in TESS, you're getting like less than 1 part per million photometric difference, which is like 0.0001%, right? And the amplitude in radial velocity space, the distortion of the star is on the order of like 6 centimeters per second, which is really crazy. So if you have these stars, of course, and if you have regular red giants, then you can do other things with them as well. If you just measure new max, you can get out the masses and whatnot. So there's other work that Mark has done on measuring masses in the Milky Way using TESS. And you just get this beautiful like galactic archaeology. So you can also do this kind of ensemble galactic archaeology with TESS, as well as individual studies of single stars. And I think Rafa is going to talk a bit more about this in this session. Okay, so that's it for soul-like oscillators. So now I'm going to move on to classical pulsators, which are driven by a completely different mechanism. It's like energy gets trapped in the star expands, the energy escapes, and the star contracts again, in a nutshell. So these stars don't really have convective envelopes that drive this kind of turbulence on the surface. So there's a lot of great stuff coming out with TESS on classical pulsators. There's young delta Scuti stars, so these like 6,000 to 10,000 Kelvin. And TESS has shown that they're kind of ubiquitous in a lot of stellar clusters, especially the Pleiades. So on the left is a plot by Tim Bedin showing that delta Scuti stars are just everywhere in the Pleiades. And if you have these stars, you can do work like what Simon Murphy has done on giving seismic age constraints of these kind of cluster stars, which is really cool. Some work that me and Connie have done actually on OVAF stars. So believe it or not, you can get light curves from Gaia, and you can measure actual frequencies from Gaia light curves, which is work that Connie's team has done, which we've confirmed with TESS, and there is a really great agreement. So TESS is also showing that there are hundreds of thousands of these kinds of OBAF type pulsators in the sky that were found by Gaia and confirmed by TESS. Connie's going to talk a lot more about this at a talk on Friday, and there's also a nice poster by Vincent Ben Lyra on kind of adjacent stuff to this. So on the other end of the scale, we have pulsations in massive stars with TESS. So there's going to be a nice talk by Lin Haomar on the blue supergiant problem and measuring variability in these stars coming up on Thursday. And there's also a poster by Rebecca on blue supergiant variability. And we also have stars that look like they're pulsating, but they're not actually pulsating, which you can show because the TESS pixel size is so big, it gets contaminated with these nearby oscillations. And Keaton Bell's done a lot of great work on that. He also has a poster. It's an interactive poster, which is pretty cool as well. Okay, so in the last 5 minutes, I'm going to talk about TESS Asteroseismology and what it's done for exoplanet science. So first off, we have TESS photometry of JWST direct imaging targets. So this was work done by a graduate student at UH, Aldo Sepulveda. So he looked at the TESS light curve of the first directly imaged exoplanet by JWST. And of course, the star is pulsating. It's a delta Scuti pulsator. And these pulsations are really cool because we have both the delta Scuti pulsations, which give you a constraint on the age. And there's these P-mode splittings, which tell you about the rotation. And then there's also a rotational signal at low frequencies caused by like surface modulation of the star. So if you take the rotation, you have V sin I, and you have the radius, then you get the inclination. So it's always good to like look at the TESS light curve of your star with whatever you're doing. Because if you have this rotation stuff, you can figure out like the spin orbit alignment and potentially the planet age. So we also have some great work done by Joel Ong, who's going to give a talk, I think, later today on a potential engulfment candidate found by TESS. So this is a red giant that was rapidly spun up, like anomalously high rotation rate, which tells you that that it's potentially absorbed something in the past, maybe a planet. And this is also confirmed by the TESS Asteroseismology, where you see these rotational split-ins that tell you that it's much more rapidly rotating than it should be. As also confirmed with ground-based photometry. So using Assassin, you can see this same rotational signal. So TESS has a lot of great overlap with a lot of different missions for figuring out engulfment candidates. And on the other end of the scale, we have stars that have actually escaped engulfment. So this is more great work done by Mark Hahn for this so-called forbidden planet. So this is 8 Umi, and TESS Asteroseismology can tell you whether a star is on the red giant branch or whether it's a red clump star based on its oscillation modes. And we know that this star has a planet with a semi-major axis of about 0.5. So if the 8 Umi is evolving up the red giant branch, then at some point it should have engulfed its planet, right? It evolved so much, the planet was within its radius, so the planet should not be there because we know that 8 Umi is a red clump star. So there's a few different theories about why this planet has survived. Speak to Mark for more information, but the prevailing idea is that this is actually a stellar merger, and what happens is as the star merges, it kind of jumps from the red giant branch to the red clump without undergoing this kind of radius inflation and then contraction again, which is why the planet has managed to survive. So I think I'm a little under time, but it's all good. So please get involved in TESS Stellar Astrophysics. This is a photo from the TESS TASC8 CASC15 conference in Porto 2 weeks ago. You can see there's a whole bunch of people interested in it, and there's a whole bunch of people in the audience here who are also working on astroseismology. So if you want to learn more, please come talk to me or Connie or anyone else. And the closing remark I want to make on this is that the TESS photometric data is approaching the levels of Kepler photometric data. The baseline and the precision is getting better and better, and it's only going to get better from here. Thank you.
Thanks, Zan, for this wonderful overview. You have plenty of time, actually. I underestimated you. That means we have more time for questions. Please remind the audience who you are, where you're from, before you ask your question.
Chaz Beichman, NASA Exoplanet Science Institute. So given now that TESS has gone for many years, will probably continue to go many years forward, what do you see the advantages, relative advantages between TESS and Plato, and of course, going back to Kepler?
Yeah, that's a great question. So of course, Plato is going to do great work. I have to say that because Connie's here, but it will. But also TESS is going to do great stuff as well, because in the continuous viewing zones especially, we'll just get more and more data. And the more data you have for astroseismology, the better. So I kind of glossed over a few things, a few recent developments in astroseismology. We have this new thing called magnetoseismology, where you see these mode split-ins, and the asymmetry in the split-ins tells you about the magnetic field of the star. So you can do that purely from photometry, but we're slowly approaching the point where we can start doing that with TESS. And as for Plato, we'll have to see how that goes.
Well, maybe add to that that there were 500 sun-like stars with Kepler. TESS is focusing more on subgiants, right? There will be 20,000 with Plato. So that gives a scale. Other questions for Dan? Here first, and then in the back. Okay.
Thanks for the overview. Tansu Dailan, Washington University. So you showed some interesting plots on the RV detecting the astroseismologic signal from the RV. So RV data is typically collected over longer timescales, so it's fairly undersampled. How does that impact your results? And is there aliasing involved?
Sorry, can you repeat the last part?
Like RV data is collected over long time scales and it's undersampled. It's not like test data. So how do you handle that aspect?
Yeah, that's a great question. So this RV data was actually collected over, I think, a single night. So just 8 hours of RV data. And the Keck Planet Finder has this kind of fast readout mode where you can like read RVs out within, I think, like 10 seconds or something like that. So we get a lot of very high cadence, rapid RV readouts. So it's not like a long baseline of RVs.
There was a question, yeah, in the back.
Hey, Dan, great talk. This is Stephen Jacqueline from Caltech. So yesterday they teased this potential 2-second mode for upcoming TESS cycles. Does that open up any new region of parameter space for astroseismology, or are you pretty much like at the limit of what the cadence can do?
Yeah, that's a great question too. So in terms of cadence, I don't think there'd be a huge difference. So in astroseismology, we worry about like the Nyquist limit, right? So for Kepler, it was 30 minutes, which limited the maximum frequency we could see. But with TESS 2-minute, that's like, or 20-second data, that's so high that there's not, I don't think there's much that can pulsate above that level. The real benefit of the 2-second cadence data here is if it obeys the same noise scaling as like the 2-minute to 20-second does, because the 20-second improves the noise quality so much more, and hopefully the 2-second will improve it that much more as well.
Other questions for Dan? If not in the audience, I have one. You haven't mentioned, or at least not put in the spotlight, binarity and oscillations, while more than half of the stars are in binaries and almost 90 to 100% when you go up in mass. Is there any comparative work that has single stars versus binary stars as an overview?
Yeah, thanks, Connie. Yeah, of course, a lot of stars are in binary systems. And there's a lot of work on like that kind of tidal astroseismology, right? So if you're in a closed binary system, it can also excite pulsations in the star, as you know. Just general things like that.
I think we're lacking an overview on that
Yeah.
now that I think of it. Are there any other questions? John, I think in the back.
Yeah, just comment on the improvement in precision at 20 seconds compared to 2 minutes. That's because the onboard cosmic ray mitigation is actually hampered by some natural modes of in the pointing stability, and we can recover a lot of that at 20 seconds. But if we go to 2 seconds, I think we've already achieved most of the gains there. And in fact, you have higher pointing instability at 2 seconds. And so it's not clear to me that you're going to gain a whole lot.
Okay, thanks for the, that's disappointing, but great. Thanks.
We'll sort it out somehow.
Yeah.
No more questions? If not, then we thank Dan again for a great review talk. The next talk is by Ward Howard from Colorado, I think, who is going to tell us about test constraints on radiation environments of M dwarfs from flares, if that's a good summary. Please take it away.
I'd like to thank the organizers for inviting me to come talk with you about 20-second cadence flares with TESS. This is another area of stellar astrophysics where the new 20-second cadence mode has really advanced the state of the field. Since the last of these conferences, TESS has now measured the optical flare rate of essentially every bright nearby star in the sky. 1 million flares from 140,000 stars were observed during the primary mission alone, which can be seen in this color magnitude diagram from Feinstein et al. 2022, showing the flare rate on the color bar with the darker colors representing higher flare rates. And by the end of EM2, we'll be at over 3.5 million flares observed at cadences ranging from 20-second to 200-second cadence, and are very much looking forward to the new 2-second cadence mode. And many of the works that report these flares are shown here, and I'd be happy to point you to those if you're interested later. Moving specifically towards the 20-second cadence data, TESS has carried out an all-sky flare monitoring campaign of the most active stars across the sky forest at 20-second cadence during EM1. This is an example of what one of these flares looks like. And in its light curve, you can see that I've highlighted the peak of the flare in red, which is the time where the emission time scale correlates fairly well with the cadence of the data. And I've shown an inset panel for this flare peak. And this panel then shows substructure that would have been completely washed out at the lower 2-minute cadence, which allows us to understand things like rise phase burstiness and the physics that's occurring in these events. Across our whole sample, TESS has now observed around 7,400 of these 20-second cadence flares from these 460 stars across a wide range of energies and amplitudes and flare shapes, which can be seen here, all the way from ones that are barely detectable, all the way up to flares that nearly double the brightness of the star and release almost 10 to the 36 ERG, which is close to the largest flares you would typically see from an M dwarf. And many of these flares have different shapes that have been very useful for solar modelers to try to test their models against new data sets besides just those from the sun. And you can see a set of examples here where I'll show the 20-second cadence light curve after showing the 2-minute cadence light curve. And when you do the reveal, you can often see a degree of substructure that again was just lost at the lower cadence. Okay, we'll keep going. While we've learned a lot about the optical behavior of these flares at 20-second cadence with TESS, unfortunately, the UV contribution of these TESS flares, we've learned less. And in fact, the UV sky, when it comes to TESS, is dark. These are the simultaneous flares that we do have. There are several dozen of them, the majority reported by Paudel et al. 2024 earlier this year. On the x-axis is the energy of the flare and the TESS bandpass, and on the y-axis is the near UV energy for most of these flares, FUV energy from STIS for a few of these flares. Out of this sample, only 17 events have been observed during the flare peak and at 20-second cadence in each band, which limits what we can learn even more. And in the absence of more simultaneous data, the typical go-to solution is to assume a 9,000 Kelvin canonical flare blackbody that does do a good job describing the spectrum of many optical flares and just extrapolate that into the UV to get a first-order estimate. Unfortunately, data from Galix, Kepler, and TESS are complicating this because they seem to be showing that this 9,000 Kelvin blackbody is significantly underestimating the amount of UV energies of these optical flares. And to see that, I've overlaid lines for a 9,000 Kelvin, 12,000 Kelvin, 16,000 Kelvin, and 26,000 Kelvin flare onto this plot. And even just from the scatter and this relationship that you can see here, there's more than an order of magnitude of scatter across all of these different effective temperatures, from some flares that don't even reach 9,000 Kelvin up to other flares that exceed 26,000 Kelvin, which could be an order of magnitude underestimate of the true near UV energy of the flare. So why does this matter? It matters because only the UV contribution of these TESS flares ultimately drives photochemistry in planetary atmospheres. Photochemistry at the FUV to near UV wavelengths drives chemistry for oxygen, biosignature false positive, H2O, and other species. And you can see why we need to have the simultaneous UV observations from this plot with these synthetic muscle spectra I've shown here, where I've superimposed two different flares onto the spectrum. One of these is a 9,000 Kelvin flare, the other a 16,000 Kelvin flare. And both of them appear equivalent in the TESS bandpass and have the same energy. However, when you move into the near UV, the hotter flare emits about 5 times more energy. And when you move into the FUV, more than an order of magnitude more energy. And the FUV to near UV ratio is very important for understanding these false positive signatures. As a result, a lack of multi-wavelength observations means we simply don't know what impact the TESS optical flare archive really has on exoplanet atmospheres, at least to within 1 to 2 orders of magnitude. So this raises the question, is there anything that we can learn from simultaneous 20-second cadence observations where the resolved emission helps us to narrow the scatter? To answer this question, I looked at a set of simultaneous observations with 20-second cadence using SWIFT in the near UV and TESS in the optical, where our near UV sample comes from some stars that we observed as part of our programs and some stars that were previously reported by other teams to build the largest sample possible. And going back to this plot, I just want to quickly remind you of how much scatter we're looking at. We have more than an order of magnitude of scatter in this relationship. So I would be happy with even some degree of improvement, maybe 50% or 100%. So what we find is that the 20-second cadence data, in fact, does help us. In fact, the full width at half maximum of the TESS light curve does a better job predicting the total near UV energy of the flare than does the total optical TESS energy that includes both the peak and the flare tail. And to see why, I'm showing a plot where I've convolved near spec observations of TESS flares from TRAPPIST-1 against the TESS response curve, where the effective temperature of the near spec spectrum is shown in the top panel, and then the TESS light curve, where I've convolved it to produce that 20-second cadence light curve, is shown in the bottom panel. And I've highlighted the full width at half maximum because this is the period where the near UV effective temperature is closer to the TESS band effective temperature than during the decay phase. So if we're integrating over both the peak and the decay phase, we're actually introducing a new source of scatter we don't even have to introduce into our relationship. So using this insight, how do we do? The answer is that we can reduce the scatter by about a factor of 2. And here I'm showing two different distributions, an orange distribution where I've predicted the near UV energies using a scaling relationship based on just the full width at half maximum of the TESS light curve. And then in the blue relationship, one that includes both the full width at half maximum, the peak, the rise, and the decay of the flare. And the x-axis of this plot shows the mean error of this prediction of the near UV energy. And this is the total near UV energy, not just the full width at half maximum near UV energy. And we're able to constrain that mean scatter by, again, about a factor of 2 here. So going back to this plot, we can now take our TESS energies, pass them through this improved scaling relationship, and then pass them back to now have an estimate of the near UV energy of these flares. But we can learn more than just the near UV energies of the flares when we have this high cadence simultaneous data. We can do a lot of other things, and one of those things that we can do is we can model and remove flares from TESS band data using simultaneous near UV data, because the same underlying processes are ultimately responsible for emission in both of these bands, even though the details certainly differ. So in the top panel here, I'm showing a swift light curve. In the middle panel, a simultaneous 20-second cadence TESS light curve, and in the bottom panel, residuals that I'll get back to in a minute. So in this top panel, you'll notice there's some times in gray. This is where Swift went behind the planet during the TESS observations of a flare. And because the TESS observations don't show any flare peaks, I just simulated a flare decay tail so I could then do planet injection and recovery tests that I'll get to in a minute. And then what I've done is I fit models to the UV flare. And then I've integrated those models to get a prediction for what the TESS band flare will look like, where the only truly free parameter is the amplitude of the flare in the TESS band pass. And as you'll notice also, I've stitched together lots of individual Swift observations and concatenated them in time to produce the equivalent of one longer duration light curve so we can do these planet injection and recovery tests. And then when we subtract off the prediction of the TESS band pass, that gives us the residuals. And this is important because the independent near UV provides a lever arm for being able to distinguish true transits from active stars versus false positive transits caused by back-to-back flares, which give this characteristic U shape. So how do we do? Again, we can inject planets with a range of orbital periods and transit depths into these residual light curves and then compare them to what we would have been able to detect without having this extra source of information. And on the left panel, we show with the flare detrending in blue. On the right panel, no detrending in purple. And we get an improvement of about 0.01, just under that, in our transit depths, which would correlate to about a half a Earth radius increase in transit sensitivity for, say, a K7 dwarf, and even better if we go to a later type star. This is significant because for this K7 dwarf, this is enough to push us across the border from only being able to detect sub-Neptunes all the way into being able to detect super-Earths. Now, I want to take a step back for a second here because you're probably all thinking, Ward, this is well and good, but where are we going to get our 30 days of simultaneous near UV coverage for all of our TESS flares? I'm glad you asked. I'd like to introduce you to the Early Evolution Explorer, or EVE, an astrophysics small explorer concept. EVE will investigate the earliest stages and the shared evolutionary pathways of stars and planets with 3 primary goals, as well as ancillary science, such as astroseismology of low-mass stars. The first of its primary goals is to detect dozens of planets younger than 30 megayear to assess their H2O inventory in their atmospheres. The second is to determine the effects of flares on atmospheric photochemistry. And the third is to discover the effects of accretion on angular momentum transport and young disks. The main point to take away is that EVE is a multi-wavelength successor to TESS. With simultaneous red optical and near UV photometry of about 10,000 young stars, it will observe nearby clusters at about 30-second cadence with TESS-like stare times and a larger aperture than TESS, but a smaller field of view. So I'm going to quickly just cover the flare science case and then conclude. So for the EVE flare objective, as you can see, we've shown the current literature sample from Paudel et al. 2024 in blue, and then the EVE sample with two different scenarios, one with an increasing near UV to optical ratio with flare energy, the other with a constant ratio. And EVE will be able to discriminate between these ratios at well above 3 sigma, especially for the highest energies. On the y-axis, on the other side of the plot, I've put in an estimated abiotic oxygen mixing ratio to show the amount of how this effective temperature would essentially correlate with an FUV to near UV ratio that would produce more abiotic oxygen than would have been predicted. So this is a source where we can then understand this abiotic emission. And EVE will detect 450 of these events in year 1, enabling test of this. I also like to just point out we're led by Meredith McGregor at JHU and Anne-Marie Cody, who's in the room, and our project scientist, Neil Turner. And then we have the rest of the team here. So I'd like to thank you for your time. And if you have any questions about EVE or the flare science, I have a large number of backup slides.
Thanks a lot, Ward, for an interesting talk. Time for questions, loads of questions. Completely in the back over there.
Hi, Brian Jackson, Boise State. This is really neat. Could you say something about how bright these stars are that you're monitoring, and the it seemed like there was factor of 4 change in flux during the flares. I'm just kind of trying to get a sense for how useful it would be to do ground-based observations of these flaring stars. Thanks.
Yeah, that's a great question. So this is the amount by which the flare energy is overestimated or underestimated at near UV wavelengths, which again correlates with a much, much larger underestimate at FUV wavelengths. So to give one quick example of that, if I go into the backup slides, here we go. So this shows the difference between the underestimate of the energy in the near UV to TESS ratio on the x-axis, when you can see the factor of 4 would correlate with about a 13,000 Kelvin blackbody. And then as you go up, you'll see that that is about more like a factor of 6 or 7 in the FUV to near UV ratio, which is really important for OT photochemistry. But then when you go to our larger flares, we often see a factor of 10 underestimate in these larger events. And then that would correlate more with an order of magnitude underestimate in the FUV to near UV ratio and more than a decade underestimate in the amount of abiotic O2 in an Earth-like atmosphere, and have similar kinds of effects for like a young Neptune.
JJ in the back.
Yeah. Thanks, Ward. This is JJ Hermes from Boston University. I wonder if you could go back to the slide where you showed about a half day of the near UV simultaneous data from SWIFT with TESS. There looked like a few really strong near UV flares that didn't actually show up in TESS at all. I'm sort of looking right in the middle of your plot there, between day 0.2 and 0.3. So can you explain what happens when you see a near UV flare and you don't see an optical flare? What's going on with that?
That's mostly just due to the sensitivity of the optical instrument. We do actually see these flares, but they are very small. If I took this whole time series and I pulled it apart, there is actually a small increase in flux there. It's just not very statistically significant. But this goes back to that large degree of scatter that we would have between the optical emission of the flare and the UV emission of the flare. And that would indicate that there's a disconnect between particle acceleration, where we see this UV emission, and then the resultant heating. And I would also point you to Paudel et al. 2024, who shows that this occurs actually a significant fraction of the time.
One last short question. Okay, I'll take the youngsters, and the others have to post on the Slack.
Glad to be young today. I'm Chris Lindsay. I'm a student at Yale. Do you have a sense of for the M dwarf stars that you're monitoring, the Gini coefficient? Like, is this high? Is there a high inequality on like some flares, like some stars flaring a ton and other stars not flaring at all, or are they all kind of flaring at similar rates?
So we can answer this question for the TESS bandpass. We don't know the answer to this question in the UV because the observations don't currently exist. In the TESS bandpass, we see that young stars have very typical flare power loss slopes, which tend to be pretty shallow compared to those seen for later stars. And there's a great paper by Dina Feinstein 2024 that you could go check out for those results. And so we see very, very similar levels of flaring for stars of a given age within a given cluster. Once you start moving to higher ages, that starts to decrease in terms of the overall flare rate.
Please put your questions in Slack because we are running out of time. Thanks, Ward, for a wonderful talk. The next, let's move on to the next speaker, Luca Bouma from Caltech, who is going to talk about transient corotating gas clumps around very young low mass stars. Please take it away.
Thank you. I imagine that many of you know what a light curve looks like when two stars pass in front of each other. I also imagine that many of you know what a light curve looks like when a star has some surface brightness distribution and it rotates, in this case, every 12 hours. However, I'm a little less certain how many of you have seen stars of the class that I'm going to talk about today. At first glance, they look messy, complicated. If you fold them, though, they're periodic. So I'd like to poll you all, quick show of hands. Who here has seen stars like this before? Okay, it's a good number. If you haven't, you're also in good company. What I'd like to spend some time on today is why I think these stars exist, and also maybe why now is a good time to think about them. These complex periodic variables, because that's what I call them, aren't rare one-off cases anymore. We have a population now of objects like this. It's about 100. And they have some common characteristics. Okay, the periods are fast. The stars themselves are young. They're also low mass. Mass is below about 40% that of the sun. They are observationally rare. They comprise about 1% of young stars. The fraction's a little bit higher for the very youngest stars, a little bit lower if you go out to 100 million years. But you know, transiting planets are also intrinsically rare as an observational phenomenon, and there's a geometric reason for that. If a similar geometric correction is applicable, the intrinsic abundance of these objects could be higher by an order of magnitude. Two other important observational points. The first is that from ground-based multicolor photometry, we know that the light curves aren't gray. In other words, they show chromaticity. The dips are deeper in the blue than they are in the red. And as a final point, there's no evidence in any of these systems for disks. There's no infrared access. There's no evidence of accretion diagnostics in spectra. So taken collectively, this distinguishes the complex periodic variables from a separate class of object called dippers. Please don't call them that. Totally different phenomenology. And this particular class of objects has now a literature that goes back to the early days of K2. And the picture that has always seemed to make the most sense for them is the idea that there are co-rotating clumps of material that move with the star. And I've thought a lot about this picture. This was the picture that was proposed going back to the original pioneering works on these objects. I thought about this picture, and I basically agree. Although I think today we can say a little bit more. I think we can say that what we're seeing is transient co-rotating gas clumps. So just to be very clear about basically what the claim is here, it's that each of these local minima is a separate clump of material, probably magnetically confined, moving around with the star once per stellar rotation cycle, because the magnetic field lines of the star are effectively rigid. There is an asterisk on gas. When I say gas, if it's influenced by magnetic fields, of course, what I mean is plasma. It's partially ionized. And what I'm going to argue today is that I think I actually have evidence for the fact that A, the circumstellar material is there, and B, that it does include plasma. I'm not yet sure, though, whether or not it's a dusty plasma. So, okay, what's the evidence for this kind of bizarre picture? There's basically two lines of evidence. Okay, the first is photometry, TESS. The second is the spectroscopy. I'll talk about both. When I say TESS, what I mean for some recent work is the TESS 2-minute data. Okay, I recently took the TESS 2-minute data from the first 4 or so years of the mission, selected bright K and M dwarfs. And this is actually a really interesting selection function. You should think about what exactly it means for a star to have a 2-minute light curve. I'll gloss over that. I'll just say if you select stars in this way, you run a shape-agnostic period search, then you find some interesting objects. Okay, in fact, so many interesting objects that it pays off to write a little bit of code to count sharp local minima. When you do that, that's why these objects stand out, right? Because they have many sharp local minima. From performing this exercise, I found a lot of weird stars. I looked at them visually to figure out whether I thought they were part of this class. And all told, there were 50. So about half of the stars of this class now we know from TESS, maybe a little bit more. This is the first 25. This is the next 25. And I won't belabor the phenomenology. I'll just say that the sharp features that are present for some of these objects are one of the main lines of evidence, photometrically, that this material needs to be moving around with the star at some large stellar distance. You can't get star spots on the surface to produce a feature that lasts maybe 10% of a cycle. Even if you play games with the inclination, in detail, it doesn't work out. So what I would like to spend some time on is what TESS specifically is giving us that's new. One thing it's giving us is long baselines. So I'm going to show you 6 months of data for one of my favorite complex periodic variables, LP12502. I'm showing a few cycles here, bin together. And there are 6 local minima per cycle right now. If I advance the movie, if you pay attention to this cycle right here, it quickly goes away. That event is actually precipitated by a flare. For the rest of the 6 months, though, these local minima stick around. So sometimes the dips last for months, but they can collapse apparently quickly in less than 1 cycle. And often those collapse events are precipitated by flares. Okay, that's one of the lines of evidence for this picture I was describing of the magnetic fields mattering, right? Because flares are a magnetic reconnection event. If you reconnect the field lines, reconfigure, maybe you free this plasma to move. The second thing that TESS gives us, beyond really great light curves, is a sample of bright stars. And bright stars mean that you can do spectroscopy. So I'll show you 2 different spectroscopic data sets. The first one is low resolution spectroscopy that we've acquired from California, simultaneous with a ground-based light curve from Arizona. So this is ground-based data. This is the TIERAS photometer. Ayilin Garcia Mejia is here at MIT, acquired this. It's a tremendous instrument. What I'll show on the right first are just the Balmer emission lines, H alpha, beta, and gamma. And what I'll show in the middle is the equivalent width time series of those lines. So just to prime your expectations, okay, if this co-rotating circumstellar material that I'm claiming might be there is entirely made of dust, then it shouldn't preferentially be absorbing light at these wavelengths. Dust is a broadband absorber. If it's made of gas, maybe we'll see something that's a little bit different from a flat line. It's a little bit different from a flat line. I'll play through the interesting part one more time. In this photometric event, a triple dip, there's a large oscillation almost in the spectroscopy. It's not exactly one-to-one. If you have ideas for thinking through how one might model this spectroscopic variability, I'd really be interested to speak with you. I'll just say that the sort of 30,000-foot interpretation is that we're seeing larger amplitude variability in the Balmer series than we are in the photometry. And it seems like there's no way to explain that using only dust. We need to have some circumstellar plasma. So I think that argument is pretty good, but it would be nicer if we had some way of directly detecting circumstellar material moving around. What I'm saying is plasma. For instance, if we were able to acquire high resolution spectroscopy, simultaneous with TESS perhaps, and actually see the material in emission. Okay, so this is the TESS light curve for a really fast one now, 4-hour period. And I'm just going to show H alpha in the middle. Okay, so at the beginning of what was a 5-hour half-night sequence from Keck high res, H alpha is in emission. It looks maybe there's only one emission line. If we look forward, though, the line splits. There's a component there, and then it splits again. Okay? If you look at the time dynamic spectrum, there's actually a double helix, right? And what that means is that there's coherent Balmer emission at a few times the star's equatorial velocity. In other words, you can just trace by the semi-amplitude of these helices where the material is away from the star. It's at anywhere from 3 to 4 stellar radii. Okay, so just really quickly, I think this demonstrates that we're learning about the circumstellar environments of these stars. We're also learning probably about the stellar magnetic fields that are responsible for being able to confine plasma in this way. One of the big questions that I think has yet to be answered for these objects, where does the material come from? Okay, it could be entirely stellar. It could come from an old and undetected disk. It might come from a rocky body, very young, hot, close in, outgassing, analogous to, say, the Jupiter Io plasma torus. I think that'll be a question for the future. I'll just quickly wrap up by giving you what I think are the main takeaways from the work so far. The first is that the complex periodic variables are observationally rare, but they might not intrinsically be so rare, especially if a geometric correction is applicable. The data that we have right now require there to be co-rotating circumstellar material, and the material needs to include at least some plasma. It might also be dusty, but I think the arguments for that are more indirect. And as a final point, I've briefly outlined 3 possible origin scenarios, but in my opinion, the key to this puzzle really has yet to be found. So what that means is that there are a lot of discoveries here waiting to be made. Thanks.
Thank you, Luca, for an interesting talk. Questions? Yes. Please raise your hand again. Yeah.
Thanks, Luke. A very nice talk. I'm Jiwon Zhang from University of Hawaii. I'm wondering for the thing, do you think about whether it's come from large star spots that could also cause the periodic signal you see here?
Thank you for the question. So, oops, too fast. Okay, so the one that's up there in the far right, the little tiny one. So people have tried modeling the scenario using only star spots. And it's certainly the case that the smooth variability is probably ascribed to star spots. But if you go through the exercise of, could I arrange star spots in some non-physical configuration to explain 1% amplitude dips lasting only maybe a tenth or even less than a tenth of a cycle? The answer is you can't. If you fine-tune the inclination, then you get a limb darkening and a foreshortening effect, which lowers the amplitude of any features. So long story short, people have tried star spots, and you can't explain every member of this class this way. The dips are too sharp.
I think there was a question. Yes, question in the back.
Thank you for this very interesting talk. Ilaria Pascucci from University of Arizona. So in your scenario, when this is due to a remnant disk, one could expect some spectral type dependence. So is there any preference for certain spectral types to have this behavior?
Yes. So if I understood the question correctly, it was, is there any preference for certain spectral types to have this behavior? So all the stars that are known to do this are M dwarfs. Mass is less than 40% out of the sun. So actually not even M0. All the ones that are known to do it are M1 to maybe M6. It hasn't been demonstrated whether or not there is a low mass boundary to this phenomenon.
There was another question in the back, yes?
David Martin, Tufts University. This is amazing stuff. Do you have any sense of this phenomenon as a function of stellar age? And like if it falls off at a certain age or?
So I won't repeat it because the question I think was pretty clear. The oldest ones that are known to do this are around Pleiades age, a little bit older. And there are a decent number of those. It's like maybe half a dozen.
David here, last question, and all others start typing your questions in Slack, please.
Hey, Luke, this is David Charity at XI. So as always, this is a really great topic. I am curious, now that you've got a larger sample and some of these combining K2 and TESS, what's the longer term evolution that you're seeing?
It's a great question. So the periods stay the same. We don't have any evidence for long-term period evolution in any of them yet. The shapes, if you look at one star, for example, at time 0, and you come back at time 2 years, the shapes always change. So for the K2 baselines, where we now have not just 0 to 2 years, but we have 0 to 10 years, they're still doing the same thing most of the time. They're still complex, but the shapes have evolved. So they're basically unpredictable in terms of detailed shape evolution over timescales of more than a few months. But they seem to, for the most part, continue to show the same phenomenon. Actually, in detail, some of them, sometimes the dips do disappear and come back later. Which, basically it means that any ground-based observing or even space-based observing campaigns focused on spectroscopy, for example, needs to be simultaneous photometry and spectroscopy. Otherwise, the experiment totally fails.
Let's thank Luca again for a wonderful talk. The next speaker is Catherine Espalliat from Boston University on protoplanetary disks, dissipation with TESS and JWST. Okay, it's on the screen. Go ahead, Catherine.
Yeah, thank you. Slight change to the title, got some extra JWST data after submitted the abstract, so broadened it a little bit to include the other object I'll be talking about. So I'll be talking about 2 protoplanetary disks that have simultaneous JWST and TESS data. And I'll be showing you why we think that these JWST and TESS data are evidence of misaligned inner disks that are casting variable shadows on the outer disk. So I'll be showing you JWST MIRI spectra that show seesaw variability. So at the short end, when the emission goes down, at the longer end, the emission goes up and vice versa. And for the 2 objects, UX Tau A and SC Cha. And then I'll be showing you TESS optical, TESS light curves that show that both of these objects are dippers. And then later on, I'll explain why we think this is connected to misaligned inner disks and variable shadowing. All right, so first, a very brief and quick introduction to protoplanetary disks. So the ones I'm talking about surround T-Tauri stars. And the protoplanetary disks are made up of dust and gas, 99% gas. And somehow, we don't know how yet, that material goes inward and accretes onto the star. So there's a point in the disk where the temperature becomes hot enough that the dust sublimates, and all we have moving inward towards the star is gas, which is truncated by the stellar magnetic field of these young objects and is channeled onto the star. And these objects, they have a lot of physical processes and chemical processes going on, and they're very variable. At virtually every wavelength that they've been observed at, they show variability. And I'll be talking about 3 particular kinds of variability and how I think that, how we think that they're all linked based on our data set. And I'll step through each of those now. Okay, so first, the mid-infrared seesaw variability that was detected by Spitzer. So here I just show SC Cha and UX Tau A, but there were a couple dozen that were discovered with Spitzer. I'm just focusing on these 2 for this talk. And let's just focus on UX Tau A on the bottom here to see the seesaw variability. So when the red spectrum here is on top at the shorter end, it's then on the longer end, it's on the bottom. So it's inversely related to one another. And these lines are models that were fit to the IRS spectra. And I should mention that both of these objects are what we call pre-transitional disks. So we have a lot of different nomenclature in the field. The takeaway there is that there is an inner optically thick disk separated by a gap of tens of AU, about 30 to 40 AU in these 2 objects, from an outer optically thick disk. And that inner disk is what's giving us the emission at the short end of the mid-infrared spectrum, and the outer disk is what's giving us the emission at the longer end. So we initially explained the seesaw variability as due to a geometrical effect. When we have less emission coming from the inner disk, that means that the inner disk is, we modeled it as being having a smaller scale height, and then the shadow on the outer disk was smaller, and so we saw more emission from the outer disk, and vice versa. When the inner wall, the inner part of the disk was taller, there was more emission from the inner part of the disk, so the shorter end of the spectrum, there was a larger shadow on the outer disk, and we saw less emission from the outer disk. All right, and then we have also the second type of variability I want to talk about is dippers. So these were seen in optical light curves with Kepler, and now we're seeing also with TESS. And here are just some examples of dipper light curves, and we think that these are due to dust that's obscuring the star. So when we measure the periods of the dips, they're equal to, in many cases, they're equal to the stellar rotation period, which is telling us that there's dust at the corotation radius, so the part of the disk where it's rotating at with the same period as the star. And what we think is happening is that dust is actually being funneled onto the star. So in the canonical picture of accretion, the dust is further away from where the gas is being channeled onto the star. But in the case of some of these dippers, it's been explained that, as some of this dust makes it inward along with the gas, and is actually being lifted off of the disk, and that's what causes obscuration of the star. And then the last type of variability I want to talk about is near-infrared images of shadows on the outer disks of some protoplanetary disks. And here on the top, there are some broad shadows. On the bottom, there are some narrow shadows. Some of these shadows have been observed to vary with periods of months to years. And they've been explained as being due to a misaligned inner disk. As it precesses around the star, the shadow that it casts on the outer disk is changing. All right, so in a bit, I'll get to how we think all of these 3 types of variability are connected. And I'll start off first with talking about the JWST spectra. Okay, so first, here are the Spitzer spectra for our 2 objects, SC Cha and UX Tau A, that show seesaw variability. And I'll be showing the JWST spectrum next, so pay attention because I don't have a fancy figure for that. It's just going to pop up. So there's the JWST spectra for SC Cha in black and gray, and for UX Tau A in black. And what I hope you notice is that SC Cha looks similar to what it was doing before, but UX Tau A has this very significant drop. And these broken lines here correspond to the stellar photosphere. So now UX Tau A's emission is photospheric. So something very different is happening in this object. So first, let's talk about SC Cha. We can compare it to near-wise data at slightly shorter wavelengths. That was taken over 10 years. And we see that SC Cha's variability seems to be more stable. It's not really varying from what's been seen previously in this object. Whereas for UX Tau A, like I said before, we're seeing significant difference. Here's the near-wise data. It never reaches photospheric levels, but here in the JWST spectrum, we're catching it doing something special. All right, so one piece of evidence that we can use to explain this is looking at that there's some additional data from other researchers that have looked at the inclination of the inner disk versus the outer disk. So the inner disk inclination was measured using gravity, the outer disk using ALMA. And UX Tau A is less aligned, where its inner disk is more misaligned from the outer disk. And SC Cha, the inner disk and outer disk have are relatively aligned with one another. So what we think is happening at SC-CHA is that its inner disk has a slight misalignment from the outer disk, not very significant, and there's a slight wobble that's happening as the inner disk precesses around the star. So not to this extreme level as shown in this figure schematic, but that's just to guide your eye. So we think that that's why SC-CHA shows relatively stable seesaw variability. Whereas for UX tau A, we think it's doing something very different. As I said before, we think that there's also dust depletion happening in this system. And this can happen due to dust breaking, where the inner disk becomes very misaligned from the outer disk and it's harder to accrete. So in the Spitzer, at the time of the Spitzer observations, we think that the inner disk was relatively aligned with the outer disk, and therefore it was able to accrete from the outer disk and the inner disk was able to be replenished. But at later stages, as the misaligned inner disk precesses, there'll become points where it's very misaligned from the outer disk. And it's harder for the accretion from the outer disk, the material to go from the outer disk to the inner disk. And therefore, the dust will be depleted on very short time scales, which could be leading to this drop that we see. So there's no, this JWST spectrum is telling us that there's a significant depletion of dust in the inner disk. Nothing is emitting at short radii. And this is just a animation to help visualize what is happening when these misaligned inner disks are precessing. It's not specific to UX tau A. I just wanted to show something more visual of how it would look like when we have an inner disk that breaks off from the outer disk and it's precessing around the star. All right, so getting back to the dust depletion. So we can estimate roughly the dust depletion timescale in UX tau A. So I'll get to these spectra in a little bit, but from the Spitzer data, where we saw that there was some dust in the inner disk, we can measure the minimum dust mass that's necessary to explain that excess that we saw, and we get 10 to the negative 11 solar masses per year. We have these we have these H alpha spectra that we took of UX tau A, also SC-CHA, but I don't have time to get into those, contemporaneous with JWST, so within a day. And we measure gas accretion rates of 1 to 2 times 10 to the negative 8 solar masses per year. So there's still substantial gas accretion going on. If we assume the canonical gas to dust mass ratio of about 100, we would measure that this dust mass would deplete within about 0.1 year. So if the inner disk was cut off from the outer disk, the dust would deplete very rapidly, where the gas could still continue. You can still have a gaseous inner disk that maintains accretion. All right, so now finally on to the TESS data. So first I'll describe the light curves before I get into the disk precession timescale. So here we have in black, the TESS light curves of SC-CHA and UX tau A. The points are assassin data, and the broken vertical lines correspond to the times of our JWST observations. Now, both objects show Dipper light curves, which, as I said earlier, we can use the period that's measured and say that that's the period at the co-rotation radius. And these misaligned inner disks have been proposed to be due to planets at the co-rotation radius. And if there is, and the precession timescale of the inner disk should be 1,000 times the planet's orbital radius, orbital period. So if there is a Jupiter mass planet in these objects, that would lead to a precession timescale using the period measured from TESS of about 10 years. And if there's a 10 Jupiter mass planet, the inner disk precession timescale would be about 1 year. So we don't have fine cadence for the Spitzer and JWST observations, but for what we do have, which spans 1 to 19 years, this is roughly consistent with the disk precession timescale that we estimate. And we also get additional evidence from UX tau A's TESS light curve that has a precessing inner disk, specifically one that has a clumpy dust distribution. So one piece of evidence is that, so these light curves look very different, but they're both of UX tau A. On the top, it has a classification defined by Cody et al. As a quasi-periodic symmetric light curve. And on the bottom, it's a aperiodic Dipper light curve. So two very different types of light curves. And we think that could be, and these two light curves are taken about 2 years apart. And we think that could be an indication that the inner disk is precessing around the star. And so at the different times, we're seeing different light curves because there's different obscuration of the star that's going on. And the evidence for the clumpiness of the dust distribution in the inner disk comes from these dips. We only caught a part of this dip here, but there's two dips before and after the JWST observations of a few days. So the JWST observations are telling us that there's no significant dust in the inner disk, but since we see these dips, that means there is dust present that is obscuring the star. So this is telling us that we have a clumpy dust distribution where we have a little bit of dust and it's in clumps, and as it rotates, as the magnetic columns rotate, they can lift that dust off of the disk and cause some of this obscuration. All right, so to summarize, we think that the mid-infrared seesaw continuum variability that we see and the Dipper light curves are both related to the same physical mechanism where we have misaligned inner disks. And the future observations that we propose to test this are first to get near-infrared imaging of the outer disks to image the shadows on the outer disks of these objects. And also, if this is due to a precessing misaligned inner disk, then the orbital, so this should be periodic, the variability should be periodic. So we need more observations of the inclination of the inner disk to see it changing over time. And also we also need more mid-infrared continuum spectra in order to set some more timescales for the precession of the inner disk. And I'll just conclude by leaving up my main conclusion here. Thank you very much.
Thanks, Catherine. We have time for one question, I think. In the back, please.
Thank you very much, Catherine, for this very interesting talk. Ilaria Pascucci from the University of Arizona. So I noticed that in the UX tau A spectrum, the JWST spectrum, you also have much stronger ionic lines from neon and argon. Can you comment on how that related to your scenario?
Yes, so if I can, I think, okay, so here you see what Larry is pointing out is that there's these very strong lines here. There's also PAH emission that pops up, but for the atomic lines, those are neon and argon, and they're very sensitive to very small amounts of gas in the inner disk. So what I think is happening is that since the dust has been depleted, more of the gas is receiving the stellar radiation, the high energy, and this is created by X-ray. So there's no shielding from the dust, and so we see more atomic lines. That's what I think is happening there, atomic line emission.
Okay, let's start. Catherine again, please put additional questions in Slack. Thank you. The final talk of this session is by Ayilin Garcia from Dartmouth College on Balmer luminosities and photometric amplitudes of M dwarfs. Please take it away.
Clicker. Hello, can you hear me?
Yep.
Hi, my name is Ayilin Garcia Soto. I am a fifth-year grad student at Dartmouth, and I work with Professor Elizabeth Newton. Today, I will sort of go back a little bit to what a combination of what Luke and Ward were talking about. We're looking specifically at fully convective M dwarfs and variability that you see in it, magnetically sensitive Balmer line emission. So I don't have to read this, but as we all know, we are very interested in M dwarfs because its signatures in transits and radial velocities. You can see the exoplanets very well, and because of its size, its habitable zone is much closer in. However, we must also think about the stellar surface features, which can mask or emulate similar features to exoplanets and high energy radiance, and as well as the average photosphere is not really represented by what the planet is transiting in front of. So basically, observing M dwarf magnetic activity and its variability provides insights into their stellar dynamos, high energy radiation, impact on exoplanet detection and characterization. A brief outline. We're going to talk about a comparison of the magnetic activity proxies, but also we're looking at fully convective M dwarfs. And then we'll discuss the results that we find when we take contemporaneous data of TESS and a spectrograph and look at these M dwarfs. So the inspiration for this project was actually from Newton et al. 2017. In this paper, they actually have the H alpha luminosity on the y-axis and the rotation on the x-axis, and this is called a rotation activity plot. However, this one's different because what it's being plotted as well is the color of the amplitude, which is related to the spot crossing in front of the star. And if you can see, it's sort of rough, but you can kind of tell that higher amplitude seems to be for the M dwarfs that rotate faster, so in the saturation regime. This is another way of seeing it. This one was actually in the paper. You have the amplitude not on the y-axis, and on the x-axis, you have the H alpha luminosity. And now it's colored by mass. So you see that it's a weakly positive relationship, but they're still scattered. So the idea was, what if we take contemporaneous data instead, would this relationship tighten? And just to reiterate, the amplitude is being calculated by the light curve. And as a spot goes in and out of view, the brightness changes over time. So that's what we're considering the amplitude. And we also have H alpha emission for all of these stars. But we also got lucky and we're able to get beta, gamma, and delta as well. So as we all probably remember from radio transfer, H alpha is usually an absorption. And while calcium H and K, which is another chromospheric line, is always an emission. And the idea for that one is that it's collisional excitation. But if you heat the chromosphere, you can actually get your H alpha to become an emission line. And the idea is that if you compare it to calcium H and K, it could be collisional excitation. However, there's another way to heat the chromosphere, and it's polarization and recombination. So in this plot, you have, you're combining X-ray from the corona and H alpha luminosity, and you can see they're almost 1-to-1, because the idea is that back heating from the corona, it might be what's causing the chromospheric heating. So just to go back, we want to take contemporaneous data, but we also want to figure out what is the mechanism causing the H alpha emission variability. So that's me. The way we did this is that we use TESS because we know when it's observing, and we use OSMOS, which is a ground-based spectrograph. And we replotted the picture where you have amplitude over the H alpha luminosity, and you see that's the same thing, even if it's contemporaneous data. However, something else that you might notice is that those are not error bars. Those are actually range in luminosity, because we took multiple spectra of these objects, and we actually found that they vary in the short time scale. So what we did is that we looked at their test light curves during the time this was observed. And so now we have the light curve on top, and we have H alpha equivalent widths on the bottom panel versus time. And you can actually see that sometimes it corresponds with a flare very clearly in TESS, sometimes it doesn't, as you can see from the second side. We did this for multiple stars. And for paper, and so basically from the end of that paper, what we learned was that no, you can't really use H alpha emissions as a proxy for spot related modulation. But in paper 2, what we decided to do is go more in depth of what the previous slide was. So now we have an even more detailed light curve on top, where we have flagged the flares in blue, and we have binned the cadence to match the cadence of the spectra. And we've also included beta, delta, and gamma. And we also added another column called Balmer decrement, which helps you determine what is the mechanism causing here. And it helps you because you're dividing the Balmer lines by a fiducial line, or in this case, H beta. So one of the things you notice is that although there's corresponding flares in the TESS light curve, sometimes there's not. And we saw this earlier with the near infrared with Ward's presentation. And he mentioned that it could be the detectability, or maybe it could also be Maybe it's not a white light flare, maybe it's not something else flare, like a UV flare. The next thing is that if you look at the ratio of the Balmer lines, you see similar changes within a detected flare in the optical, but also when there's not an optical flare detected. So the ratios are the same. So those are like the two main things we saw from the contemporaneous data. The other thing though, is if you just look at the spectra, you see a higher variability in H delta. So if right here we have a spectra, we have flux on the y-axis, and on the x-axis we have velocity, and we're centered on each Balmer line. And we see that the black line is the median flux, while the shaded regions are the upper and lower limits of the range in observations. And for H alpha, we see much less variability than if you go to higher order line like H delta. To make sure that was a real result, we actually incorporated the error bars into the calculation of an intrinsic variability value. And we also incorporated the range in the equivalent widths, and we find that it's a real result. There's more variability as you increase to higher order lines. So basically, what we found in paper 1, paper 2 is that when you compare the proxy magnetic field activity indicators such as H alpha luminosity with spot-related amplitude, you actually get still a very weakly tight correlation, even if you are doing it in contemporaneous time. We use TESS and Osmos to find these, and these are fully convective M dwarfs. I have to reiterate that. And then the results are basically that you get significant Balmer lines variability that matches with flares, but sometimes it doesn't. And another thing you notice is that the ratio in Balmer lines show similar changes whether in or out a white light flare. And I didn't really answer the question, what is the mechanism causing this? The idea is that it could either be pure recombination and collisional. I will say the answer is both, but also not. We need more data is the real answer. And the last thing was the intrinsic variability increases towards high order Balmer lines. Thank you.
Thank you. Thank you, Ayilin, for staying well in time. We have time for questions. Everybody's tired? Oh, here in front. What?
Great talk. I was looking at your plot showing the higher level of excitation for the higher order lines, and it was making me think of Adam Kowalski's rating models, where he found the pressure broadening led to seeing sometimes more variability in those lines and the models. And I was wondering if you could comment on if you think that that might be related to the mechanism behind what's occurring here in your plots.
It's possible, but not all of these are, these aren't not the young ones in our sample, but both young T-Tauri stars and the main sequence stars show this. I was under impression, I think that the T-Tauri ones have higher pressure broadening rather than these. And I do actually notice that the width is much larger for the T-Tauri stars. But this is probably more to do with pure recombination and collisional excitation just because of the age. But again, I just said that they're similar, so maybe not.
Really interesting.
Time for one more question, if any. I don't see any hands, so let's thank Ayilin again for a great talk.
All right, if we can all take some seats. We'll keep going with some stellar astrophysics. We don't need to be partisan about it. So we're going to hear from Yuto Kajikiya about some simultaneous photometry and spectroscopy of stellar flares on the M dwarf YZ CMI using TESS and Semei. Yuto, take it away.
Thank you. Hello, everyone. My name is Yuto Kajikiya. I'm from Tokyo Institute of Technology. I'm a master course student. Today, I'd like to talk to you about my observational research on M using TESS and Semei. First, I'll explain the background of my research. Recently, M dwarfs are considered for searching for habitable planets because their habitable zone is close to the host star. However, M dwarfs shows frequent flares. So these flare and associated coronal mass ejection may significantly impact crossing habitable planets. For example, they may affect atmospheric chemistry and atmospheric. Therefore, understanding the flare and mass ejection in M dwarf is very important for future search for exoplanetary life. M dwarf cannot be especially observed like the sun. Therefore, we cannot directly observe coronal mass ejection. However, their initial stages called eruption can be observed as blue or red asymmetry in H-alpha line profile. This figure shows an example. The vertical axis shows normalized flux and horizontal axis velocity and wavelength. This figure shows blue asymmetry, and these blue shifted components are candidates for prominence eruption. In previous study, many of these asymmetries show duration exceeding 20 minutes. However, short duration events with duration of less than 20 minutes are commonly observed on the sun. M dwarfs having stronger surface gravity are expected to show shorter durations. Therefore, a previous spectroscopy may have missed this short duration event due to insufficient time cadence. Okay. Next, I will explain the simultaneous observation with TESS. TESS can observe white flare, which represents the radiation from flare footpoints. And the TESS light curve enables the dissipation, volumetric energy of flares, and estimation of star spot distribution. On the other hand, optical spectroscopy can measure the velocity and duration of prominence eruptions. Therefore, these simultaneous observations enable the investigation between the investigation of the relationship between prominence eruptions and white flares. However, such simultaneous observation tests are still rare. Therefore, we conducted optical spectroscopic monitoring observation active M dwarf YZ CMI using Semei telescope simultaneously with TESS. We conducted high time cadence observation using 3.8 meter Semei telescope and low dispersion spectrograph Cool's IFU. This high time cadence observation enabled to capture the short-term velocity changes that were previous spectroscopy could not capture. Okay, this is a light curve from TESS and Semei. The top panel shows a 20-second TESS light curve, and the bottom panel shows a H-alpha light curve. The vertical axis shows normalized flux and H-alpha equivalent width, while the horizontal axis shows a eccentric Judean date. We detected 130 white flares from TESS light curve and 27 H-alpha flares from H-alpha light curve. The upper arrow in the figure shows detected flares, and these are enlarged view of representative flares. Next, I will explain the analysis method of H-alpha spectrum. First, we created the normal vertical axis shows a normalized intensity, and horizontal axis shows velocity and wavelength. The black solid line shows clear state spectrum, and red line shows a quiescent state spectrum. Next, I created the differential spectrum by subtracting the quiescent spectrum from flare state spectrum. These differential spectrum enable to evaluate the asymmetry of H-alpha line profile. From these differential spectrum, out of 27 H-alpha flares, 3 flares shows blue asymmetry, and 5 flares shows red asymmetry for line profile. Next, I'd like to move on to the results and discussion. Here, I will show the statistical result of asymmetry duration. And this figure shows a histogram of asymmetry duration. The vertical axis shows the number of flares, and horizontal axis shows the asymmetry duration. And the dark blue and red bar shows this work, and light blue and red bar shows this work. As you can see from this figure, we discovered short duration events that were previously detected. Previous studies may not have time cadence enough for such short events. In the next few slides, I will show the result, the shortest blue and red asymmetry events. First, I will show the result of the shortest duration blue asymmetry. The light curve on TESS and HRF. The vertical axis shows the normalized flux and HRF equivalents, and the horizontal axis shows time from start of flares. This light curve shows the impulsive white-white flares and HRF flares. And the photometric energy derived from TESS flux is equivalent to the largest solar flare. This figure differential spectrum at the HRF flare peak. This figure shows the blue asymmetry and bump-like shape. And the velocity is approximately 450 km per sec. This value is relatively faster than previously reported value. In the next slide, I will show the temporal changes of this differential spectrum. This figure is a spectrum showing the temporal changes of differential spectrum. The blue lines, the differential spectrum on the right part, and the color bar shows the vertical axis of differential spectrum. Dynamic spectrum shows a clear blue asymmetry that lasts for approximately 8 minutes. These are the properties of blue asymmetry. These properties are consistent with solar prominence eruption. Therefore, we interpreted this event as rapid short duration prominence eruption. Next, I will show the result of the shortest duration event. This is a figure of dynamic spectrum and light curve. This light curve is an impulsive HRF figure. And the dynamic spectrum shows red asymmetry that lasts 6 minutes. And the velocity is 300 km per sec. However, there is no clear changes in TESS light curve. These are the properties of red asymmetry. And these properties are consistent with backward prominence eruptions. If flare occurs on the stellar limb, the white light emission from the foot point will be hidden and barely visible. However, if backward prominence eruption occurs, the red-shifted HRF emission will be observed. Therefore, we interpreted this event as rapid short duration backward prominence eruptions. Finally, I will discuss the implication for exoplanets. In previous slide, I showed the short duration prominence eruption. This velocity, as written here, slower than the surface escape velocity of YZ CMI. Therefore, it is unclear whether these prominence eruptions themselves developed into coronal mass ejection. However, in the case of the Sun, as shown in this schematic picture of solar coronal mass ejection, the velocity of coronal mass ejection is approximately 10 times faster than the associated coronal mass ejection. Therefore, assuming these relationships, outer hot plasma associated with these short duration prominence eruptions could be accelerated to more than 1,000 km per sec, potentially leading to coronal mass ejections. This is the last summary slide. In this research, we conducted optical spectroscopic monitoring observation using TESS and Semei. As a result, we detected 27 HRF flares. Additionally, we discovered rapid short duration prominence eruption that were previously detected. These results suggest the previous study may have underestimated the frequency of prominence eruptions and coronal mass ejections. This is very important for understanding their impact on exoplanets. For future work, I will investigate the statistics of blue and red asymmetry, and I will also conduct multi-wavelength observation, including X-ray and ultraviolet. Okay, that's it. Thank you for your attention.
Questions?
Hi there, Lauren Doyle from the University of Warwick. A great talk. I just wondered, you talk about backwards prominence eruptions. Is there any evidence in solar physics or any evidence from what we know of the sun to know about, like, what can we say more about these?
Yes. In the case of the sun, sometimes it shows red shifted components and correspond to backward prominence eruption. But it is not reported in publication.
Great talk. We're Howard C. Boulder. I wanted to ask if you have any plans to try to observe several of these indirect methods to get at the CMEs at the same time, like say coronal dimmings and red-blue asymmetries.
Sorry, could you repeat the question more slowly, please?
Would it be possible, do you have any plans to potentially try to observe both coronal dimmings along with the red-blue asymmetries in the H-alpha line to get like multiple messengers of a CME?
So sorry, please, sorry.
Like with a coronal dimming where the star can become fainter following a CME.
Or maybe you can clarify what observations for a coronal dimming?
Yeah, usually what you would use, so on the sun, we often see the X-ray or EUV
thank you.
strong coronal dimmings. Yeah.
I see. Back up side. As you can see from this figure A, and ultraviolet ray capture dimming due to coronal mass loss caused by coronal mass ejection, which is so we will reveal the physical mechanism by these simple observations. Okay.
All right. Any other questions? If not, let's thank Yuto again.
Thank you.
And next, we're going to hear from Rafael Garcia about measuring rotation periods and stellar oscillations in red giants with TESS data.
Can you hear me? It's okay? Yeah. So hi, everyone. Good morning. And I want to thank you, the SOC, to give me the opportunity to talk here. And above everything else, to the TESS people, because this is a wonderful mission, and I hope that you will enjoy the presentation with much more new results. So what I'm going to talk today, it's how we can proceed to characterize stellar signal with TESS, but at really low frequency, so rotation and red giants. So as it was said this morning by Dan, our objective is to go from the light curves that you see on your left-hand side towards a power spectrum in which you can see several sources of variability. You have rotation, you have convection, you have oscillations. And then I will be talking about the two extremes, so oscillations and the rotation. So on the left-hand side, you can see the Kepler, typical Kepler F-type star. And on the left-hand side, that's going to be complicated. The same star observed by TESS. So it's 5 sectors that we put all together. And as you can see, there is the rotation signature. It's almost the same thing. And in fact, if I superimpose the spectra of one to the other one, it looks the same, apart from the different level of noise that we have because of different instrumentation and electronics, etc. So what are the requirements we need to go to look for these low frequency signals? What we need we want to analyze several hundred thousand of stars, which means millions of sectors. So I apologize with the mast because we were downloading massively a lot of sectors the last month. So if there is a peak in France, it was us. And we were even banned because we were downloading too much data, but that's another thing. And then we don't want to bother with the FFIs. That's much more data. So we wanted a product which already handled the FFIs. And then we decided to go for the QLP data, which is an amazing set of data. It's available for millions of stars, and it has two important things for us. It has an aperture that depends on the magnitude of the star, which is good. And also it's normally corrected by the background in most of the cases, although it's not always the case as I will show later in the talk. So this is an example of a star that you can see. So first of all, we are going to remove all of the outliers that you will see, as you see in the top plot. Then we are going to put the data together. This is simply because we are going to use these plots to vetting or to check the reliability of the corrections we are doing, etc. And also because, as I will show later, we need to remove these gaps if we want to look for rotation rates above 10 days, something like that, even 20 days. And finally, we are going to do a high-pass filter at about 20 days, just because this is the limit that we fixed for this first analysis. And on the bottom one, you have the power spectrum of a beautiful red giant measured by TESS with 4 sectors. So what I'm going to show is a procedure that we follow to uncover around and characterize around 200,000 new red giants. So first of all, it can be shown, as you see in the plot there, that the amount of power that you have in the power spectrum will depend on the evolutionary stage of the star. On the bottom left, you will see the first star is the sun, and then as you go up in the evolutionary track until the superluminous RGBs, the power will be increasing, and then when we will be back in the red clamp, the power is slightly below. So this has been known since 2018, something like that, by the group led by Savita Mathur and Thomas Kallinger in 2014. So we can use this relation to relate the amount of power with the nu max of the seismology or with the log G of the star. And this is what we did in 2018 with my PhD student Lisa Bounier. And we were able to use this average power at different bands on the spectra to take into account, for example, rotation peaks or pulsations or even pollution, to do a random forest algorithm and then be able to recover either way the nu max or the log G of the star by simply this metric, which is the average power. This gives us a precision which is slightly less good than the astroseismology, when in fact we use astroseismology to calibrate this relation. So to do this properly, we need to train the data set. So we analyze 158,000 stars that Mark Hahn did in his paper on 2021. And as you can see, you have a vertical, nearly vertical relation between the flipper, as we call this metric, with the nu max of the star, with a bunch of stars that are behaving kind of weird. So what is happening for those stars? So those stars, in most of the cases, have either way a position in this diagram that does not correspond. They have too much power to what they should be. And this is because, for example, it's a binary. So it's a very clear way to flag binaries. So many of those stars that you see there, it's a binary of there is a polluted binary just behind. Or also you have something else, which is here, calibration problems. So this is a case, and there are a lot of stars that have this problem, which is in fact what we think it's a bad correction of the background in the QLP data. As you can see in the twin sets that are shown there, corresponding to the 2 halves of the sector, it's in fact in blue is the actual data, and in red is the background correction that it's supposed to be applied to the data, properly calibrated, and it's absolutely not the case. So for whatever reason in the QLP data, sometimes the background correction is not working properly. So we have to either way correct this sector or remove them from the from the set. Another important and interesting thing is that as you see there, it's again the log, like logarithmic scale of the flipper against the Numax. If we, in the vertical plots, we divided the stars by magnitude. So the stars that are the brighter ones, nearly there are no problems with calibration. The amount of stellar power is much higher than the problems induced by the calibration, and then the relation is perfectly linear. When we go to fainter and fainter stars, the calibration problems are more and more evident, as you can see in the plot. So with all of this that I have said, how well the data is working, how well the flipper is working, you see it here. So we divided the set into a training set and a testing set. And in the right-hand plot, you see the recover. So it's the Numax from Mark Hohn's paper and the Numax that we recover for this, I think it's a set of 20% of the sample. So 30,000 stars, something like that. And at the end of the day, we finish with a median absolute deviation of about 3 microhertz for the Numax, which is really, really good. So we want to go beyond what Mark did. So we also analyze the Kepler data observed by TESS, which allow us to go much lower in frequency. And we found a very great correlation between the power in the TESS data with the luminous giants. And when we apply all of this to the new set of 300,000 candidates, this is what we obtain. It's the same shape. We have the same type of behavior than before, but we need to verify if this is working or not. So what we did is we took Gaia log Gs, we compared to the log G that we infer, and we obtain a maximum absolute deviation of about 0.29 dex. Of course, we didn't stop there. I'm not going to show it. We run our seismic pipeline, and for many of those, we obtain a better Numax and delta nu for those. So for about 200,000 new red giants that are waiting. And we will be working with Mark Hohn also to complement the both methods for all of these sets. Now, the second part of the talk is going to be about the rotation. So that's the other part that we want to measure. And up to now, we have been in most of the studies that are outside. We are limited by if we are talking about one single sector of about a limit of 10 days, something like that, then you see also at 9 days and 14 days and 27 days of the multiples of the 27 days signal. And unless you use the continuous viewing zone, where you can go up to approximately 27 days, as shown by Zachary Claytor in the last paper in 2024, we are always limited by these kind of things. What we want to do is go beyond this limit of 10 days by using the multi-cycle test capabilities. So we're going to use one sector, 2 years gap, one sector, and see what happens. The first thing that we have to take into account is just if you take the data as it is and you use the usual methodologies like the autocorrelation function or wavelets or the power spectrum, you will have either way a very nasty window function. Or if you do autocorrelation and you have a gap, you will never be able to go beyond half of the set. So again, a limit about 10, 12 days, because when you do the correlation, you have the zeros and you cannot work with this. What we thought about is just, we put the data together, as I said before, and we work with that. Of course, it will depend on the phase shift between the two segments that we are doing. If you are absolutely in opposite phase, the autocorrelation function will be 0. So in that case, you will not measure anything. But you will not measure anything anyway if you have the gap in between. But in many other cases in which you have a better phase situation, then you will be able to measure rotation rates up to 20 days. To test that, what we did is to use Kepler data, so no problem with the calibration. Just use 1 month, a gap of 1 year, 1 month. We put it together and we analyze it through the pipeline, which is in fact the Plato scientific pipeline that we are actually testing with this data. And what we obtain at the end is that, well, there are many things on the slide, but just go to the last column there. When we use the machine learning Rooster methodology, which is also applied in Plato, we will be able to obtain a retrieval rate of about 90% of the rotation rates up to 20 days. Remember, no problem on the calibration. But what happened with the real data? That's what happened with the real data, the test data. These are 2 examples with 5 sectors and 9 sectors. You have the non-corrected QLP data on the left-hand side and the corrected one and properly stitched on the right-hand side. And you see the solution of the wavelets and the ACF. If you don't do a proper job removing the bad sectors and you don't do a proper job in the stitching, you will not retrieve the proper periods. So it's very important to do these kind of things. So this is actually the results of what we obtained. So again, we took all the Kepler data. We did a vetting on the data. So we only took those results in which we have a GACF. So that means the amplitude of the ACF between the two minima, the average of the two minima around the main maximum. So if they have, in fact, a peak above 0.1, so 10% of the power, then we accept the star. If not, we consider it's not rotating or it's problems. So what we obtained at the end is that in the 1-1 line, so the proper rotation rates, we obtained approximately at about 75% of the stars up to 13 days. And we degraded this up to 67% for the rotation rates from 0 to 20. There are, of course, always the eternal problem of the half periods. You have the numbers there, 10%, 6%, and we have, in the worst case, a 25% of false positives. Of course, this can be tuned. It can be tuned depending on the vetting that we are doing. And for just visual inspecting many of those, the problem is still the corrections are not at the grade that we would like to have. So as I want to be friend with JJ a little bit more, that's my conclusions, and I will stop here. Thank you.
Questions?
Hi, Tara Feather, UC Riverside. Great talk. I have actually a lot of questions, but I'm going to start with something bigger picture and then maybe follow up for the more specifics. So I'm really interested in how you just kind of ignored the gaps. You just kind of stitched together. And I guess I'm wondering what happens if you have like spot evolution.
So that's two great questions. So for the stitching, we're using a modified version of the Bayesian inference criteria that we were applying since a long time from Kepler. So it's a decay stitch Kazakh filter thing. We added some more cases. So we are checking at the end of the end of one sector, the beginning of the next one, if the average of the two are correct, or a linear regression, or a cubic, parabolic one, cubic one. Well, there is a lot of things, and then we let the Bayesian inference to decide which one is the best. It works for many cases. Of course, sometimes it doesn't work. So this is part of the ones that we want to solve. We are testing also, if we have an idea of the period, we can do also a kind of sinusoidal stitching, which is working also very well when you have an idea of the period. So these are the things that we are still trying to fine tune a little bit. And when we stitch together, I mean, when we remove the gaps, the big gaps, and we put together, we don't do anything because the phases are completely different, which I think is the second question you have. So that's what we do. We only stitch together those that are really close for less than 3, 4, 5 days.
We have time for one quick question.
Hi, Damoto, University of New Mexico. I have a question about background subtraction. I think you said at some point that QLP did not apply a background correction that should have been applied. And is that because we knew that that was what the background was doing at that time, or just because you applied a normalization that corrected it to like 1?
Okay. In principle, QLP data do a background correction, and in fact, they do one of the products that they give in the feed files is the background. The background time series, something like that. But the thing is that sometimes I don't know if I can go back, but I don't know if you have it in mind. There are a few light curves in which we have a very funny thing like the green in the 26 sector, and then we just superimpose the background that they are normally be used to correct that, and it's exactly the same thing.
Okay, right.
So which means that something went wrong on that particular case.
That was my question. Thank you.
All right, sorry, Derek, we're gonna have to move on. So please post your questions on the Slack for Rafa. Let's thank him again. And next up, we're gonna hear from Lyra Cao, who's gonna tell us about TESS light curve amplitudes, rotation periods, star spots, and lower main sequence stars.
Thank you. Thank you so much, JJ. Hi, my name is Lyra Cao, and I am a postdoc at Vanderbilt. I would like to thank the SOC and LSC, as well as my collaborators, for giving me a chance to talk about star spots and how they can potentially change the way we think about doing stellar and planetary physics in the era of TESS and beyond. Okay, magnetism is important in stars. We often talk about this concept of a precision stellar astrophysics, of reaching sub-percent level precisions on stellar parameters for many stars. But it is documented that stellar activity has the potential to kind of dominate the error budget in many cases. So to deliver on the promise of a precision stellar astrophysics, we need to get a handle on how to understand stellar activity and how to work around stellar activity, which can be quite common in the field. My role in this picture primarily has to do with my two temperature fits, which I perform on apogee near infrared spectra. On the left-hand and right-hand sides, I'm plotting continuum normalized flux plots, and both the best fit line and the band indicating its departure from the, the best fit line and the band indicating its best fit, its departure from the observed spectra. I postulate a model which incorporates an inhomogeneous surface for the star and compare it to the spectra, and I obtain a best fit value for the entire apogee spectrum from 1.5 to 1.7 microns. In essence, we're optimizing and finding the minimum of our chi-square distribution in a high dimensional space, including a concurrent fit to spot fraction, as well as the spot temperature contrast, as well as parameters such as the TEF, log G, velocity, surface rotation, microturbulence with this ensemble line-based technique. Okay, this is all done in the pursuit of the idea that we need interpretable magnetic activity proxies for the purposes of testing and informing our theories of stellar evolution. That, as evidence has shown in the literature, magnetic stellar models are needed to explain the parameters of active stars, aka planet hosts. It is on one hand easy to measure H alpha, calcium, and X-rays in emission. It is comparatively harder to make direct magnetic measurements of stars. This is kind of a shame because with a direct magnetic field proxy, such as magnetic field strength or the star spot filling factor, you know something about the stellar surface that is clearly interpretable with stellar models. With a star spot filling factor, so this, however, is not the same picture that we get with the indirect proxies, which means that a catalog like the Leopard star spot catalog will help us stress test these new generations of stellar models and produce better stellar parameters as well. So here I'm showing an activity Rossby plot for star spots in the Pleiades open cluster. On the x-axis, I'm showing the log of the Rossby number defined as the rotation period divided by the convective return time scale. This is essentially showing you how rapidly stars are rotating relative to their internal structure. A small Rossby number indicates rapid rotation, and a larger dynamo number, which is thought to imply stronger magnetic activity. In this plot, you can see a characteristic decline of spots at the limit of slower rotation and a genuine star spot saturation at rapid rotation. We published this paper in 2022, along with the relationship shown here, so that anyone with a rotation period, say from TESS, and some estimate of the convective return timescale, whether it's stellar models or empirical tau-CZ relations, you can estimate the star spot filling factor and start interpreting it with our public models. The public spots isochrones, which are a set of stellar models which incorporate star spots as a free parameter to better constrain stars out there with a fully batteries included self-consistent magnetic stellar modeling process. Now, I kind of hinted at systematics in stellar parameters. Here I'm showing a radius TEF plot including stars from the alpha per cluster, where we've done SED fitting on each star. Underneath the black points are a spread of colored lines. These colored lines span a large range in star spot filling fraction, and they're modeled from the spots isochrones. So they indicate the variation in star spot filling factor, the amount to which magnetic activity can affect your radii. We observed that the points deviate from the classical model at f spot equals 0, pretty much everywhere, but especially in certain places. This known issue with the measured stellar radii being too large for stellar models to explain is called radius inflation. Normally, we'd look at this plot and say, it's plausible that star spots can explain the spread in radii and move on. But now, with star spot filling factors measured with spectra, we can actually test the hypothesis that the underlying magnetic stellar models are giving us a more consistent answer for the radii of stars. explaining the bends and wiggles in isochrones. They're not calibration errors, but real physics due to the systematics of stellar activity. We can see that the lighter colors seem to be visually closer to the lighter lines on average, and colors seem to roughly correspond here in alpha per. We can repeat the same exercise with the Pleiades at an older age. And sure enough, even the departures from the standard unspotted isochrone seem to be well represented by lighter colors and an all-around good fit to the underlying data set. You can see domains where the spot fraction really seems to be very low, where the standard isochrone is preferred, and then domains where it's not so low. There are points that scatter up from this diagram, but we warn that perhaps there's some kind of binary contamination, but the underlying trend seems to be robust. Signals of radius inflation in stars, that they seem too puffy compared to standard models, seem to vary on an activity-dependent fashion, and they seem to quantitatively be consistent with star spots as underlying mechanism. We now place the two clusters together with a smattering of stars also from Upper SCO and from the Hyades. This is a radius inflation Rossby plot. We see the same features of saturation and decline that we pointed out in the previous diagram. But now, for the first time, in the discrepancy between measured radii and the radii that unspotted stellar model Webb predicted, which is the y-axis. So we argue that the underlying driver of radius inflation may be the one and same phenomenon, magnetic star spots, which work to suppress convection by blocking the outgoing flux of the star, forcing it to compensate and expand as a result, and also becoming cooler. The fact that the same picture persists across clusters of different ages suggests that this standard model of radius inflation may be a universal one for stars. So we've demonstrated that stars are spotty in open clusters, but they seem too inflated for standard stellar models. Let's go to the field with TESS. Let's take advantage of this SDSS5 Milky Way mapper and obtain multitudes of star spot filling factors, here shown in a Kiel diagram with point sizes corresponding to star spot filling factor. We have a lot of data, and we're releasing it as the leopard star spot catalogs, since leopards have spots. Here's a sneak preview into some of the relevant samples. The first 5 panels indicate the mean spot fraction in each pixel expressed by color in kind of different panels by metallicity as a function of absolute K-band magnitude on the y-axis versus TEF on the x-axis. The gray dots are the remainder of the sample that are binaries candidates, and we focus purely on the single stars due to our technique at present. And we use Gaia and metallicity-dependent color magnitude cuts to try to obtain the purest single star sample that we can get. You can see there are domains of enhanced activity that pop out of the data and intensify in different metallicity bins. We can now start doing statistics on these large samples. And there appear to be these really interesting trends that also pop out with star spot filling factor and TEF and other parameters. So here's f-spot versus TEF in a 2D histogram. We have enough stars to start making these kinds of comparisons and establishing mean relations to help the community better understand stellar activity in their targets and how to apply magnetic models to start interpreting these stars. But there's a good chance that you might even be able to find your star in the catalog, given how big that these catalogs will continue to grow to be. So before I talk about the last cool sneak preview from the full catalog, I want to talk about this idea from stellar evolution, that stars with convective envelopes and radiative cores can initially have the envelope spin down before the core has enough time to react, then over a period of time communicate through internal angular momentum transport mechanisms to then spin down the core during an epoch of core envelope recoupling. This theoretical scenario from stellar evolution, if over long enough periods of time and with sufficient internal torques, might manifest itself as an activity signal. So we see on this plot, this is a period TEF diagram, a bunch of cluster sequences are plotted from open clusters showing the angular momentum evolution of stars, but there are places where the rotation piles up. These rotational pileups exist between clusters such as Presa P and NGC 6811, where little to no evolution of angular momentum is observed for these stars for hundreds of millions of years. Core envelope decoupling appears to show improvements in how we model the rotational distributions of clusters, reproducing this observed stall and stellar spin down in models. But for all the internal angular momentum transport that's thought to occur in this domain, could it also have a magnetic signature at the same time? And so here is a plot of S-plot versus TEF. While looking at our data sets, we observed for the pre-CP open cluster, there's this strong kind of non-monotonic spike in the data in this very interesting temperature domain. So what's going on with these stars? So I'm again showing pure TEF diagrams, but I'm now showing predicted internal shears on the top panel. Warmer colors indicate strong internal shears in stars. On the bottom panel, this is showing the degree to which angular momentum has evolved in these stars. And warmer colors indicate stars for which core envelope decoupling has had a chance to operate. In the intersection of the warm colors, we see stars for which they have strong internal shears and sufficient evolution. Those are the highlighted red stars. Those are the stars for which we find evidence that they deviate from standard laws. So interpreting our models, we suggest that there may be this underlying shear front that drives this anomaly of overactivity in stars, keeping them active for far longer than previously expected due to core envelope decoupling. The orange band in this diagram of age versus TEF indicates our model predictions for where shear enhanced magnetism might be relevant. If these enhanced shears can irradiate stellar companions or systematically alter the stellar parameters or affect stellar evolution, it might deeply affect our understanding of such systems. So here's the really cool plot from the catalog. I'm showing Rossby on the x-axis again and f-spot on the y-axis. And I'm showing the mean relation from the Pleiades overplotted. And what we see is kind of this little, in this preliminary data at least, we see evidence for stars that deviate quite strongly from the standard relation. And in fact, if these slow rotators, which lie to the right of the saturated point, can in fact be active for extended periods of time, perhaps even gigayears, they could significantly affect our understanding of stellar and planetary evolution scenarios. For many of these stars, the stellar and planetary parameters may be off, even though they are genuinely in a domain of slow rotation. If radial shears and internal angular momentum transport can conspire to create these effects, we need to understand whether the enhanced activity in spots can affect companions, whether previously not accounting for these systematics may have affected our understanding of stellar and planetary physics. And I will conclude with that and take questions.
Questions? Bouma from Caltech, thank you for the wonderful talk and congratulations. Could you tell us what the selection function for the leopard catalog is again, please? I think you said it and I missed it.
Sorry.
The selection function for the leopard catalog, what stars are you releasing this star spot information for?
Right. Thanks for the great question. So we run everything on anything that we have sufficient SNR from Milky Way mapper. Or from any kind of apogee spectrum. So in principle, there's no, the selection function should be more or less the same as what apogee is selecting, which is actually really important when you're talking about actually having to be able to see star spot signals. We report the non-detections as well.
Tara Featheroff, UC Riverside. I'm curious how activity cycles may play a role into this picture for the slow rotators, and where would the sun lie when it's in its highest peak of activity versus when it's really quiet?
Right. Excellent question. So the question of whether activity cycles plays a role in for instance, the scatter about some of our mean relations and some of our plots here is a very relevant one. And we're going to be exploring that in some of our upcoming work by looking at repeat visits and looking at whether our measurements actually change beyond what can be explained with random error. As for where the sun would lie, we would expect it to lie way below some of these measurements. The sun, we think, should be like 0.1% or below in terms of f-spot. So.
Hi, thanks. Connie Arts, Leuven. That's of course great, but in all your clusters, there are also very many hotter, more massive stars that have radiative envelopes for which your spot models are not really relevant, but they have to lie on the same isochron because they are adhering to the same general physics. So have you taken your physical input such that all the stars in the clusters are well modeled by your isochrons in the hotter regime?
Yeah, so excellent question. So for the hot stars, we're kind of truncating our analysis to the cooler stars just for kind of simplicity, and also because, as you mentioned, some of the assumptions that we build into the model are kind of starting to break down at higher temperatures.
All right, great. Let's thank Lyra again. And perhaps appropriately for our last talk before lunch, we're going to hear about a star that gobbled up a planet, gobble, gobble, gobble. We're going to hear from Joel Ong about astroseismic identification and characterization of rapidly rotating engulfment candidate.
Thank you for the opportunity to speak. I'm here to tell you about an engulfment candidate, but in some ways, this talk is also about how we currently and may soon be able to get rotational astroseismology from TESS. So to begin, we've seen earlier today how one might get rotational rate estimates from surface modulations of spots in photometry, right? But if you peek in the frequency domain, you realize that most of that information lives here at very low frequencies. And the other way that we typically characterize surface rotation is by spectroscopy, which lives way over there in the frequency domain, right? But in between, there's also lots of interesting stuff, including but not limited to pulsations. And it turns out that seismology also permits us to measure rotation in some form. In particular, I will restrict my discussion here to solar-like oscillators, which pulsate in pure pressure waves. And these exhibit, as Dan said earlier, a dense forest of mode frequencies, all of which collectively constrain the internal structure and therefore the age of the star, for example. But in addition to structure and global properties, they also tell us about rotation. The way this works is that, as we've seen earlier, stars pulsate essentially in spherical harmonics, right? And different spherical harmonics are indexed by different integers, L and M. So modes of the same L, and this functions identically to quantum mechanics, pulsate with identical frequencies, but with different amounts of degeneracy. In the presence of rotation, modes which propagate in a prograde sense around the rotational axis will appear to you, the stationary observer, to pulsate more rapidly, compared to modes which propagate in a retrograde sense around the rotational axis. Moreover, the angle of inclination of the rotational axis determines which modes appear to pulsate the most when integrated over the visible disk, and which cancel out when doing this integration. So the observational effect of this is that in the presence of rotation, each single peak in the power spectrum splits into a multiplet of peaks, with the azimuthal degree of the mode, latitudinal degree of the mode, determining the number of components in the multiplet, and with the inclination of the rotational axis determining the distribution of power between multiplet components. And so this is, in a sense, how we use seismology to measure the internal rotation of stars. Now, with this in mind, we are now able to think more carefully about how we might measure rotation from seismology. The case study I'm presenting here is one that was published earlier this year, where we have a test light curve of a star with rather high lithium abundance, but which otherwise appears, at least initially, rather innocuous in its photometry. Now, if you take the power spectrum, you will identify peaks. And as you can see here, some of these peaks correspond to multiplet components. And what we're able to do with some effort is to fit a best fitting model of the seismology against these peaks in the power spectrum to derive estimates of the rotation of the star. When you do this, you realize that the star is rotating very fast, or it's supposed to be rotating very fast, as the seismology indicates, with a rotational period of just over 100 days. This is kind of problematic because this exceeds the angular momentum budget of any star this far up on the red giant branch. If you set a star rotating at more or less breakup rotational frequency on the main sequence and let it magnetically break up the red giant branch, it will end up with a rotational period of several thousands of days. So this kind of situation is very hard to produce under a standard single star evolutionary scenario. Right. The other problem, of course, is that the photometry doesn't tell you anything about such a rotational period. And we initially suspected that this rotational signal, which would have been produced by spots, might have been differentiated away by the standard error corrections applied to the spot light curves, which is what we use here. So we did our own photometry and found a more or less 100-day signal emerging. And to confirm that this was real and not induced by the rather primitive photometry pipeline that we just cobbled together, we also compared this against assassin photometry and found the signal also emerging. Right? So this collectively tells us that there's something very strange going on with this star. From seismology, we have a rotation rate that is very fast, and also some indication of some suggestive indications of perhaps rotational shear in the envelope. And from photometry also, we have a comparable rotational period once we've fixed the issues with TESS photometry. And we also have a spectroscopic rotational broadening that is, again, consistent with both of these measures of rotation. So collectively, these tell us that this red giant is rotating really way faster than it has any right to. In addition, we have further constraints from Gaia, which place bounds on the kinds of orbits that, say, a companion would be permitted to have in order to spin up this star. So let's put all these together. The Gaia RV scatter tells us that we can't have a companion with a semi-amplitude larger than indicated by the red curve. And we can't also spin a star up to a period of 99 days if the companion doing the spinning up is at an orbital period of more than 99 days, right? So both of these shaded regions are excluded. And if you were to place a companion in the unshaded region, it turns out to be also tidally unstable. So these collectively suggest to us that such a rotational configuration would have had to be produced by some kind of engulfment scenario. Okay, so what? Well, with all this in hand, we could, place constraints on the tidal quality factor of orbital damping and the engulfment mass. But more generally, we could also use this indirectly as some kind of constraint on spin-orbit interactions between stars and planets. And this is particularly interesting in the light of new discoveries about spin-orbit misalignment also from seismology. So Nick Saunders is going to talk a little bit about spin-orbit interactions later this week. But I also like to point out some recent discoveries at the TASS conference a couple of weeks ago, where we've now been able to determine not just differential rotation rates from seismology, but differential rotational directions. And that is to say, the constraining that the core and envelope are rotating around axes pointing in different directions from seismology. This is from Kepler, of course, but with enough patience, TESS will also get us there. So the outlook for TESS as far as finding similar engulfment candidates is concerned is fairly encouraging. TESS provides us with astroseismology, particularly in the continuous viewing zones, which in turn give us some insight into the underlying astrophysics of the structure of these stars. And with the help of ground-based photometry, such as ASSASSIN, we also are able to compensate for some of the lingering issues in its photometric stability. It turns out from this analysis also that any seismic rotational signals that are present in TESS data are fairly robust. They survive the aggressive detrending that has been applied to the spotlight curves, for example. And if we have the patience to wait, we may one day have light curves and therefore power spectra of comparable temporal baseline and therefore quality to that provided to us currently by Kepler. And that is an opportunity for us, for TESS also to teach us lots about spin-orbit interactions across the whole sky. Returning to this star in particular, we've shown, hopefully, that this is a lithium-rich, rapidly rotating, and likely single red giant. And its very rapid rotation has been confirmed independently now using ground-based photometry, space-based photometry, seismology, and spectroscopic rotational broadening. right? And other constraints from Gaia also strongly suggest an engulfment scenario when we put all of them together. We are able to place some constraints on its engulfment age and mass, and that's in this paper shown here. And I'd be happy to take questions.
Lots of time for questions.
Hello, very nice talk. Ling Hao Ma from Princeton. So I'm wondering if such engulfment happens, is that going to alter the internal structure of the red giant so that it's like may modify the wave cavity that you do your astroseismology on?
Okay, there's two parts to this. So first, we are certain that it will modify the internal structure of the red giant, right? But there's two parts to what happens next. The first is that, I have a backup slide about this, I think. Okay. Yeah, so the first is that the timescales for thermal relaxation of the structure are much, much faster than either the magnetic breaking timescale or the spin down timescale from just the usual structural expansion over the course of evolution of the RGB, right? So there will be a transient event where you get a spike in photometry, for example. And I think that there was such an engulfment event reported also earlier this year, but that will go away much more quickly than the rotational signal, which will remain. The second thing is that this is a red giant that is quite far up the red giant branch, right? And so if there are perturbations to the structure, the thing that dominates, however, is going to be essentially the convective part of the star, in which P modes propagate. And these P modes, since the star is basically fully convective in the envelope, are very well approximated by the mode frequencies of a fully convective holotrope with a bunch of glitches. So we do not expect that the engulfment will modify the structure so much that P-mode seismology becomes infeasible, which is what is used here.
Yeah, thank you.
Hi, Josh Wynn from Princeton. You mentioned the possibility of determining whether the core is rotating in a different direction from the surface, but has that been achieved, or are you saying that it might be achievable with more data?
That's something I presented at the task meeting a couple of weeks ago. I'll be happy to talk about it in more detail with you later if you wish.
Great.
Connie Aasleuven, just for the fun of it, Joel, can you exclude that the star swallowed a whole bunch of planets instead of just one, massive Jupiter?
We cannot. So you are right. It could have been multiple engulfment events. It could also have been a stellar merger very, very, very long ago, but that would be also quite unlikely given other constraints that we discussed in the paper.
Any last questions? Going once, going twice. Otherwise, let's thank Joel and all of the speakers of this session. Avi, anything to say?
We have a brief announcement by Hannah. You can go up stage.
Hello. All right. Okay, there should be a slide coming up. In the meantime, I'm Hannah Jane Condell. I'm from NASA headquarters. I am the soon-to-be former program scientist for TESS. Again, Josh Pepper over there will be stepping up as the TESS program scientist soon. We're working on the transition right now. But I just wanted to make a brief announcement. So this announcement just came out. There's a new opportunity in ROSES to get funding to do research on mass measurement, so exoplanet mass measurement. If you're familiar with the former EPRV call, this is an expansion of that. But rather than just focusing on extreme position radial velocity for getting mass measurements of exoplanets, we're expanding that to also include astrometry. So this is not necessarily to fund your observational work. This is to look at how best to get our sensitivities, so reduce the systematics and either EPRV, or astrometry down to the sensitivities we need to actually measure masses of Earth-like planets. So if you have any questions about this call, please, I will be here all week. You can come talk to me. My contact information is up there. This QR code takes you directly to the solicitation, so take the photos you need. But that's all I had to say, and I will stop getting in your way of lunch. Thank you.
Welcome back from lunch. I hope you found something to eat. We are once again back on the exoplanet session. Okay, so the stellar people are more enthusiastic, apparently. Okay, my name's Hugh Osborne. I'm chairing this session. And first up, we have Sydney Vac, who's going to tell us a little bit about young exoplanets with TESS.
Hi, hello. I'm Sydney Vac. I'm a second-year PhD student at the University of Southern Queensland, and I would first like to acknowledge traditional owners and custodians of land on which this research was conducted. I was joking that I would definitely be able to use the clicker, and now I can't. Okay, so yeah, I'm going to be presenting our work on the occurrence and evolution of small young planets with TESS in co-moving populations. I've highlighted the authors that are here, so if you have complaints about the talk, bother them, not me. So I really hate to do this. Period radius distribution of the Kepler transiting planet population. And just to go over some brief definitions, I'm going to be talking about small planets. So this is between 1 and 8 Earth radii for this talk. And we've subdivided this into the classical 3 subpopulations of super Earths, mini Neptunes, and then super Neptunes. And so thanks to the wonderful mission that Kepler was, we were actually able to understand the demographics of these planet types. And we know now that mini Neptunes and super Earths are the most common outcome of planet formation around FGK type stars. Whereas the super Neptune bin is extremely rare around the mature planet population, in the mature planet population. So now that we know that this is what planet formation creates, we need to ask the question, okay, how are these planets born and how did they evolve? So I'm going to be talking about 2 extremes and 2 extreme cases of planet formation. First, we have the volatile depleted scenario, where the planet forms in an environment that's depleted in volatiles, and it results in a planet that's engulfed in a hydrogen-helium dominated envelope. In contrast, we have scenario 2, which is a water-rich formation. So this planet forms in a volatile-rich environment, and the resulting planet has a higher mean molecular weight atmosphere. And this is like the steam-dominated atmospheres or water worlds that you all have heard a bunch about. However, when we evolve these planet populations forward, through just the traditional like transit and radial velocity surveys, they produce a mature exoplanet population with the same bulk densities. So we need to look to the youngest planet population to see, can we distinguish between these 2 different formation scenarios? So luckily for us, the evolution of scenario 1 versus scenario 2 is quite different. So specifically, if we look to the first 100 million years or so, the evolutionary tracks of a hydrogen-helium dominated envelope is vastly different than the evolution for a water world. So if that is true, then in theory, the occurrence rates of these planets should also vary as a function of age, and they should reflect either the water-rich formation environment or the volatile depleted formation scenario. So I'm going to be presenting our results on the occurrence rates of short period small planets younger than 200 million years. So in this time range where these evolutionary paths are most divergent with TESS. And just for some short definitions, short period, smaller than 20 days, and small planets, again, shorter than 8 Earth radii. If you want to read the paper, that's the QR code, and you can stop paying attention to the talk. So how do we do an occurrence rate calculation for this? We were able to correlate a population of known young moving stars in co-moving populations, thanks to this wonderful work that really used Gaia to help us understand the true population of young stars in the solar neighborhood. We then developed a planet detection pipeline. So we have all these stars, and now we need to search and find which planets are actually around these stars. So then not only can we search for planets, we need to understand how well can we actually detect planets. So for every single star in our survey, we did 1,000 injection recoveries to understand how well we can recover planets on a star-by-star basis. And then I'm sure many of you guys can name maybe 1 or 2 young planets off the top of your head. That is very true. There's not that many. So we really need to be aware that we're working with a small number of statistics, and also 7,000 stars, that's also quite small in the area of TESS. So we used a population Monte Carlo approximate Bayesian computation to calculate our occurrence rates. Okay, so what did our planet detection pipeline find? It recovered all known published planets that were within our stellar parent population, all TOI planet candidates within our stellar parent population, and 4 new planet candidates. And I'm gonna take the opportunity for some free advertisement right now and talk about these new candidates. Specifically, all of the new candidates are younger than 100 million years. So when we think back to our different tracks of evolution, these are all occurring in that time frame when the evolutionary paths between water worlds and the hydrogen-helium dominated envelopes are most divergent. So 2 systems I'm going to be talking about in particular are TIC 434398831 B and C, and TIC 88785435B. I didn't get a TOI, I'm really sorry. But thanks to all the wonderful work of my co-authors, I can now present these also as published planets. And one of them is on the archive today, if you want to read it. And that's this one. That is a multi-planet system around a 61 million year old star. This is the light curve from TESS in sector 33 from QLP. We have an inner transiting mini Neptune at about 3.6 days, and an outer transiting super Neptune in a 5 to 3 mean motion resonance. So after we found these in our detection pipeline, we applied for KOPS time, and these are the phase folded KOPS observations of these transits as well. And so because this is in a co-moving population that's not necessarily well characterized and like well studied, such as SCO-SYN or Orion, we wanted to search and ensure that like the age for this stellar population is well studied as well. So we used TRACE to perform a lithium survey and measured lithium equivalent widths for members of Thea 116. And we also analyzed the rotation distribution of the cluster, and we're able to age the system at about 61 million years, or sorry, the cluster. Another side note, the other one is a super Neptune in UCL. It is a 4.8-ish Earth radii planet orbiting at 10.5 days. It is an established literature member of UCL. We were able to get ground-based follow-up to confirm the planet. And now back to occurrence rates. Okay, so now we have this planet population, and we want to understand what is the statistical significance of this population. You know, as Elizabeth Newton said, if we look at it by eye, it looks like the young planets are much larger than the mature planet population. So just to reference back to the mature planet population, the Kepler occurrence rate tells us that there are about 14 mini Neptunes per 100 stars, specifically FGK type stars. And super Neptunes, as I said, are really rare, with less than 1 super Neptune per 100 FGK type stars. So because TESS is wonderful, as we all know and love, we were able to do 2 independent occurrence rate calculations, one with Spock. So the Spock results were a slight increase in mini Neptunes to 35 plus or minus 12 mini Neptunes per 100 stars. And super Neptunes, we see an increase to about 27 plus or minus 9 super Neptunes per 100 stars. Really sorry, got to go through the numbers again. And our QLP occurrence rate calculation also follows in a similar suit. We see a slight increase in mini Neptunes around these youngest stars, with 22 super Neptunes per 100, or mini Neptunes per 100 stars, and about 13 plus or minus 5 per 100 stars in the super Neptune bin. So I hope by eye, all of you guys can see that the super Neptune bin seems much different when we look at the youngest planet population in comparison to the mature Kepler distribution. So going back to this evolutionary path, if we look in this first 100 million years or so, the volatile depleted formation scenario predicts an excess of super Neptunes, but then over time will evolve down to represent the Kepler distribution through photoevaporation, boil off, and thermal contraction. In contrast, because of the higher mean molecular weight, the volatile rich formation scenario predicts a fairly steady state population, meaning the youngest planets should have a similar occurrence rates to the mature distribution. So we found this excess. Now, how significant is it? In SPOC, our excess is a 2.9 sigma excess, and in QLP, it's a 2.8 sigma excess. So we found this excess, and now we need to independently validate our results to ensure that they're actually accurate of the population we're looking at. So we did this through a forward modeling exercise in which we assume a planet population purely born from either the volatile rich or the volatile depleted formation scenario, applied our pipeline detection efficiency, and looked at how many planets should we recover if scenario 1 or scenario 2 were the absolute ground truth. So looking at scenario 1, planets born in a volatile depleted formation scenario are born much larger and then over time evolve down. And so this is a synthetic occurrence rate in both period and radius space. And so in contrast, because the water-rich formation scenario predicts a fairly steady state evolution of the occurrence rates of planets, we're able to just adopt the Kepler statistics for our young planet population. So these are the number of planets we actually recovered. And if scenario 1, the volatile depleted formation scenario, were the ground truth, this is what we predict to find. So we see a fairly strong agreement. However, there is a slight excess in the 6.2 to 12-day period space then. But in contrast, if the steady state or water-rich formation scenario were the ground truth, this is the number of planets we predict. And we see a very strong disagreement in this, specifically again in that 6.2 to 12-day period then, and also in the super Neptune then. So if we look at this, we can start to say, well, the youngest planet population starts to agree with one formation scenario rather than the other. However, it's not absolute fact, and that's where Eve could come in and work really well, as Ward talked about earlier. And so with that, I'm just going to put up my conclusions. The youngest planet population is most consistent with a population that's formed in a volatile depleted scenario, paired with contracting hydrogen helium envelopes. Thank you.
Thank you very much, Sydney. Do we have any questions? So there's one over here.
Hi, I'm Damoto from the University of New Mexico. I'm wondering if you could say a little bit more about these differences between your occurrence rates for SPOC versus QLP, and whether you think that just means like a difference in dissection limits between these two pipelines or something else?
I actually prepared for this. So the stellar populations are inherently different, right? So SPOC stars are kind of pre-selected. So say you look at a star in QLP and you see a planet signal, then you can say, oh, hey, let's get this with the shorter cadence data. So the stellar populations are different. So if we look at the QLP population, it's more reflective of just a magnitude, or sorry, a volume limited sample, whereas there are biases induced by the SPOC selected star sample.
Any other questions? Yep, this one here.
Hi, Elizabeth Newton, Dartmouth College. Lovely work, Sydney. Could you tell us a little bit about your planet detection pipeline? And I'm particularly interested in how you developed and specifically trained it.
So it is a lot of visual vetting. So we just used a spline for the stellar variability, and then a BLS, and more detailed we can talk later. But really it's just looking at the stellar variability, trying to remove the rotation-induced signatures in the light curves, and then searching for transits there. Moving forward, we're starting to look at combining flare modeling with this to better understand the true features of young stars in their light curves.
We had one over here, question. The mic's coming.
Thank you. Daniel Bayliss, University of Warwick. I was wondering whether the Kepler population and the SPOC or QLP population had different metallicities, and maybe that could account for some of the occurrence rate rather than just age?
So we're not working with a sample large enough to where we can truly separate the population down into metallicities. However, we are working with an average of solar metallicity after doing a spectroscopic survey of the stars, but that's not a part of this paper or this work right now.
We maybe have time for one quick question. So there's one hand up Okay.
Hi, Sam Grunblatt, Johns Hopkins University. I was wondering if you tried testing different limits on what you're calling young here, and how sensitive you are to basically that cutoff, if that changes if you were to looking at things that were up to 1 gig a year, for example.
So for this work, we just looked at 200 million years. Our next work is expanding out to 1 gig a year, and we do have a much larger stellar population with about 80,000 stars with QLP light curves. That also just takes much longer to visually vet. So we did this. So for this, we do account for the possibility that some number of stars are indeed like field contamination. So we did a rotational analysis of all of the stars to see like if we expect rotational signatures in the light curves, are they there? And then filtered for between 10 to 30% of the stars being non-members, and that is accounted for in our occurrence rate calculations.
Okay, so let's thank Sydney again. Next up in this young stars and planets section, we have Rachel Fernandez, who's going to be telling us about tracing the evolution of short period exoplanets, insights from young stellar clusters.
Hi, everyone, and I'm glad I'm going after Sydney because now you know why young planets are important. So let me show you something new that nobody has ever seen before, the radius valley. So the radius valley is such an important discovery in our field that it has led to so many other demographic and planetary analyses. One of the things, let me go take a step back. The radius valley, just as a reminder for those who forgot, it's a single peak at the super Earth's regime and another peak at the sub-Neptune regime. It's a bimodal distribution, and we wonder why. To be fair, if it was a unimodal distribution, we'd also be wondering why. So we always wonder how did the radius valley come to be this way? There's a few theories out there. To very, very, very briefly summarize them. They could be planet formation theories, they could be planetary atmospheric evolution theories, or they could be planetary migration theories. And each of these have their own sub-theories. But what is most likely is that it's some combination of all three. Planets don't just evolve, they have to form, and they do indeed migrate. And how exactly all of these processes come into play is very complicated. And one way we can disentangle that is by looking at demographics as a function of time. So with TESS, we can finally do that. Unlike Kepler, TESS is an all-sky survey. And so we can finally search for these planets in young clusters. And we search enough that we can actually do demographics on this. For my work, I rely on full frame images because it's the most de-biased data set. It looks at everything. The primary mission has 30-minute cadence data, and the extended mission 1 has 10-minute cadence data. The first work I will be talking about works on primary, and the second one on the extended mission 1. So when I started this as a very bright-eyed graduate student 5 years ago, there were 9 known confirmed planets or planet candidates in about 5 young clusters and moving groups, and that's what we decided to build our code and test all our methodology on. So how do you find young planets? The short answer, it's extremely hard. I spent 3 years on it. And so I created a tool called pterodactyls that can extract the light curves, detrend light curves, specifically for young high variability stars, search for planets using TLS because we're looking for relatively smaller planets, and also vet the planet candidates currently using EdiVetter and also Triceratops. Now let's put this into context. Kepler, for small planets, or I would say everything 1.8 to 10 Earth radii, everything within 12 days, I would like to take a moment to just appreciate that there is a Y error on this plot. It'll come into context more later once you see the TESS error bars and the small number statistics we're dealing with, but Kepler did such a good job that there's a Y error, you just can't see it. Our work found a very high increased occurrence rate for FGK stars within 500 million years old. After we did this work, more people came out and said the very same thing. For example, Jesse Christensen looked at K2 data on Persepi and also found something very similar. And as Sydney just spoke about, she also found an increased occurrence rate. So it seems like what the consensus here is that regardless of the age and the exact parameters we're looking at, there is an increased occurrence rate compared to Kepler. However, the two studies that I'm pointing out here are biased in the sense that I only looked at stellar clusters in which there were planets, because that's what we were testing our methodology on. And that's why it's higher. And for Persepi, we only looked at Persepi, and it's not fair to say that Persepi is the norm for all stellar clusters in its age. So what we did after the study, once we had established our methods, is to go and expand our sample using EM1 data. We started with about 32 young clusters from the Gagné-Banyan Sigma catalog and also Gaia DR2 bona fide lists. We started with a sample of about 11,000 stars, out of which 7,000 were looked at the test with the TESS EMIs, EM1. And out of that, about 6,000 were available with SPOC. Now, out of that, only 1,377 were single FGK stars. And we know that because we did our own stellar characterization, taking into account the age of the star, using photometry and spectra where we could. So that is our stellar sample that we're working with. Our planet sample, since 5 years ago, now we have at least 30 known confirmed planets or planet candidates in these clusters. For the purposes of our study, I will be focusing on this specific region, which is 1.8 to 10 Earth radii and 1 to 12 days. You might say that a 10 Earth radii is a Jupiter. That has been proven wrong. There's a few posters out there, I forgot to write down their numbers, that planets the size of Jupiters that are young actually have Neptune masses, so just really inflated planets. So there are actually no hot Jupiters that are known in this sample. They're all Neptunes or sub-Neptunes. So this is what I will be focusing on. We had 14 recovered planets. The non-recovery were mostly additional planets in multi-planet systems, or those discovered around very faint stars with K2 that were hard to recover with TESS, but mostly those were long period stuff. So how does occurrence depend on period and radius? When we take our entire sample, that is 10 million years to 1 giga-year, we find that the slope of when we fit for period and radius dependence doesn't really change, but there is definitely an increased occurrence either way we fit it. Now, I was a little disappointed when the slope didn't change, so why not split the sample to see what we can do by splitting it by age? So we split it to 10 to 100 million years and 100 to 1 giga-year. It's log equal bins, and the number of planets in each bin are equal as well. That was just a coincidence. What we find is that the period slope flattens over time. That could be sub-Neptune slowly migrating in with time from slightly beyond 12 days or even further beyond, it's unclear. And for the radius, we see that first the radius slope steepens and then flattens over time. What we think is happening here is probably some combination of migration and also the sub-Neptunes shrinking in time and occupying space below where the super Earths are once their atmospheres are stripped, and so they shrink. Now, what do we expect to see when we put it all back into context with time? Just to manage expectations, this is not a real plot, this is just a figure I made. So if disk migration and or in situ formation is the dominant and the only mechanism, we would expect the occurrence to be flat with time, nothing changes. Atmospheric mass loss will show a decrease in occurrence rate with time when it comes to young versus old planets. And when it comes to post-disk migration, we would actually see an increase because the number of planets keeps increasing in the same period bin. So let's put this into context. What are my real results? It's going to look a little bit like this. And this could have been me in the past 3 months with each of my collaborators. So again, this is the Kepler point that we had before. Our point for 10 to 100 million years is consistent with that of Vach et al. 2024. We find an increased occurrence rate. Cool, it's increased. That's what we were expecting when it comes to photoevaporation and atmospheric mass loss. Then we have our second bin, which is 100 to 1 gigayear, and that shows an even higher increase. And we were not expecting that. We were expecting if atmospheric mass loss was dominant, it'd be lower and fall in line between the 10 and 100 million years and the Kepler population, but that is not what we find. So what does this mean? What could it mean? The error bars, again, very large, it's a log scale, but what could this possibly mean? What we find is that this is, in the first 10 million years, whatever we probe after that has already been sculpted by in situ formation and gas disk migration. So we cannot probe that region. We cannot say very much about it yet. This increase is likely dominated by tidal migration, possibly, because that's the only reason we would see an increase, at least according to me. If a theorist disagrees, please come find me. The paper is not yet submitted. And finally, what we find is that maybe that final decrease is when atmospheric mass loss, it's dominated by atmospheric mass loss and not really as much tidal migration. Now, one way we can test whether or not atmospheric mass loss is really at play over here is that when these Neptunes are shrinking, they're not disappearing, they're falling into a smaller radius bin that with young planets, we do not currently have the detection of sensitivity to actually detect numerous of and actually do proper demographics of, but we do with Kepler. So if we include the small planets with Kepler, it's actually consistent with the point that we see between 100 million years and 1 gigayear. And this is a very cool picture of planet formation. It is very, very preliminary. We are in the very early stages of young planet demographics. This was done with 15 planets. Sydney's work was done by the same order of magnitude. Kepler, we're dealing with thousands of planets. If we want to shrink these error bars, we need to find more young planets in order to do this better. Not just that, our understanding of young planet formation is severely incomplete. And what we need for that is we need to simultaneously map out at young ages the population of small planets so that we can actually account for how much is shrinking with time. And doing that with age and how they interplay is very important. Same thing, if we want to trace how migration plays a role, we would have to also map out how planets at larger orbital periods change with time. Do they move in? Are we seeing some movement there? We also need mass, density, compositions to better characterize these planets. There's a giant planet or like a giant Neptune at 2 days. How did it get there? We can say something very preliminarily from theory, but what would be useful is actually studying the volatile compositions of these to see whether they could have formed where they are or did they form in a more volatile, rich environment and then slowly migrate in. And finally, like always, we always need more planets. We want to, if we want to say something more definitive, those error bars have to shrink. And also we need finer sampling by age. 50 million year bins would be amazing. Right now it's log equal massive 100 million year bins, but that would be the most useful so we can really get an accurate picture of planet formation. And with that, this is my summary slide because I didn't want to write all of this down again, but this is the entire picture of the whole talk. So with that, I will take any questions.
Perfectly timed, well done. Do we have any questions?
Hi, this is Sharon Wang from Tsinghua University. Thanks for a great talk. I have a question about the distribution as a function of period, because we know the Kepler super Earths tend to peak around 10 days, which is thought to be planet migrating in and stopping at the inner edge of the disk. For the first two pink or magenta points you plotted down there, presumably at 10 million years, the disk has already dissipated, so the planets should have already stopped at the 10-day period where they parked, but your results seem to suggest that they keep coming in. So do you think this is sort of at a conflict with the 10-day parallel?
Personally, I don't think so, just because 10 and 12 days is not that big of a difference in my head. And also, one thing that we did try with our data is to see if there were any trends beyond 10 days that we could actually fit to see if there's a slope and then flattens just like Kepler, but we unfortunately just don't have that kind of planetary resolution yet. but we do find the same slope. So maybe that is indeed planet formation.
Okay, thanks.
We have time for more questions. There's one here.
Yeah, thanks for a great talk. This is Ling Hao Ma from Princeton. So I don't exactly remember the numbers, but if you believe that tidal migration is happening around 100 million years, isn't that going to be the phase where the star is still like fastly rotating?
Can you repeat that again?
Yeah, so what I'm saying about is the star, I don't remember if it's exactly this age, but the star at 100 million years might still be rotating pretty fast. So if you want the tidal migration to be very efficient, the star cannot be rotated so fast. Like if it's faster than orbit, and it's actually going outwards, like that.
Yeah, it could be. That's something I want to look into in the future, but currently I don't have. These stars are definitely rotating pretty fast, but fast, I have learned, is very relative. I have seen less than half a day rotations and also less than 10-day rotations, but I'd be happy to chat with you a little bit more to see if there's a trend with that as well.
Okay, great, thanks.
Yeah.
Okay, let's thank Rachel again. Okay, next in this young planet session, we have Madyson Barber, who's going to be telling us about a 3 mega-year transiting planet in the presence of a misaligned transitional disk.
That is not the beginning.
Jump forward. There should be a back button from there.
It's giving away all my secrets. Okay. Hi, everyone. My name is Madyson Barber. I am a second-year graduate student at the University of North Carolina at Chapel Hill, where I work with Dr. Andrew Mann. And I primarily work on the detection and characterization of young transiting systems in TESS. So I will throw up the obligatory period radius diagram. So with Kepler, we have a large population of known transiting systems that are primarily older. This is shown as the background contours here, adjusted for detection bias. And a relatively small set of young transiting systems. Those are shown as the colored circles here, colored for their age, and all of these have been found within young stellar associations. And as Dr. Elizabeth Newton mentioned yesterday, it's very important that we look for these planets in young stellar associations because their ages can be precisely derived based on the parent population. Young field stars can get an age determination, but it's generally not precise enough for the kinds of statistics we want to do. We're ultimately curious on how formation and evolutionary pathways look, so we need precise enough ages to create a sort of timeline with those planets. However, a lot of these young systems you may recognize. Bonus points if you recognize HIP 67522C that we posted to the archive just a couple weeks ago. But these young systems have been very powerful tools for understanding the early life of young planets. Some of these planets have atmosphere observations with JWST to say something about the atmospheric composition. Some of them have mass measurements, which have shown that young planets are less dense and more puffy than their older counterparts. And some of them have transits which show spot crossings, which have been able to say something about the host star and the spot coverage on the host. But something you'll notice is that these systems only go down to about 10 million years old, and we lack the truly infant systems, less than 10 million years old. And that is where our survey comes into play. So TIDI is a new search survey looking at young transiting systems. Right now, we're particularly interested in the discovery of systems less than 20 million years old. And we're ultimately trying to figure out formation and evolutionary pathways and occurrence rates of these young planets. So part of this search, we looked in the Taurus-Auriga Association. So Taurus itself is made up of 17 distinct subpopulations, ranging from 1.5 to about 15 million years old. And part of the D4 North subpopulation, we identified target this long number. So this is a M0 pre-main sequence T Tauri star. Like I said, part of the D4 North subpopulation. Daniel Kowalkowski out of UT Austin did a large study on the Taurus molecular cloud, and his age determination was about 2.5 million years old. Our isochronal models of the system shows it's about 3.3, so we're quoting about 3 million years old for the system. This is a class 2 protostar. This means the star is done forming or just about done forming, and the protoplanetary disk is beginning to dissipate. This disk will dissipate from the inside out, creating almost ring-like structure, and this is known as a transitional disk. And in fact, if we look at previous observations of the system, we do see a near face-on transitional disk. So this sort of a blobby looking plot, we don't think this is a true characteristic of the disk itself, and rather has to do with the quality of the SMA data. So on the right here, I have some ALMA images of transitional disks, just if you're a visual person like me, a better idea of what the system might look like. And normally, if we are looking for transits, this might be a cause for concern. If we have an expected geometry for a transiting system, we're expecting edge-on rotation, an edge-on planet. So if we have a disk following planet evolution and star formation theory, if the disk is present, it will be in the same plane of rotation, therefore blocking the star and any hopes of seeing a transiting signal. So if we're seeing a near face-on disk, we're expecting a near polar-on star, and therefore no hopes of a transit. But based on VSign I observations of the star, we do believe that it is near edge-on rotating, and this has allowed us to discover the transiting planet in the system. So across 6 sectors of TESS data and 17 transits, we have determined that the period of the planet is about 8.8 days, which is just shorter than the rotational period of the star, which is about 11 days. We do find that the planet is just shy of 1 Jupiter radius, and based on 6 radial velocity observations taken within 1 stellar rotation of the star, we get an upper mass limit of about 0.3 Jupiter masses. This is consistent with the puffy nature of young planets, so don't worry if it seems like it's a little light. We were able to do follow-up observations from the ground in 3 additional wavelengths. The transit duration is quite long, it's about 6 hours, so we were only able to observe partial transits of the system. Nonetheless, we were able to see that the transit happened when we expected it to happen, at the depth we expected it to happen with, and because it's from the ground with our smaller aperture, it is from the area of the sky we expect it to, so most likely on the star we expect it to be. And then using other follow-up observations as well, really to nail down that we are for sure this is a planet on our star. We looked at radial velocity measurements. Like I said, we had 6 radial velocity measurements within our campaign, but just in case we got a weird season of the stellar cycle, we looked at archival radial velocities as well, and we find that those are consistent with our measurements, and we were able to completely rule out a stellar mass object. Additionally, we looked at imaging to check for any foreground or background stars that might be causing or mimicking our transit on our star. We are in an extincted region of the sky, so we don't have to worry too much about any background stars, but this is a good double check. And we, in fact, don't see any stars coming in or out of view as the star moves across the sky. And if that's not exciting enough, we have a planet in the presence of a highly misaligned disk. We also find that the system has a wide binary companion. It is a low mass star, about 0.2 solar masses on a 600 AU orbit. And the interesting thing here is that the rotation of the stellar companion, the wide binary, is at the same inclination as the planet's orbit. So overall, we find that the wide binary companion, the planet rotation, and the stellar spin are all in the same inclination, but highly misaligned in comparison to the protoplanetary disk. I do want to point out here that there is a missing angle in between the stellar spin axis and the planet orbit. We are not sure if it's in true prograde, but the inclinations do match. So with that, IRAS 04125290 becomes the youngest transiting planet known to date and the only transiting planet known to be in the presence of protoplanetary disk. The planet actually rivals to be the youngest planet, which is currently occupied by a directly imaged planet. The difference here is that directly imaged planet is high mass, so greater than 1 Jupiter radius, or 1 Jupiter mass, so will likely end up as a brown dwarf or a hot Jupiter, while our low mass planet will likely end up around a Neptune-ish sized planet. There's a ton of follow-up work to be done on this system, a lot of which we are actively working on. Something we're interested in is the mass. Right now we just have an upper mass limit, but it'd be really nice to have a mass measurement. So we were approved for a long-term radial velocity campaign to try to figure that out. But because of the low mass and the relatively large radius, we do believe that there is a large extent of atmosphere that would be ideal for follow-up observations with JWST. And something else we're looking at is the system alignment. So the geometry of the system is pretty weird, right? We're really curious to see if the planet rotation is in prograde, retrograde, somewhere in between. So we have been approved for a Rostrom-McLaughlin measurement to try to get a better idea of that geometry. And finally, the discovery of the system motivates further efforts to look for these truly infant planets. The better we can understand the prevalence of warp transitional disks, the better we can target surveys to look at these baby systems, look for these baby systems. So with that, I will throw up my summary slide and leave you all with a quick lesson on the power of manifestation. My advisor, Andrew Mann, made a joke that we just need to find one 3 million-year-old planet and the proposal we're writing will go through. And Andrew Vandenberg, 2 weeks later, was telling us our signal looked good. So if Andrew Vandenberg thinks it looks good, you must be onto something. Thank you.
Okay. Do we have any questions from the audience? I can start with one, if not. So often when transiting, planet hosts have companions. That makes confirming them as the true source of the transit to be difficult. How did you confirm that the target star is the source of the transiting planet?
Yeah, so luckily for us, the stellar companion is far enough away that with our ground-based observations, we were able to get it out of the aperture. So we don't have to worry about it. We're pretty certain it's on our star.
Thanks. Any other questions for Madyson? Yep, there's one here from Heath.
Hi, so one of the hypotheses for transition disk is that they are created by planets. So do you think this is the planet that is responsible for the gap in the transitional disk?
I will be completely honest with you. I had never done any sort of disk work before this, so I am not super sure. Maybe somebody who wants to figure that out can let me know.
Okay, we have a question here from Ward.
Ward Howard C. Boulder, great talk. I was curious about the bump in the transit. Was that a small flare?
In one of the ground-based transits?
I think so. There we go. Yeah, in the PS panel.
I'm not sure. It could just be random scatter in the data. This Z transit is 2 transits stacked on top of each other. That is something that we could look into and see maybe it is.
Okay, one final question for Madyson. No? Okay, well, let's thank Madyson and we'll move on. Okay, so next up we have Nardiello Domenico, who's going to be telling us about young exoplanets with TESS.
Okay, thank you. Thank you for giving me the opportunity to talk about the young exoplanets observed by TESS and analyze it in our projects. So let me introduce the importance of young planets and of knowing the inaccurate age of the stars with an example. This is a star that hosts an interesting planetary system formed by 5 exoplanets. But if we look to the age of this star has an age of 6 gigayears plus minus 4 gigayears. So the star is young, the star is old. We don't know, and at which evolutionary stage is the planetary system. So as we see, and also in the last talk, looking to reconstruct the formation and evolutionary history of the planetary system is important to know their age. And to know their age, we have to look to the stars inside the stellar clusters, co-moving groups, stellar association, for which we are able to obtain with extreme accuracy the age of the stars and the age of the stars that host exoplanets. How? With many methods. Some of the most simple are the isochrones or the gyrochronology. Not only, but looking for stars in stellar clusters and association allow us to obtain accurate stellar parameters. And accurate stellar parameters means that we are able to obtain accurate information on the planetary oscillated by these stars. Finally, looking into different stars in different stellar associations and clusters with different ages allow us to obtain information on the evolutionary history of the planets. So, focusing on young exoplanets, and for young I say less than 1 gigayear, we are able to obtain information on the planet formation, orbital evolution, and planetary radius evolution, as we see also in the last talks. So why the sample of young exoplanets is too small if compared to the sample of to the large sample of all the exoplanets? The answer is simple. You know, it's the activity. Young planet means activity. Activity introduce problems both in the photometry and in the radial velocities. Photometry, we have a strong variation of the light curve, and that can mask the transits of the planets. And strong, robust trending methods are mandatory to detect the transit of the exoplanets. Anyway, if the planets have a long orbital period or are small exoplanets, it's very difficult to detect them. And this is an example of one of the first exoplanets discovered by TESS, that is the TESS AB. Elizabeth Newton talking about it also yesterday. This is the first sector. Here there are 3 transits. One of them fall in the degraded but it was detected because of the trending method used for detect them. So in the radial velocities, the activity worsening the spectral information, especially the radial velocity dispersion. And here you can see that the radial velocity dispersion is a function of the age, and for very young stars, we have variation of the radial velocities up to 1 kilometer per second, compared to the few meters per second of the exoplanets. Moreover, star spots distort the spectral lines and can introduce also fake signals of the planets. Anyway, if we use information from the spectral indices like H alpha or S index and the photometry, we can minimize the effect of the activity also on the radial velocities. And a bit of advertisement for my code. This the use of a good pipelines for the extraction of the light curves of a stellar of young stars, like my code. That here there is an example of between the PDC set light curve corrected light curve and the pathos corrected light curves. You can see that my code preserves the variability of the star. This is very important also to constrain the age of the star. So combining good light curves with radial velocities, with high precision radial velocity, for example, collected with the HARPS Nord facilities. This is the GAPS collaboration project I am in, and we collect this radial velocity. We are able to constrain the masses of the planets. So some examples: TOI 1807, that is the youngest ultra-short period planet, only 300 megayears in a co-moving group. The co-moving group has no name, that is the TOI 1807 co-moving group. And here in the left, you can see the activity both in the photometry and the radial velocity. It is a very strong activity for this star, and we were able to model this activity by using a multidimensional Gaussian process framework, implementing the public available code PyOrbit developed by Luca Malavolta, and we were able to constrain with extreme accuracy, with extreme precision, less than 20% the mass of the planet, and to find that it is a Earth density planet. Another example: this is a young planet. This work is ongoing. I don't say the name of the planet, but some of you probably know it. And this is a young exoplanet with an evaporating helium atmosphere. This is a very young star, 700 megayear, and the activity is evident both in the photometry and the spectroscopy. Again, we modeled it with a multidimensional GP framework, and we were able also to detect it in the radial velocity and constrain the mass with a precision less than 20% also in this case. This allows us to constrain the density of the planets, but not only to also to obtain information on the evolutionary history of its atmosphere from 3 megayears to up to 5 gigayears. And we have that this is at the beginning was a Jovian, puffy Jovian that is losing its atmosphere. So an overview of some exoplanets. We analyze it. The topic covered by our project, by the GAPS project, are the planetary mass radius determination, the analysis of orbital obliquity, atmosphere evolution, but also multiplanetary system, also brown dwarf or activity indicators as a function of the planets properties, etc. Again, these plots with different colors, and in the mass radius diagram, we can see that there are some. There is a group of planets, even if they have not constrained masses, but only upper limits. But the youngest planets are in the less density region. Unfortunately, for these planets that have ages less than 50 megayears, we are not a constrained mass. The planets with ages below 100 megayears are in the low density region in the orbital period radius diagram. And if you look to the radius age diagram, it seems that there is a trend from small to larger ages. It seems that for younger star, we have a larger radii, and are they the progenitors of the older planets? Anyway, if we look to this diagram, there is a lack of small young planets, and can be an observational bias. Probably yes. And the future is Plato, and that can solve this problem. This is a simulation of Earth-like planets injected in the light curves of very active stars with activity that is randomly simulated with a different number of star spots or rotation period. And we injected Earth-like planets with 100 day and 300 days orbital periods. And in the Plato-like curves, the 100 days orbital periods planets are always recovered in our simulation, while the 300-day orbital period planets are recovered in 75% of the cases, because some in 700 days of observation of Plato, there are only 2 or 3 transits, and some of them can occur in the minimum of the activity, and can be difficult to detect them because the trending method absorbs the transit. So this is also the importance to use robust detrending methods, and there are working group and working packages that are working on this. So don't miss the talk by Gianpaolo Piotto on Friday on Plato. So that's all. Let me conclude with this romantic view of TESS and Plato that look each other, because the 2 missions are complementary. It's very important. So thank you.
Thank you, Nardiello. Do we have any questions? So I can go first. You mentioned that you have this detrending package, which removes the effects of the light curve a little bit better than something like PDC. But what do you then do to detrend the stellar activity in order to model the transits?
Sorry.
How do you detrend the stellar activity in order to model the transits?
The first detrending, if I have to look for new exoplanet, I use Wotan, the big weight spline, the 30 big weight spline, but only to look for other planets. If I have to, when I have to model the transit, I use the Gaussian process or local spline plus the transit itself. So it depends on what we, but as a first guess, I use the big weighted spline implemented in Wotan.
There's a question here in the center.
How do you estimate the age of the system?
The age?
How do you estimate the age?
Of this system is 700 mega-year.
How do you estimate it?
For this system that is not belonging to moving groups or stellar cluster, we use kinematical information and lithium and lithium and also the spectroscopic indices. So, indeed, the error on the age is a very large. Also, the rotational period of the stars. Indeed, these planets. At the beginning, when in the first study of these planets, the age was 300 mega-year because the light curves was corrected in bad way.
So it's a member of some association, young stellar group?
No, this is a single star. This is a.
If you estimate it from the rotation period, then
yes.
You have to be careful because the field stars are notoriously look younger than they should.
Yeah, but we also compare the lithium with the Pleiades and the Hyades abundances. So
okay.
Yeah, the age is well constrained.
We have time for one more question, if anyone has one. Yeah. This way, somewhere.
It's Huan Yu from Korea Astronomy and Space Science Institute. And I would like to know, did you try any injection and recovery tests for your radial velocity and Gaussian process? Because Gaussian process sometimes or mostly overfit the mass of the planet or something like that. So have you ever tried something like that?
Okay, not me, but some of my collaborators are doing this for young planets. Some collaborators in the GAPS program, Mario Damaso and other students, they are doing this, and it's the answer is not simple in this case because not always you are able to recover the planet even if it is there because of the high activity, especially if the study is very young. Yes. So we are working on this also.
All right, thank you.
Okay, let's thank Domenico once more. Next up, we have Louise Nielsen, who's going to be telling us about tracing planet formation with the youngest transiting exoplanet candidate. So the second time we have the youngest transiting exoplanet candidate.
We're going to have a little planet off or age off afterwards. So hi, my name is Louise Nielsen. It's really great to be back here in this beautiful auditorium. It's kind of nostalgic for me. I gave my very first science talk in this room 5 years ago at the first TESS Science Conference. Since then, I've been jumping around a bit. I've finished my PhD, thank God, and now I've landed as a staff scientist at the university in Munich, where we're trying to build up a little exoplanet team. So if any one of you are interested in, I don't know, like Germany or learning about exoplanet science in Germany, do come talk to me afterwards. So tracing planet evolution with maybe the youngest transiting planet candidate. I don't think that's true anymore after the talk that we had from Madyson two talks ago. So I could also have named this talk Titori host stars are just as annoying as we were expecting them to be. And that's going to be a bit of a theme in this talk. So let's have a look at it. So young planets really act as an empirical anchor of our understanding of planet formation and evolution as well. Looking at this nice, very classic diagram from this 2012 paper, you can see how the radius of a Jupiter-like planet, a Jupiter mass planet, will go down rapidly and quite drastically with age. And my idea here is it's nice to find planets that are very, very young compared to, I'm still sort of like we had in the talk before, I still consider anything younger than a giga-year young. But if we're trying to look for, these really clear signs of planet evolution, for instance, it does look like if you look at something that's very, very young, you will see the biggest changes, right? On top of that, you do have some formation or some processes that are just washed out after a while in your planetary system. So for instance, the primordial misalignment of a planet, which over time will then circularize and do all kinds of things, where you basically lose that information unless you're looking at very young planets that are just a few mega years old. Alrighty, so just to give you an idea of what we're looking at when we're looking at younger planets, so this is a 20 mega year old for V 1298 tau, where we have a lovely mass radius diagram, and then you have these 4 points that are green, where we have the planets in the system, and they're all found to be more massive than we would expect them to be. And actually, if you compare to synthetic planet populations, and this is a little bit hard to read, but basically you have some red points here that are taken from a synthetic planet population model where they're all as young as the planets that we're measuring, and then comparing to the blue points, which are mature population. Actually, the planets around V1298 tau appear to be more similar to our solar system mature planets than we were expecting them to be. I should say that this is under the assumption that we actually measured the radius and the masses of the planets here correct, and I do think that there's it's probably more likely that we have some errors or some complications in measuring the masses over all of planet population synthesis models being wrong, for now at least. All right, so let's look at this very young transiting planet. So sadly, I can't really disclose the tick ID right now because we're still in the process of getting the detection paper out. I was hoping to sort of be able to show everything today, but I promised my co-authors that I won't. I don't know, make them unemployed while we're here. Anyway, so this is a TESS detection from year 1, from sector 11 and 12. And what you see over here in the phase folded plot is where we've taken the red GP model here, and we subtracted that from our TESS data, and then we phase folded onto the detection of the planet. So we have quite a bit more TESS data now, and this is really, I think, part of the power of this mission. You know that the satellite keeps going back to the same stars again and again. And what we can see in the very young systems is that the stellar activity can change a lot or little between visits or sectors or years. And that again helps us to really disentangle what are planet signals and what are stellar signals. So if your star is changing over time, but your planet really shouldn't, that's a nice sign for us to see that. So over here again, I have a nice space folded light curve from TESS, and then we end up with a mass or radius, of 5.3 Earth radii, and the orbital period is 11.7 days. So we're a little bit on the long period side of what we're talking about very often when we look at TESS planets. But that's also making the follow-up a little bit harder. So yeah, I work with radial velocities, and that's really where my forte lies, is to look at the density of planets over time, not just radius. So, let me see, I hope we are going somewhere. Very good. So assessing the age of this planet, so I have a color magnitude diagram, color magnitude, rotation period distribution in the middle, and then we have lithium equivalent width on the side. And then if I just plot in some different comparison regions, we will first have the AB Dorado moving group, which is around 100 to 150 mega years old. And then on top of that, I put this epsilon Cameloonitis association that our star is part of. And we can see that our star appears to be a fairly good member of this group. So I should say that I'm showing it in a tiny little star here. That's a little bit hard to see, but especially the lithium emission, I think, is quite convincing. Let's say like that. How much time do I have left you? All right, that's for the talk, not for questions as well. Good. All right, so in the end, we find an age of 3.7 mega years. So maybe not the youngest transiting planet after all, but I would say it's young enough that we can really do something interesting. We should talk later for everyone else who are interested in planets around T-Tauri stars. Okay, come on. Yeah, all right. So going a step back and talking about stellar activity and so on. So I work under the assumption that most of the activity we see around young stars or on young stars is spot dominated. So in photometry, it looks quite simple like this, that your spot will be rotating in and out of view. And this is real data from DS2A that we also just saw in the previous talk. And I'll highlight one transit there in a little arrow and then one transit right there. So by eye, of course, these transits are very difficult to weed out, but I do think we're at a point where in our field where we have quite good algorithms for weeding out the data, of weeding out the planet. So why I see the big, let's say, buildup or the difficulty is radial velocity. So sorry, this is just showing what we can do in radial velocity. So in radial velocities, we have the same problem as the spots rotating in and out of view. It's distorting the absorption lines in our spectrum and then looks like a radial velocity movement of radial velocity variation. But of course, this is not the star, moving back and forwards. It's really just, it looks like that we have a radial velocity variation. So this is a nice example from K233. There's a more recent paper out, but I just took the old nice RV timeline here. Oh, sorry, go back. Oh no, this is gonna take a while. All right, there we go. It's always dangerous having too many overlays. But what you see here is that we have a quite complex radial velocity time series where the biggest contributor to the radial velocity signal you see here is the star, not the planets. But if we then model our activity with a nice GP in this context, we can subtract that, and then that's what you see on the bottom here. This is what is left when we only believe we're looking at the planetary signals. And this planet in particular has 3 transiting planets around it. So I should say all of this work is done on transiting planets, and I think it's quite powerful to use radial velocity as a follow-up for transiting planets and when your star is young and active, because it helps us immensely to know what the periods of the planets actually are. All right, so our solution to doing radial velocities and measuring masses of young planets is to look at stars in the near infrared. So again, I'm assuming my activity comes from spots and not everything, and not other things. And I think that's that's an assumption that I'm doing right now. But if we go observe in the near infrared instead of visible, the contrast between the spot and the continuum of our star goes down, because we're observing closer to a temperature that's closer to the temperature of the actual star. Basically, the contrast between the spot and the surface goes down. And then we can use the information that's given in that is that the stellar activity signal is probably wavelength dependent, or should be wavelength dependent if it comes from a spot at least. And our Keplerian signal from a planet should not be. So at the moment we have what I believe is the best engine to do this. And that will be HARPS plus NIRPS, which are both installed on the same telescope. It's a 3-meter telescope in Garcia in Chile. And HARPS is, let's say, a grand old man in the field. It's been operating for decades and routinely gives very, very good radial velocities. NIRPS has been in operation since 2021, and it's been out as open time since 2023. So I should say anyone in this room can apply for NIRPS time as well. And if any of you are interested in that, do come talk to me. I used to be on the science team, but now I'm getting my time in my own open time as well. But NIRPS is also a high resolution spectrograph that operates in the near infrared. And the nice thing is that you get these 2 spectra simultaneously, more or less for free. So I think it's a perfect workhorse for doing this work in the future. And I believe you'll be seeing a lot of HARPS plus NIRPS mass measurements of young planets in the future. So we tried to apply this to our planet around a T-Tauri star. And this is where my title should have been T-Tauri stars are difficult. So first of all, we did have a problem getting the sampling that we were hoping for. And I just got the last RV data point a few weeks ago. So that's why this work I'm showing right now, sadly, is a little bit more mature, but that would have been great. But what you see here is in the closed circles, we have the NIRPS data, and then we have our simultaneous HARPS data on top of that. Sadly, we had some problems with one of the spectrographs at some point, so not every night has both HARPS and NIRPS, but most of the time we do. And it was quite interesting in the beginning that we really saw a large scatter in the HARPS RVs and a much smaller scatter in the NIRPS RVs, at least when you take into account that the NIRPS RVs here have a larger error bar, or larger uncertainty. But then the final observations we got, the 2 spectrographs are actually very much in alignment with each other. So I do think we're seeing a change in the activity output of the star in this specific case. But sadly, this is as much as I'm gonna talk about this data right now. So I wanna say we do have this really interesting data set, and we are really looking forward to doing something with it. I think a lot of the work to be done on this will be investigating veiling. So this is a very young star. T-Tauri star, it has emission lines as well, and has active accretion of material around it. So veiling is going to be a problem. And then we're going to develop our multi-dimensional Gaussian process treatment of this, so we can really look at these 2 time series as having the same Keplerian signal, but you should have a different stellar activity GP on top of that. So with that, I'll go to my conclusions slide and at least say that TESS is finding some of the youngest planets, not just transiting planets, but youngest planets that we know to date. And I think it's a really interesting time now where we can start comparing transiting planets to directly image planets and get this nice unified theory of planet formation. So thank you very much.
Okay, let's have some questions for Louise. Don't be shy.
I do bite.
In the middle here.
Hi, Sharon Wang from Tsinghua University. Nice talk, Louise.
Thank you.
I have a question about the stellar type. If I missed the stellar type for the whole star,
Yeah, it's a K-star.
K-star.
Yeah.
So do you have plan to do raster McLaughlin or Doppler tomography?
Yeah, we actually already have an RM observation with espresso. We actually got that before we got the HAPS and YEPS observations, and they're looking as difficult as the others are. So we're in the middle of looking into all of this at the moment. And actually, I think what will be quite nice is that I hope we can use some of the GP modeling of the radial velocity time series to actually understand the RM observation as well, because we have like a really weird like a discontinuity basically. So far it looks like it's probably in a misaligned orbit, but since this is being recorded, I won't say any more than that because that might change. Yeah,
that's awesome. Thank you.
Do we have any more questions for Louise?
We're so close to the break.
I guess I can.
There's actually one there, sorry.
One from Ward here.
Hi, great talk, Ward Howard Seabolder. Same question I had for Madyson. I noticed a bump in your transit too. Did you look for flares?
Yeah, so this star does flare. I think in the transit, I think what we have there is probably just noise. We could have a spot crossing maybe. That's something we're gonna look at for sure. And especially in the RM observations as well.
One more question from Luke.
This is Luke Baumer from Caltech. What kind of RV sampling would you like to have?
So we were going for once a night, which I think would have been all right, because the rotation period of the star is 8 days and the planet is at 19 days. So some nights we did go for two data points in a night, but because of visibility of the star, once per night was really the best we could ask for. Yeah, and I do think we are in this situation where it doesn't matter how good your data is. If your sampling or your cadence is off for these very active stars, you're not gonna get it.
Okay, so let's thank Louise.
All right, thank you.
And let's move on to the final talk in this young planet session from John Livingston, who will be telling us about low densities, eccentricities, and entropies in a young compact multi-planet system.
All right. Hello, everyone. John Livingston here, based in Tokyo. Happy to be back here after, I think, 5 years since the first conference. Thanks to the organizers for having me. And I just realized that the bad thing about being last in the session is, of course, keeping people from coffee. But in this case, I don't think it could have gone any better given the material that was just presented. So thank you all to the kind introduction. So I'll be talking to you about just one system today, but it's kind of an old favorite, V1298 tau. And as you can see here, this is the family portrait. At the top, the gorgeous K2 photometry showing a 2.8 day rotation period. The 4 transiting planets shown at the bottom there, very easy to see in the bottom row, but very difficult to see at the top with all that stellar variability going on. So there was initially the discovery of the 3rd planet out, followed by the others, which is why the ordering of the planets is C, D, B, E in order of increasing period. So just a little more background on this. It's a 20 to 30 mega-year-old system. It's part of an association called Group 29 in the foreground of Taurus Auriga. And our old favorite plot here, just have to come back to it again, because at the time we saw this system of fairly compact configuration, very similar to the orbital separations you see in the Kepler multi-systems. But of course, the radii were much larger. And this was sort of in keeping with the trend that had already been starting to appear as the numbers of young transiting systems had slowly been increasing. So this immediately made us very intrigued. And of course, the fact that we had multiple transiting planets in the same system made this a rather unique laboratory to be able to compare how planets form and evolve without having to worry about differences in stellar activity between systems. And just another point to keep in mind in context. So this, of course, you all are familiar with the radius valley, but not only was its origin first detected in population, looking at the distribution of radius, but there's been a little bit of hints at the time evolution of the radius valley. So here you can see a little bit of that at older ages. But one of the reasons we were so excited about this system was that for once we could really look a little more carefully and in more detail at a single system instead of population level. So one of the things we did was immediately try to do follow-up observations. We got some Spitzer data, and we were lucky to get that fairly quickly after the Discovery paper came out. And so that was all looking good, and this project was really small back then because we just wanted to catch the transits, update the ephemeris, ensure that we could continue studying the system. But soon after that, a very interesting and surprising result came out, which was mentioned in the previous talk, actually. The RV measurements of the masses of the outer two planets came out to be surprisingly large. And so this immediately sort of prompted us to think more carefully about what we might be able to do to study this system in more detail. And right around the same time, we were also very fortunate that TESS had been observing the star. And so soon after the RV result came out, it was rather interesting to find another transit of planet E. So in the original K2 photometry, there was only a single transit of this planet. So it had a completely unconstrained period. But now with two transits, thanks to this additional detection by TESS, the period could be constrained to sort of a comb of periods, which you can see on the right, period aliases. And another thing that came out of this was that the period that had been found in the radial velocity measurements was ruled out. And so it was a little unfortunate that this came out, I think, the same week as the RV result, because they did a lot of hard work to try to ensure that they got that right. But as alluded to in one of the questions earlier, they actually did injection and recovery as a way of checking for GP overfitting. And it was actually the case that soon after that, it was found to be the case that injection and recovery didn't actually work as a method of checking for that. And this paper by Blunt et al. Came out and showed very nicely that cross-validation or possibly other methods are needed to check for this. And so we immediately began thinking, okay, more transit follow-up. That's got to be the solution here, because RVs are just too difficult. And so we scrambled to get working with a bunch of collaborators and amass more telescope resources and just observe as many transits as we can. And of course, the thought at the time was, given the orbital architecture, we might hope to see transit timing variations. But in the K2 data alone, you don't really see anything. However, as we started to collect more data, some possible signals started to emerge. So this is showing the Spitzer transits and just the beginning of the ground-based transits that we were starting to get. So we got excited and we continued observing. And here you can see all the way up until the TESS epoch. And what happened with the TESS data was that we got another transit of E. And so now you can see E is showing up on this plot. But we were still stuck not knowing the period of that planet. So it was not without further challenges. But the only thing to do was really just hit it as hard as we possibly could. So I did some sort of brute force calculations to try to narrow down the possibilities of the period of planet E. And fortunately, we got it. We were able to recover this outer planet, and we hit it as many times as we could just to be extra confident. And here it is all the way up to the present. You'll notice that the cadence of observations increases with time, which is probably a complex function of additional telescope resources and increasing levels of obsession. And then finally, with that giant timing data set assembled, we were able to do what we had long been dreaming of doing, which was to measure the masses and eccentricities of these planets with dynamical models. So this only recently got wrapped up. I'd be happy to chat offline with you about some of the challenges involved, but it was really a long process. We had to be very patient and collect all of this data just to barely be able to get to a unique solution. But I'm happy to say we've got it now. And so we can now look at these familiar parameter spaces and see where these planets lie and where the planets will evolve. And so you can see, similar to the plot I showed earlier, they will end up as sub-Neptunes or even super-Earths, depending on the activity tracks of the star. And then, of course, the mass radius plane, you can see the same general idea here. So these are truly anomalously large, low mass, puffy young planets. And that means that the original idea is now confirmed that this is a true progenitor of a Kepler multisystem. And so one of the other things you can do with this that's quite interesting is that because of a degeneracy between thermal state and the envelope mass fraction, you can, given the age, you can wind back the clock and figure out what's the minimum possible initial envelope mass. And then that sets a limit on the entropy. And so another way to think about this is that you can compute the cooling timescale and then just compare it to the age. And if the cooling timescale is much longer than the age, well, you know that something else must have happened to cool rapidly these planets. And so for the inner two planets in the system, because they're so close to the star, we have good constraints on this, and we can actually measure these low entropies, which are, I think, the first empirical evidence of boil-off actually having taken place at the disk dispersal. And then one other thing that I thought was really interesting was looking at resonance. And so these planets are actually quite close, but not in resonance. And this is in keeping with the trend that is emerging with similarly young and older young stars, which you can see on the right here, this recent work by Dye et al. And so it's possible that mass loss due to photoevaporation is actually the mechanism, or one of them at least, to help to push these planet pairs further from resonance as they age. And so with that, I'll just leave my takeaways up here and take any questions. Thank you.
Well, I'm sure we have questions after that. Who's going to go first? We have just one here.
Gijs Mulders, Universiteit Adolfo Ibáñez, Chile. So previous mass measurements shows that these planets were more dense, and now you have a measurement showing these planets are less dense. Do you have an idea of where this discrepancy could come from?
Yeah, so the previous work was to measure the masses from RVs. And you can see here, if you just look at the top plot here, that's a subset of the RV data. The peak-to-peak scatter is, like a half a kilometer per second. And if you were just to consider the mutual Hill radii of these planets and look at the system as a typical Kepler system, given the typical spacing in mutual Hill radii, the mass constraints are very low, certainly lower than they measured. But you can, even before having done this, you could imagine that measuring such low masses would be exceedingly difficult because the semi-amplitude is smaller than the stellar activity signal by about 2 orders of magnitude. And so the paper I'm referring to here, this plot comes from Sarah Blunt's paper, which showed that the GP method itself had been overfitting and resulting in the overestimates of the masses.
There's another question from Elizabeth.
Hi, Elizabeth Newton, Dartmouth College. This is really cool to see all that coming together. I was curious about the boil-off. Is it weird that you only need it for 2 of the planets, or, I'd just love to hear more.
That's a great question. I'm not an expert on this, but as far as I know, it's not weird that we wouldn't see it for the outer 2. So I have those plots, I just didn't show them because they're not as interesting. But basically, those planets are so far from the star that at this age, there just hasn't been enough time for much photoevaporation to have taken place. And so this constraint only works for the closer in planets.
Sorry, can you remind me the order of the planets again?
C, D, B, E.
And maybe one quick question if anyone has one. See from Sarah.
Hi, Sarah Milhon from MIT. Really, really nice work. I was wondering if you could talk more about the eccentricity constraint and also any extent that the fit was impacted by mass eccentricity degeneracy.
That's an excellent question. So first of all, we're getting very good eccentricity constraints. They're all less than 1%. And so this is, pretty much inconsistent with any kind of past violence in the system, presumably convergent migration and some mild instability, possibly during boil-off or even before it. The low densities, I think, are inconsistent with anything like giant impacts. The second part of your question, the mass eccentricity degeneracy, that's an interesting one. The outer pair, the BE pair, are far enough away from resonance that is more of an effect. But we were actually quite lucky that the inner pair is so close to resonance that we don't suffer from that. And then even though the interactions between D and B are quite weak, we think that there was some assistance from those interactions in helping to break the degeneracies for B and E.
Okay, make it quick. We can.
I was just curious if you'd taken these masses and worked backwards and done the prediction of what the RVs should have been, and then get out what the RV model of the star is.
That's a great question. I've actually been thinking a lot about how much value there is in the RV data set, not for the planets, but for the star. And now that we know the masses from TTVs, I think there's a lot of work that could be done using the RV or even the full spectroscopic data set. There's a huge amount of value to be mined from that. And I think since this work, many groups have continued observing it. So the size of the data set has at least doubled since then. So just putting those mass constraints from TTVs should enable tremendous improvements in understanding of the star itself. Thanks.
So if anyone has any additional questions for John or for any of the other speakers in this session, please ask them on the Slack. Hopefully they can be answered there. And so let's thank John and all of the other speakers.
Welcome to the Data Analysis 1 session. We'll get started in just a moment. Our first speaker is Doug Caldwell, who's going to speak to us about Spock data products.
Okay. Hi, I'm Doug Caldwell. I work at the SETI Institute and at the SPOC at NASA Ames. The SPOC is the Science Processing Operations Center. And I don't have any period radius diagrams, I'm sorry. And I don't even actually have all that much science, but hopefully I can tell you about some things that I think we can hopefully enable more and better science. So the SPOC is responsible for producing the primary mission data products that are in the archive. And there's a poster in the poster session by Stephanie Striegel, who's our operator, who that explains in more detail what these are. But as you probably all know, we have the 20-second data, which average about 2,000 targets per sector. And we've got about 81,000 targets to date in the archive. The primary data we've been producing for the whole mission is the 2-minute data. And for these, we produce light curves, target pixel files, co-trending basis vectors to allow you to detrend the data as you want. And we also perform a transit search result on these 2-minute data and produce a list of threshold crossing events, or TCEs, or detections from the pipeline, and supporting material from data validation, which I'll call DV here, that gives you information about the validity of these TCEs. And all the detections go into the archive and are available for you to review or look at it any way you want. We started at about 20,000 targets per sector in EM1 and 2, or I'm sorry, in the primary mission in EM1. In EM2, we went down to about 10,000 or so targets, and we have about a total of about 1.4 million light curves target pixel files in the archive now. We also calibrate and archive the full frame images, FITS files, and uncertainties at all the cadences we've been using throughout the mission. The SPOC has been continuously evolving the pipeline and fixing things that we find out are causing issues. And two fairly significant efforts we undertook were, one, as to reprocess all the year 2 data. This is looking way back in your Wayback Machine, but we're reprocessing the data to get it to the current processing standards. And the big fixes in that are, we fixed a background aperture overfit that was present in the earlier data. And this results in significantly improved photometric precision, CDPP, for especially faint targets, starting around 11th and increasing up to about 20% improvement for the faintest targets. We also improved the way we select the ensemble targets that go into the systematic error correction in pre-search data conditioning and generate the co-trending basis vectors. Sorry for all the acronyms. We had originally put in a change to try and better remove variable stars that were introducing signals into the ensemble. And the first attempt at that was a little over aggressive, and we ended up generating ensembles with too few stars and that ended up increasing the noise on our corrected stars. So we backed that out and done a better job at iteratively removing variable stars, and that fix is now in for year 2, and all the data will be caught up when I talk about year 4. We also we went back and implemented the updated TESS input catalog, TIC 8.2, and that affects one-off stars where we had artifacts or duplicates in the original catalog. We've now removed, those have been removed in 8.2 to the best we can, and that'll improve the target aperture definitions and optimal aperture photometric aperture definitions for a number of targets. All these data have been delivered to MAST and are waiting to go live. So year 2 data should soon be up to the same processing level as all the rest of the more recent data. We reprocessed year 4, and the primary fix there was again this improvement in the PDC, the pre-search data conditioning, systematic error correction ensemble creation. And that primarily affects bright stars and results in a modest improvement in CDPP of a couple % on bright stars. Probably more importantly, does a good job of removing variable stars from the ensemble, which will then introduce their variability into other stars that are corrected. So we hope we're doing a better job at that. Those data are under review, and will be delivered as soon as we get ready. I'm suspecting probably in the order of a month or so. We have one upcoming fix that's being tested now, and that's a change to the data validation multi-sector centroid fitting for potential planet candidates or threshold crossing events. And there's a poster by Joe Twicken in the poster session describing that in a lot more detail. But essentially that takes advantage of the fact that we have multiple sectors to improve the centroid, to improve our ability to centroid the targets, the difference image signal coming from transiting candidates, and especially is beneficial for low signal noise or small planet targets. In addition to the SPOC primary mission products, we've been processing the targets selected from the FFI data, and this is currently named TESS SPOC high-level science product data at the MAST. We've been processing up to 160,000 targets per sector. We're using the same code as the 2-minute pipeline, and so therefore we have the same data products and archive formats as the 2-minute data. So it's hopefully easy for everyone that's familiar with those pipeline products to use these results. So that's target pixel files, light curves, including all the simple aperture photometry, the PDC corrected photometry, and co-trending basis vectors to allow you to detrend any other FFI targets that we didn't pick. And since sector 36, we've been running those light curves through the same transit search as the 2-minute pipeline. And so for those, we have threshold crossing events, data validation products also at the archive for all these targets since sector 36. So what data are there from this TESS SPOC data? We have sectors 1 through 69 are live at the MAST. It's about almost 11 million light curves for 3.7 million unique targets. And you can see the sort of distribution on the sky there. We've got the little cowboy hat of empty space, which we're hopefully filling in. Sectors 70 through 73 have been processed and reviewed and are, I think, in the process of being delivered or will be delivered soon to the MAST. I know the MAST has a backlog of putting things up, understandably. So these are all high-level science products that are available now. And again, it's the light curves, target pixel files, plus co-trending basis vectors for all these targets. In addition to that, as I mentioned, we've been taking these TESS SPOC light curves and running transit search. And we've been doing a single sector transit search starting with sector 36. And based on our searches, we've had a total of about 180,000 threshold crossing events on 116,000 unique target planet number potential detections. These are all, again, archived at the MAST, the TCE list, the data validation reports, and machine readable versions of the data validation data. We're in the process of going through a multi-sector search, which we've been hoping to do for a while, on sectors 56 through 69, and it's still in process in the pipeline. We did finish the transiting planet search part of the pipeline, and from that we've got something like 17,000 TCEs I'm sorry, we searched 370,000 targets. We've got 17,000 TCEs out of those. And those will go through data validation, which will do a multi-transit search, so that number will bump up. And again, all those data will be delivered to the MAST. To date, the effort to look at all these threshold crossing events and results has really been a small effort by me some, and Emily Simpson, a researcher who works with me, and a series of interns that I've had over the spring and summer, Mayola Valencia, Jasmine Freeman, Theo Chawla, and Kendra Nguyen, some of whose names you might recognize. And we've been using the transiting exoclass or tech code that Chris Burke developed, and we modified slightly to work on the full frame image data. That works to the extent that it works, but it's very labor intensive. And so we've been working with a group at Ames who's been developing this ExoMiner product that you may have seen that's been used on Kepler data and to some extent on TESS, trying to implement a machine learning AI approach to vetting all these TCEs, of which we have many, most of which are no good. And so there's a couple graphs of very preliminary results from ExoMiner. The first runs through have have good recall in the sense that they recover most of the positive signals, but not such good precision. And you can see that by they don't clearly separate. There's a big band of targets that fall in between scores of 0 and 1. Ideally, we'd like to separate things better. So that's work in progress, and hopefully that will improve things and enable us to much more quickly come up with exciting lists of TCEs. We also just started working with a citizen science network with Lauren Scrow and Dan Peluso, have some papers out on different objects they've looked at, but they started observing some of our interesting finds coming out of this pipeline. So we hope to be able to come up with some more good signals that we can go further into to confirm if they're planets or not. So our TCE distribution on the sky looks like this. In green, there's the 116,000 unique threshold crossing events from this FFI target search. The yellow ones are ones that pass the tech vetting, which is based on Kepler's RoboVetter originally. And so those are the tier 1 TCEs, they're called. There's about 1,000 of them. And the magenta or pink, whatever color that is, ones are the tier 1 TCEs that are new, not in the TOI catalog or known planets. So we're finding new transiting objects that look good, look likely to be happening on the sky, on the target, and probably not, as far as we can tell from test data, eclipsing binaries. So we've got a number of them. And they're, as you can see, they're scattered over the sky. And since we started our search only in sector 36, there's some bigger gaps that we haven't filled in yet, but as we go on, those should fill in. So I think that's it. My summary, I think the SPOC has been producing consistent data for a long time. The numbers are there for you to look at. I think we've got a number of processing updates that are in place, and data has been delivered for some and will be delivered soon for others. And I think we're ready for EM3, maybe whatever you bring at us. We'll see. And the TESS SPOC data are hopefully a good resource for people to look at for light curves. If you want to look at a whole bunch of transit detection results to run machine learning approaches on, they're there. They're in the archive for both SPOC 2-minute data and TESS SPOC FFI data. And we're investigating increasing the number of TESS SPOC targets from this 160,000, which was a processing imposed limit to not overtax the resources of the SPOC pipeline, increasing the number and also folding it more in with the SPOC pipeline processing so the deliveries happen on a more timely basis. And I think that's it.
Nicely done, Doug. You almost nailed it.
I just watched.
Do we have any questions for Doug? We have runners. We have one here. Hugh? No, you can't have my mic.
I got you. Don't worry. Don't worry.
Thanks, Doug. Hugh Osborne at Bern. What is the procedure by which the detections from TESS SPOC end up as TOIs, or do they not?
Currently, they do not. We have a small subset that have ended up as CTOIs through the vetting of the interns. We're actually working at our last meeting, our mission meeting with MIT. We were talking about how we're going to try and fold that in. I think the agreement was that we would start with the multi-processing results to feed them into the regular TOI pipeline. So hopefully soon.
We have a question, 2 questions over here.
Hi there, Sam Gill, University of Warwick. A lot of us who look at the long period planets are quite excited to look at the data as it comes out. What's your plans and timescales for post Sector 69 data for the TESS SPOC light curves on MAST?
We are still, so we have 70 through 73 processed, and the other ones are in the queue, basically. 74 will be next. So we are delivering them. We had gotten behind, we caught up, and then with the multi-sector search has been some delays to get that working, and so we fell behind a little bit again, but we do plan to continue doing this. And again, hopefully, if we're able to fold this in with the mission processing, there'll be more timely deliveries.
Appreciate that. Thank you.
Yeah, thanks.
Was there a question to your left?
There was. Hello, Toby Rodell, Queen's University, Belfast. I was wondering, you said you were thinking of increasing the number of TESS Spock targets. Can you give us a rough indicator of what kind of number that might be?
The real question is how much essentially cost and effort does it take to get what increase? We think we can do a factor of 2 without much effort, maybe up to a factor of 4. We've been talking about this and trying to figure out how we'll make the changes. Another limiting factor is where right now we have a 13.5 mag cutoff, which we don't reach completely. But once we get much above that, simple aperture photometry probably is not necessarily the way to go. So I think it doesn't make sense to do 10 times as many targets.
Okay, thank you.
All right, let's thank Doug again. Sorry, out of time for questions. You know where the Slack channel is.
Thanks, Roland.
Our next speaker is Glenn Piripa, who's going to tell us about QLP and TEV at the TESS Science Office.
Play? Green. Okay. Hi, I'm Glenn. I'm here to tell you about the Quick Look pipeline. Hopefully most of you have heard of it or know what it is. We've been making some changes lately, improving things, making them faster, making everything better. And I'll summarize all the things we do here. Quickly, I'm from the TESS Science Office across the street in Kavli. The members are me as the manager, Jack Haviland is our software lead, Willie. They're both actually here, which is great if you have questions. Is our database engineer expert and software engineer. Catherine is also here. Actually, everyone's here. Catherine is our TOI manager. She manages the TOI catalog and organizes the vetting process and things like that. And I'll work my way through all of that later. Avi, you all know, is our grizzled scientist. And we have 3 postdocs, Jeroen, Mark, and Daniel currently, and they're either going to be trained or will be trained or have been trained on running the Quick Look pipeline. And they're also pretty heavily involved in the development of the AstroNet machine learning classifier I'll talk about also. So the Quick Look pipeline itself is the MIT-based full frame image light curve generation machine. We take the 200-second FFIs and we do aperture photometry on every star down to a Tmag of 13. We then send those light curves to MAST for general usage. And then we also take them and keep them in-house, and we do BLS search, planet search, triage, et cetera, and generate TOIs through this pipeline, which I'll summarize briefly. I want to point out that every planet search we do with the QLP is full multi-sector. We use all the data all the time, all the way down to K2 data if it exists. We'll throw that into and do our planet searches using all of it. And then the ultimate goal, of course, is new targets of interest, test objects of interest. So, quick overview. Quickly, we have full frame images. You see them. We do 5 apertures, actually. We have 5 predefined apertures. We do aperture photometry on all the stars down to Tmag 13 for 5 different apertures. And then when we're done that, we do a systematics removal, and we do a detrending. And to MAST, we deliver 3 light curves, the raw for 3 of the apertures, the systematics removed light curves for 3 apertures, and the systematics corrected and detrended light curves with the stellar variability removed also for 3 light curves. We have the best, for 3 apertures, sorry, we use the best +1, best -1. So we're technically sending 9 light curves for every star to MAST. I got an email this morning. Oh, this isn't updated. Sector 75 is now available on MAST, with sector 76 being ingested sort of as we hopefully speak. Planet search. So we don't have the, we're getting close to having the resources to go all the way down, but currently we only search down to Tmag of 10.5. A couple of years ago, we switched from CPU BLS searches to GPU-based searches. Let's see, pointer, yes. So for like the period power diagrams, we were able to increase our search grid by a factor of 1,000, which increases the signal to noise quite a bit. The black one is GPU-based. The blue one, you can't see it because it's only up to that dotted line right there, was the old CPU-based signal to noise for these frequency searches. So in addition to searching a grid 1,000 times finer, we also are still running 40 times faster than we used to. The whole planet search on the entire sector takes on the order of a day. But now, this is the new stuff. Coming soon, currently what we do for the BLS search is we look for signals around every star down to 10.5. And the strongest signal gets passed on into the triage process. The problem with that is if you have a bright, and then those all get triaged, and then the signals that pass triage become our planet candidates, and then we feed those back into the multi-planet search and look for multiple planet systems around the strongest signals. Now this has a problem in that if you have your strongest signal isn't a planet, it doesn't get fed back into the multi-planet. So Jack has been working on a new routine now where we look for basically every signal around every star, and they all get triaged, and there is no risk of losing that whole category of planets around things where the strongest signal was false. We have code running and testable. We're just doing diagnostics sort of now. That should hopefully give you some new batch of TOIs, Dave. But currently, as I said, the brightest signals get sent to our AstroNet triage machine learning classifier, and they get sorted into junk contact binaries or passed on for human triage. The BLS search generally finds tens of thousands of signals every sector, and then the AstroNet triage classifier will filter out generally all but 1,000-ish, a few hundred signals. And then those few hundred signals get passed on to the QLP operator, who will then manually inspect them and then pass them on for group vetting at the end of the process. Now, another new development that's being developed is the AstroNet vetting, which is the second stage machine learning classifier, which has finer categories. I'm generally sort of new to this, but Daniel can, if you have questions about it, you can talk to Daniel. But basically what it is intended to do is sort of remove the human part, the human triage, where the QLP operator will manually inspect all these signals. Your brain goes kind of mushy when you're looking at like a few thousand light curves. So it'll be better for everyone if humans aren't doing that. And this is one step in that path. The ultimate goal, of course, is to do full planet search all the way down to a TMAG of 13.5, which if Michelle is here, her faint star search is doing something similar, but with Leo Vetter, which we'll talk about, I think, tomorrow. After we do all of our triaging, we generate reports, and the best candidates get reports, which you've probably seen. They're delivered over to the TEV website for the vetting. You've probably seen TEV. That is a terribly small font. I'll go to the next one where you can log on to the TEV, put in your favorite tick ID, and see if we have any vetting reports for them. We do this for Spock signals and QLP signals. It's the general all-purpose vetting website. Willie has been working on something new and exciting, which it's a TCE catalog, which will have it'll have entries for all signals, not just the ones that pass triage. So if you have a favorite tick that you think should be a TOI and you want to know why, you will be able to go here, enter the tick ID, and then see where in the process of either Spock vetting, Spock tech processing, or QLP triaging, it fell out of the process. And you're free to hopefully try and do a beta. Jack confirms it works, yeah, if you all don't crash the site, you can go on now and take a look. If you see anything you don't like, you can let us know. Willie's still sort of working on the interface. I have a oh man, those are tiny. I just got these earlier, but basically this is a timeline. So see, this is one that failed. You can see the different steps where it dropped out, and this is one that passed. You can see all the steps that it passed through to get to the TOI catalog successful entry. I apologize, that is not readable. The last thing that we do at the TESS Science office is we sort of do the vetting. Well, Catherine is in charge of the vetting process. This is the pathway for all of the signals. So SPOC signals, QLP signals, and CTOIs all get their reports sent to the TEV, which is the website I just showed you. The vetters look at those reports and they get together, and if it gets more than one planet candidate or uncertain vote, it goes to group vetting. If the vetters all agree that it's not likely a planet candidate, it gets dropped. And then the group vetting process flows like this. Till eventually it makes it into the TOI catalog or it doesn't get alerted. In the olden days, you wouldn't be able to know what happened to these ones. But now with the TCE catalog, you'll be able to go in and see where along this, well, sorry, I guess more along where this way it didn't make it. The TOI catalog is a living document maintained by Catherine. We get new data, update the parameters. TFOP gets supplemental observations. We update the parameters. It's always being updated. And say Catherine's got that well under control. We have some updates coming along those lines. Catherine is working on a parameter code checker that will keep her from having to put two planet parameter sets side by side and find the most recent one and update it. We recently, what do you call it? Requested and received a change to the ExoFOP CTOI category where you need more parameters. I'm right there. And that allows it makes it easier for us to make the reports, which get sent to the TEV for the CTOI category of the vetting. And it also allows better history tracking. And that is my last slide. So thank you. Is there any questions?
You said you wanted more time. Do we have any questions for Glenn? Oh, good, thank you.
Hi, Glenn. John Jenkins, Ames Research Center. Just to clarify, I think I heard this, but I didn't quite catch it. So the new TC catalog, will that also contain all the SPOC TCs that didn't make it through vetting?
The example I had was a SPOC.
Oh, it was, okay.
But
So that,
sorry, you couldn't.
oh, that's fantastic. Okay, thank you so much.
Yeah,
I thought that was the case. I just didn't quite hear.
Oh, it gets the tech, the tech stages and tracks where it dropped out of that process.
Okay, fantastic. All right.
Willie just said it will have everything for those who didn't hear him.
Thank you.
Any other questions for Glenn? Hearing none, let's thank Glenn again for his talk. Our next speaker is Daniel Muthukrishna, who will tell us about AI-generated scattered light background models.
All right. Hey, everybody. So my name is Daniel Muthukrishna. I'm a postdoc at MIT. And I'll talk today about what I think is a pretty interesting and novel solution to trying to model and remove the scattered light issue we have in TESS FFIs. Before I go on, I really want to shout out and thank my great undergraduate students. Whoop, let me go back. All right, great. Wait, I can do this. All right, Joey is a undergraduate who's just about to finish, and he's about to start his PhD in UT Austin, and Jenny is a junior who's going to take over the reins from Joey. And they've done some really fantastic work, and they've got a poster in the poster hall. So please go and talk to them about the kind of work they've been doing. It's really quite fantastic to see what undergraduates can do these days. All right, so the issue we have is that scattered light. Anyone who's dealt with TESS data knows that scattered light can significantly impact the data, and is probably the biggest source of systematics we have. Right, and the issue is that whenever the Earth or the Moon come above the sunshade, you have a lot of light reflected off the Earth and the Moon coming into the sunshade and into the lens hood and bouncing into the camera's CCDs, right? And this nice little animation by Roland really depicts this. And you can see that as the Earth and the Moon come above the sunshade and they turn dark and they go overhead, you see that massive scattered light bubbles appear into the 4 cameras. All right, so how do we deal with this? And so you've probably all got your own methods of approaching this, but typically it's on the light curve level, right? You can see that on the light curve level, these scattered light can significantly dominate your signal, yeah? So either we throw away an FFI, and that's typically what we do in transient science, supernova science, which I'm interested in, particularly if you have a saturated signal, or you do some sort of median filter of the light curve, or you can do something smarter like take a PSF and subtract the background around that star, okay? And this is all fine, but it doesn't really approach and really attack the key problem that we have. And there is some sort of physical model that is happening, right? And in principle, if we perfectly understood the system, and if we perfectly understood the positions of the Earth and the Moon, and we understood the properties of the lens hood and the response function of the CCDs and the pixels, then we could do ray tracing, and we could write an analytical model down that would depict exactly what these bubbles should look like, these scatter light bubbles. But we don't, right? We don't fully understand the properties of the lens hood. We don't fully understand the CCDs, but we do know the positions of the Earth and the Moon. So the question is, can we build a model? Can we learn a model that goes from the angles of the Earth and the Moon to these images, right? And can that forward model exist? And so that's what we've tried to do. And so to do this, we've taken advantage of some of the advancements in AI, in particular, one called diffusion models. And so if you've never heard of diffusion models before, you probably have seen them in practice. Anytime you've typed into ChatGPT and asked it to generate an image, that's used a diffusion model, and here's a typical example. If you've seen deep fakes or videos or images, those are all using diffusion models, right? And so we can leverage the kind of technology that's being used there. This paper came out in 2020, and we can apply it to try and model scattered light bubbles. So at the risk of scaring anyone not interested in machine learning, slide will be the only one that really gets into the maths, but feel free to ignore it. But the idea is that you start off with some image and you just add noise continuously to it, right? You add noise at several iterations, what I call diffusion time steps, and you can have several of these. Say we've got 600 in our model, okay? And then once you've done this, and this is a fixed process, you want to learn the reverse process, right? You want to learn the distribution that goes from a noisy image to a slightly less noisy image. And you do this iteratively over and over again, and each of these models you're learning have some complexity to them within your network, right? So that's kind of the process. You have you're just undoing this noise process, and you get back to your original image. And so in our case, we start off with our data, we continuously add noise, our data being the scattered light bubble, and then we learn the reverse process. We learn to undo that noise. All right, so that's the goal we're trying to set ourselves. And so how do we do this? All right, so to actually achieve this, what we want to do is we want to first isolate the scattered light. Okay, so to do this, we have to do some pre-processing. And so we start off with our image that includes both the stars and the scattered light, and we end up with just the scattered light. And we have this pre-processing stage like follows. We start off with your image. You then do a median filter downsample. So you take the median of this image, and you can see that we start off with these 4096 by 4096 pixel images. And we then downsample it to 128 by 128 by doing a median filter at each of these windows. And what this does is this basically acts as a low-pass filter, and it removes most of the stars, okay? And in this image, you're basically left with just scattered light, but you've got still some Milky Way left over, some of the galaxy background light. And so we then subtract a background image. Now, weirdly, I'm talking about backgrounds very differently to what we typically talk about backgrounds. For me, background is stars, and I'm interested in that scattered light, right? So what we're considering is every single image in a particular orbit, where both the Earth and the Moon are below the sunshade, right? And in those cases, we know that no scattered light can be entering our image. And so we sum up all those, we take the average of that, and we subtract it away from a particular FFI. And when we do that, we should be left with an image that has no stars in it, no galaxy, and just have our scattered light, okay? We then downscale it, so going from these large pixel values down to just a range of 0 to 1. And we do that just so that a machine learning model can handle it. And so this processed image here, right, with just a median filtered down sample and subtracting out the stars is what we're using in our machine learning model. All right. And so ideally, we go from this processed image into some sort of latent representation of the data, right? What we call here my noise, my Gaussian noise in the middle. And then we want to repredict that scattered light image. Okay. The key to this is we want to condition on things that we understand, right? We know the positions of the Earth and the Moon, and we know the distances. And so we can condition on them. We can give this information to our model, right? So what we're going to do is we're going to pass in the azimuths and elevations of the with respect to the sunshade and the Earth, the camera and the Earth, and the Moon and the sunshade, and the camera and the Moon. And so that gives us 8 angles that represent the positions of the Earth and the Moon. The other thing we do is we pass in 1 over d squared, and we do this because we know that this scales with the brightness of the Moon and the Earth. And we also pass in 1 over d, and we know that this scales with the angular diameter of the Moon and the Earth, right? So as the Earth and the Moon go further out, the relative albedo of it will decrease. Okay, so these 16 parameters, or these 12 parameters rather, is what goes into our model. Okay, and so we want to build something that takes in this conditional information with just these angles, right? These are just the positions of the Earth and the Moon, and passes into this latent representation and predicts this particular noise. Okay, but key to this is that we don't actually need this image at all. We don't need the original FFI. Okay, and so we can just say, with just using the positions of the Earth and the Moon, we can now predict the scattered light. And this is a really, really powerful and interesting thing we've been able to do, right? We can now predict this image, a perfect scattered light image, without ever seeing an FFI. And the neat thing here is that given any positions of the Earth and the Moon, given any distances, I can tell you the scattered light. And that means that next week or next year, on a particular date, we can exactly infer, and we can exactly predict what that scattered light bubble would look like without ever seeing an FFI. And so I think that's really, really interesting. And so in principle, we've learned some sort of forward model that goes from these angles to this scattered light. So how does this look in practice? So we pass in our processed image, and we can make a prediction without ever needing this prediction at all, without ever needing this original processed image. We're just using the angles and the positions of the Earth and the Moon, and we can make a prediction of the scattered light bubble, right? And not only do we get a prediction of the scattered light, we get an uncertainty associated with it as well. And so we have our standard deviation. You can see that those uncertainties are on the 5% level, right? And we can do this for every single FFI. The other thing that's really important here is that because our machine learning model is quite large, we can't actually pass in the full image. And so we have to downscale. And in this case, we've downscaled to a 64 by 64 pixel image. And so after we've predicted our model, ultimately we'd like to change this later down the line, potentially getting more GPUs, more compute power. But we have to upsample. And so we do this linear spline upsampling where we just upsample with a linear interpolation, and we can get back to our original sized image, 4096 by 4096. And this here, again, is our predicted image of what a scattered light looks like with an associated uncertainty. Okay, and so ultimately what we get is we have our original image, and we can then subtract out our prediction of the scattered light and produce an FFI that has no scattered light in it at all, in principle. And so that's kind of the end goal, where we can just subtract this out, and we get an FFI, a corrected FFI, with uncertainties associated with it as well. So this is the full process. I'm not going to go through it all, but basically there's a pre-processing step. You can do this prediction, you upsample, and you get your corrected FFI at the end. Okay, and again, key to this is that we've only tested this on camera 3 so far, still a work in progress. But the neat thing is that we can train on just past orbits. So just training, we've trained on orbits 11 to 46. We've been able to then predict on future orbits. So we can predict on orbits 47 to 54, for example, which have a very different distribution of positions and angles of the Earth and the Moon. And yet we can make very good and accurate predictions of the scattered light. And so this model really does generalize well to completely unseen data without ever seeing an FFI. And so if we look at the actual distribution across the entire test set of all of our models, all of our predictions, we can look at our RMSE, so the root mean square error, and we can see that our uncertainties are relatively well calibrated. Cool. All right, so in conclusion, what we've been able to do is see that using only the positions of the Earth and the Moon, we can make accurate predictions of the complex spatial patterns of scattered light, and we get uncertainties for free as well. And so this generalizes well to any new data and can predict any future orbit. And hopefully demonstrate these conditional diffusion models can actually work to predict scattered light. Now, still a work in progress. We'll see how well this works on smaller scales and on the light curve level later down the line. But if you're interested in this, please come and chat to me or Joey and Jenny, who are both giving a poster as well, or Roland, who's heavily involved as well. All right. Thanks, guys. And that's me.
You don't need me at all. Dead on 12 minutes. I see a hand. I see two hands. I'm going to go with just two hands because I saw them first. Back there, please.
Angie Wolfgang, Eureka Scientific. How large is your training set? So how many of these pre-processed models did you create in order to train this algorithm? And how many time steps are involved in the diffusion model?
So we have trained on all orbits 11 to 46 so far, and we've been able to make these predictions on future orbits. And so ideally we go to the entire TESS set, but we've just got a few thousand FFIs at this stage. I think your second question is how many diffusion time steps? We're using 600 diffusion time steps, so that adds complexity to the model.
Yeah, Eric Gaitis, University of Hawaii. So have you looked into what is the dominant source of your error for the predictions? Is it the size of the training set or the interference from stars in the field?
So not sure yet. It's unclear. Still a work in progress to see where the error is coming from. But actually the error is pretty well calibrated. And so it seems to be relatively small. It's less than 5% level, but I'm not sure yet. But we'll see. And so if anyone's got any test cases and particular objects they'd like to test on, please reach out to us.
Okay, Andras.
Thank you very much. Very, very nice work. And I really liked all of the aspects what you explained. So my question is just a funny question. Are you prepared for lunar eclipses? No, it's just a joke. The important question is that how linear is this behavior?
How linear?
Linear, yes. Because, so I'm just thinking about that. Can you use Earth when the Earth is above the sunshade to teach the algorithm when the Earth is below the sunshade, but the moon is up?
I suspect that this problem is highly nonlinear, is my best guess. And so we are using data from below this. We are using data from when the Earth is both below and above the sunshade to make our predictions. But I'm not sure I fully got the question.
So because Earth is something, you know, it's bright and this is there. Mm-hmm. It produces some scattered light pattern.
Yeah.
But what would happen if the Earth is just just below the sunshade, but the moon is up at exactly the same position?
That's a good
question.
The
apparent position.
Yeah.
It is much more dimmer, of course, but would the patterns on the 4 cameras would be similar, just fainter? Or would those patterns be different because some reasons? I don't know. That's why I'm asking. So did you check this aspect, or can this aspect be checked?
So we can make predictions where you just don't pass in the Earth and the Moon. So you set the Earth and the Moon, or you particularly set the Moon below the sunshade and the Earth above the sunshade, and you can make predictions on just the impact of the Earth. Yeah, totally, you can do that. And so you can linearly separate the contribution of the Earth's scattered light and the Moon's scattered light to the image, which is really cool, I think. So I think that's your question. So you can linearly separate the contribution of the 2 components, the Earth and the Moon.
Okay, yeah. Let's talk about it later. Yeah. Okay, thank you.
I think we're done, Andras. We have to move on. If there are other questions, that's what the Slack channel is for. It's you again. Should see you sooner. Our next, let's thank Daniel again, please. Our next speaker and the final speaker for this session is Ayilin Garcia, who's going to tell us about detecting planets with nuance.
This one?
That's advanced. I think below just the.
Great. Okay, hi everyone. Thanks for the opportunity to speak here. And my name is Ayilin Garcia. I'm from the Flatiron Institute, CCA in New York. And today I'll be talking about how we can search for transiting signals in the light curve of active stars. And when I talk about the light curve of active stars, this is maybe what I'll be talking about. But I think we got a very nice, actually, introduction to the subject in the previous session where we're talking about Young systems, right? So let's look at the light curve. We would like to determine the transits in the light curve. We see a lot of variability, a lot of correlated noise in general. Might be, in this case, maybe not pulsations, maybe still our variability from star spots. It might be the gas clumps we seen in this in one of the previous session as well. And we understand that it will be very difficult to actually find the transits in the light curve, and of course this light curve may be impossible. And one of the things we can do is we can try to, and we heard that a lot in this session, detrend, right? So we can detrend the light curve. Here I use a B-weight filter. It's a data-driven approach. The detrending is not perfect because here I try to reconcile the transit signal. So I reapply the guideline of, for example, this 2 Votan, which is like to have a window scale, which is 3 times the transit duration. Anyway, this is our detrending light curve. This is maybe the best we can do. And then we can apply a box least square algorithm, right? A BLS. We have the transits, we have the white noise, we should be safe. So this is the result. This is a BLS of the detrended light curve. You see that we cannot detect the transit. We don't have a peak in the periodogram to detect the transits. Actually, I could try different window length. In this case, for example, for the B-weight filter, I would have the same result, or even using a spline, polynomials, harmonics. In this case, it's actually very hard to detrend and have a clean BLS. I can even go a step further and detrend with the same Gaussian process as I used to generate the data. So I will model the variability with the same Gaussian process that was used to generate the data. I will remove the variability, apply a BLS, and here again, it seems that we detrended everything. We removed all the transits. So what I'll be showing to you now, it's a technique that can lead to this kind of periodograms where we do have a detection. It is called nuance, and it's a documentation of nuance. You can actually play with this data and maybe find a way to break nuance and have a clean BLS. So we understand that it's all about the light curve. Not all light curves are actually problematic. In this case, no detrending might be fine, or even a slight detrending will not harm the transits. But in this case, we have to be careful. So we have to understand first, where do we have an issue, right? In which cases we have an issue. And the thing is, like, if we're going to do that based on the variability, it's always related to the kind of transit we're trying to look for. So we need a metric. One of the metrics possible is to estimate the relative duration of the transit compared to the stellar variability. Okay, so let's call it tau. This is the relative time scale of the transit. And we do the same for the amplitude. So relative amplitude here of the transit compared to the stellar variability. And with these adimensional parameters, 2 and delta, we understand that if we're close to 1, we have variability that's very close to the kind of transit we're actually trying to detect. Okay, here in this case, for example, it's kind of close, but maybe not. So first of all, we have to understand where, for which parameter, tau and delta, we have an issue. So that's what we did. We simulated a lot of light curves with different tau and delta values. And before, we tried to detrend, here using 2 techniques, a B-weight filter or the original GP. And we compute what's left of the transit by computing the remaining signal-to-noise ratio of the transit. You have to know that here I started with a transit, the same transit with an SNR of 30, so well detectable. And you can see here that in this parameter space, there are a lot of actually light curves for which we reach an SNR which is lower than 5. So we don't detect a transit with a signal-to-noise ratio of 30. And we already knew that, but we show here how detrending can be bad, and for which cases of tau and delta it is actually bad. Okay, so let me describe to you a different approach now, which is not involving detrending at all. The goal is to model everything together, and later we chat about how long it can take in terms of computations. So we will model the light curve as a Gaussian process. I will show you some equations. Don't pay attention if you don't like it, but if you know what I'm talking about, that might be useful. So the Gaussian process to model the light curve, it has a mean function and a covariance error matrix. And first of all, we just decide to model the stellar variability as correlated noise. Okay, in this case, it's noise. We have many ways to do that. Choose a physically informed kernel. Many things later actually related to that. For the mean model, we want to model the systematics and let's say here, a single transit signal. So a non-periodic transit signal. Let's say that we know the duration of the transit signal and the epoch. We go a step further and we assume that the mean model is linear. So linear model of systematics, you can use co-trending basis vectors, you can use pixel level declaration basis, but basically we will assume that the systematics model can be linearized. And we also make the transit model linear. We take this template of this transit model with a certain duration and epoch. We take the depth to 1, and we just here multiply this template by the depth to have the full transit model. And with this formulation, with this hypothesis, we can compute the likelihood of the data containing a single specific transit. And this is analytical because we're using this Gaussian process, okay? And that's basically what Nuance is using. So if you have this analytical way of computing the likelihood, you can compute the likelihood of the data containing a transit for different epoch of the transit and different durations of the transit. And you have this grid of likelihood of the data containing a single event. Next step, which I will not detail mathematically, is to actually combine, kind of facefold this full likelihood to now have the likelihood of the data containing a periodic transit signal. So combining these single events into a periodic transit signal, which will be the likelihood of a planet with a certain period being in the data. So we can also do that analytically. We do that for all the periods we want to try. And every time what we will do is for each period, find the best transit parameter, compute the SNR, and that will give us this periodogram. All right? Here again, we do not detrend, we model everything together, both the transit and the rest of the signals, including systematics as a linear model and stellar variability as correlating noise. All right? And here, I really want to emphasize that we are actually using the metric, which is the signal to noise ratio, and not like in the BLS, some empirical power. So what about the time, right? We do everything at the same time. This might take a lot of time. Actually, we implemented that using the high performance machine library JAX, all right? And JAX is a package where you can basically write your code in Python and deploy that in whatever hardware you like. So not only it is fast on GPU, for a single test sector, you have 2 minutes, 30 seconds, but on GPU, we really get the acceleration here with only 12 seconds, and it scales very well with a number of sectors. So that's really a practical option here for this algorithm. That's replacing both the detrending and the BLS. So let's talk about the benchmark. Is that actually working in reality? So let's first simulate some data. What we did is to simulate, again, a bit like before, 4,000 Likers with different relative timescale and amplitude for the transit compared to the stellar variability. And again, we search with Nuance compared to methods where we detrend and do a BLS. So the result, oh yeah, here I have to emphasize that for this experiment, we cheat a bit. We use the optimal Gaussian process, meaning the same Gaussian process that was used to generate the data, we use it in Nuance. But don't worry, the search with the detrending is also biased. I encourage you to look at the paper. And here is the result. So the 5 first plots are the same as before, but this time with different detrending technique before the BLS. The last one is a GP, so the same GP, optimal GP to detrend and then to a BLS, and the last one Nuance. So Nuance works really well. We see that the recovery is close to 100% over all this parameter space that seems to be problematic, especially for the 4 first detrending technique. And here, surprisingly, the GP works also really well, right? We only have this dark region. This is maybe where we were at when I showed you the example at the beginning, but here we can detrend with the GP and search for the transits. Let's now talk real Lie curves. So what we do is we took this list of 438 M-dwarf Lie curves that we identify as variable, and we take only one small section of a single sector. We inject 100 transits into each of these Lie curve with SNR from 2 to 30. In this case, we have real data. So we have data that contain things that we're not modeling, such as flares. So we really need to do a cleaning step. This is true for any technique. And also in this case, we cannot cheat. We have to define a kernel for the covariance of the data, for the stellar variability, and to optimize it. So in this case, we're really not in the case of an optimal Gaussian process. And this is the result, and this is in a better form. You can see that Nuance is working really well. Here I identify in gray the true positives and the false positives. So Nuance is the best technique. We can see here that actually the GP was not working so well. So maybe if we could detrend with the GP before, it's because it was optimal. But in the case of real data, it seems not to work so well. And Here, if we consider both the true and the false positive rates, nuance is the best technique in 93% of cases. So it's really working well on this sample of 438 Lyra curve of active stars. So now applications and only potential, because you might be asking, where are the planets? Well, I don't know. I didn't apply that to any good data. And I think there are many applications for this algorithm. So here are some ideas. Of course, finding planets around active stars. Something I didn't mention is that it's actually quite easy, but it has to be done and also studied to search for planets with transit time variations, just because of the way the method is actually developed. So if you're interested, you should talk to me. Actually, I think there is a really easy way to do that. Graph-based search, because with this algorithm, what you will do is to do this estimate of the likelihood of a single event. You will do that on separate nights. For each night, you can consider different systematic model, different GP model for the stellar variability. And then you will, like in a probabilistic way, combine these nights together and have a real algorithm to search for transits, even on really sparse data or even graph-based data. And finally, the search for single events. And this is what I described before. When you compute the likelihood of a single event in the data, and then you combine that. But this first step is actually really useful. You can use it alone. And to show you that it actually works, what I did is I switched the template of a transit to an exocomet transit. And I searched into the Lyra curve of Beta Pictoris to find back some exocomet transit that had been found before. Here, I do not detrend for the stellar variability. Stellar variability in the original paper was actually detrended just because these are delta QT variations and are very, very reproducible. So that's the only reason why we could actually do that in the first place. And here it's really a good example of how you could do nuance for this single events search. So I will leave you with some links, the documentation of nuance. It is on GitHub. I encourage you to read the paper if you're interested. Please, if you use the software or if you have any question, feel free to open an issue, shoot me an email. I'm really interested in collaborating with you for any potential applications. Thank you.
We have 4 very punctual speakers this session. So we have a couple of minutes for questions. I'm going to look to the left side of the room to start with. Dom?
Dom Odo from University of New Mexico. This is really exciting work. Thank you. Can you enumerate some of the ways in which nuance is different from a GP plus BLS? Because it kind of seems like that's the framework from which you're working, but your nuance code obviously works better than just a GPA plus BLS search.
Yeah, sure. So when you use a GP, you're still detrending, right? And if I show you, for example, the Lyra curve I simulated here, you can see a transit here, you can guess it, right? You can see these events where the GP tried to actually fit. And this is how the GP will be very bad. It will really degrade the transits if you try to detrend using this GP. So that's really where the difference is, that what we will do here virtually is we will take a transit, we will slide it across the Lyra curve. And every time there is a transit, instead of the GP explaining the Lyra curve, there will be a transit explaining the Lyra curve. And that's where the likelihood is actually computed, I would say, in a full-fledged form. So that's the difference.
We have time for one more question, and you're in my field of view. So,
hi, Nick Saunders, University of Hawaii. Great talk. This seems really interesting. I'm curious because you're using a template to describe the transit. You have to make some assumptions about the impact parameter or limb darkening coefficients that build that transit model. And I'm wondering if nuance accounts for the variation along those axes, or if you're worried about biases introduced by the assumptions you make.
Yeah, I might ask you to repeat the second part of the question, but for the first part, you're right, you have to use a template. So there are many templates available. But the thing with the use of JAX is that you can actually scale the computation for very different templates. So that's what I did. So in the first example, I won't go back to the slide, or maybe I will actually. You can see that I compute the likelihood over different duration and durations and different epochs. And this duration axis is actually parallelized over different CPUs. So if you want, you can take different limb darkening coefficients, you can take different templates. This would even allow you to actually search both for transits and, for example, exocomet you can just like extend this axis to whatever you like. So you're right, you have to take that into account, but because it is very scalable, you can actually include that and compute that on the go.
Thank you.
All right, let's thank Lionel again and thank all of our speakers for a great session.
So hello, everyone. This is Dr. Jonathan Chow. Yeah, Jonathan is a psychiatrist from the Student Mental Health and Counseling Department at the MIT Health Center, which is right here on campus. As I mentioned yesterday, at the beginning of the planning of the conference, the SOC was thinking about taking a small amount of time and doing something else. Eventually, we landed on, let's talk about mental health in academia, because it is not talked about enough. And since mental health is health, we have a professional to tell us, to educate us about this. So Jonathan will talk for about 15 minutes, and then we'll have 15 minutes of Q&A, which will be more like a conversation. Go ahead.
Thank you. Thank you, Avi. All right. Let me just make sure that this is working. And all right. So hi, everybody, and thank you all so much for being here. My name is Jonathan Chow. And as Avi mentioned, I'm not an astrophysicist, but I am a psychiatrist. I work here at MIT in student mental health and counseling. I'm a psychiatrist, and I also have a role here as the multicultural community engagement specialist, which sort of affords me opportunities like this to talk to folks like you about mental health and how we can make MIT and institutions like MIT sort of spaces where mental health and well-being are more talked about and sort of, you know, cultivated. I'm also on faculty at the Keck School of Medicine at the University of Southern California. So this topic of teaching and sort of graduate programs is sort of dear to my heart as well. I wanted to start by thanking and acknowledging Avi for inviting me here. This is a pretty unusual sort of speaking opportunity for me. I don't usually get invited to come to conferences, and I think that reflects Avi's, as well as I think many of you here in the audience today, your interest in and concern about what has been called the mental health crisis in graduate programs, in institutions of higher learning, and in academia in general. So as far as I can tell, and I really know nothing about astronomy, this is cutting edge stuff. I also think that inviting somebody to come talk about mental health in a space like this is itself pretty cutting edge. So as Avi mentioned, I'll talk for a few minutes and then hoping that we'll have a bit of a back and forth here on stage. So first, let's talk about kind of what we know. There's a 2018 study out of the University of Texas that oftentimes gets cited, where researchers found that graduate students are 6 times as likely to experience anxiety and depression as compared to the general population. They surveyed more than 2,000 graduate students across 26 countries and 234 institutions to find that 41% of graduate students have moderate to severe anxiety and 39% have moderate to severe depression. That's more than 1 out of every 3 students. Another study from 2022 surveyed 513 PhD students from 8 top-ranked economics PhD programs, including here at MIT, and found that 12% of students have experienced suicidal thoughts in the last year. In terms of who is most affected, the same 2018 study from the University of Texas found that female graduate students, as shown here on the right in red, are more likely to experience anxiety and depression than their male peers. Transgender and gender nonconforming graduate students here in green are more likely to experience anxiety and depression than their cisgender peers. And this is consistent with general trends in the general population based on gender. In 2014, UC Berkeley put out its graduate student happiness and well-being report, which found that 47% of all of its graduate students have depression. They reported that LGBTQ+ students are significantly more likely to experience depression than their non-gender minoritized peers. They also found that students who belong to minoritized racial groups are not only less likely to seek care, but also more likely to experience significant mental health challenges. This too is consistent with trends in the general population, and I think reflects the ways in which graduate programs are not immune to the wider societal issues of race, gender, and sexual minoritization and discrimination. Things are only getting worse. In a 2014 national survey of American college counseling centers, 94% of college counseling center directors agreed that the number of students presenting with quote unquote severe psychological problems was increasing. Faculty too, 87% of professors in 2021 say that student mental health has worsened over time. On the right, you'll see our own utilization data from MIT Health Student Mental Health and Counseling, which shows that in the academic year 2012 to 2013, which is the leftmost column, we had 6,000 visits from graduate students. In 2021 to 2022 academic year, which is the rightmost column, we have over 12,000 visits. That's double the number. As I hope that these numbers and graphs have demonstrated, the extent of the problem is vast, to the degree that poor mental health in academic environments has been termed, I think rightfully, and I hope you agree, a mental health and public health crisis. Before I move on to talk about some of the major contributing factors that are thought to sort of underlie some of these very concerning rates of mental health issues in academia, I want to make a couple notes about the fact that most of the studies that I've sort of shown you so far have to do with graduate student mental health. So the first point is that far more studies have looked at graduate student mental health than faculty mental health. There's a recognized dearth in the literature that people comment on, sort of studies on the mental health of postdocs, faculty, researchers, and other staff at universities. That being said, the National Education Association reports nearly matching rates of severe depression, anxiety, and stress among college students and faculty. And according to a survey conducted by Insight Higher Ed, 38% of university faculty and staff say that they are often or always emotionally exhausted. At the same time, if we take a more systems-based perspective and consider the structural determinants underlying the rates of mental health issues among graduate students, it's not unreasonable to say, I think, that the mental health of graduate students is a reflection of the culture, structures, and systems that constitute graduate programs and university institutions. We could even begin to talk about things like the health of a program or the health of a department or institution. Sadly, as we'll sort of see in a moment, the factors that have been shown to contribute to poor graduate student mental health are not unique to graduate students. If anything, they're unique to academic environments. But graduate students, I think, are especially vulnerable to these structural and cultural forces sort of sitting at the middle of all of them. And in that way, I think we could sort of think about them as canaries in the coal mine. So can we begin to understand what might be contributing to some of these very concerning sort of levels of mental unwellness in academia? What does the literature say? That takes us to part 2, factors associated with mental health outcomes. So of course here, we could spend a whole hour longer even sort of talking about the various factors that are thought to underlie some of these rates. Mostly, Avi and I were hoping that this could serve as a kind of request for collaboration, a kind of clarion call to not let this be the sort of end of the conversation, but actually the beginning of it, to take back to your own institutions some of these numbers, which are not just here in the US, but sort of globally. See it as a mirror and a prompt to ask questions about your department. How does it feel in terms of support and mentorship and care? So if we go back to the study by Evans et al. At UT Health San Antonio, which I previously mentioned, in addition to surveying rates of depression and anxiety, they also gathered data related to 2 key psychosocial factors, work-life balance and mentorship relationships. And so here, they found that students who reported having an quote unquote unhealthy work-life balance, which are the 2 bars on the left of the graph, the blue sort of green represents the percentage of students who have anxiety, and the red represents students who have depression. Those students were more than twice as likely to have anxiety and depression than those who reported having a healthy work-life balance. They also found that students with anxiety and depression were significantly more likely to feel unsupported and unvalued by their PIs or advisors. These bar graphs show, so on the top, there are students who had anxiety, and on the bottom are students who had depression. And the bars represent whether they disagreed or agreed with statements having to do with sort of various dimensions of their mentorship relationships. So provides mentorship, provides ample support, positive emotional impact, asset to career, feel valued by mentor. And as you can see in the red, which represents students who disagree with those statements, students with mental health issues were more likely to feel unsupported by their mentors. This is a really interesting 2022 study conducted by a team at UC Irvine that looked not only at negative factors, but also positive factors related to graduate student mental health. So they surveyed over 3,600 graduate students over the 10 UC campuses. And they found first, just generally, that depressive symptoms were higher among women, among international students, unmarried, unpartnered students, people pursuing degrees in the humanities, and people pursuing PhD degrees. And then they looked at sort of negative and positive factors accounting for these demographic factors. So what they found was that negative factors were correlated, or negative factors that correlated with depressive symptoms included financial concerns, poor mentorship, and instances of bias, discrimination, and harassment. These are listed in the graph on the left in light gray. Meanwhile, positive factors that correlated with depressive symptoms, meaning factors that were correlated with lower rates of depression, included general social support, specific support from departments, and optimism about career prospects. These are shown in black. Each of these correlations were significant. The researchers also performed a really interesting additional analysis to determine whether the positive factors attenuated the relationship between the negative factors and the depressive symptoms. They found that the associations between depression and the negative factors, so financial concerns, poor mentorship, and instances of bias, were weakened when students had those positive factors, so greater social support, a more supportive departmental climate, and optimism about their job prospects. It's really quite striking in all three cases, the presence of those positive factors cut the impact of the negative factors by close to half, or in the case of poor mentor relationships, almost entirely. I find this really interesting. A student can have a bad mentorship relationship, but if they have those positive supports from their department and in general, it almost sort of doesn't matter. It's a pretty significant change. Finally, if we go back to the 2014 UC Happiness and Wellbeing Report, which I previously mentioned, they found that the #1 predictor of well-being among graduate students was optimism about career prospects. And so on the right here, you can see how satisfaction with life, which is on the y-axis, correlates with optimism about career prospects on the x-axis. I'll also mention that other papers noted the unique challenges that international students face related to restrictions on travel, distance from family, perceived and real discrimination and bias, and challenges on the level of culture and language. So what do we do? If there's one point that I want to make today, something that I want you all to take home, it's that, in fact, you all are making a difference, and not just any difference, but a big difference. The data here that I've shown so far, I think, bears this out. The fact that poor relationships with mentors and instances of bias have such a large negative effect, but if we can create a more sort of positive environment in the department and sort of help students feel optimistic about some of their career prospects, or at least realistic, that can have a really big positive effect and even sort of attenuate some of the negative factors. Which gets us, I think, to one of the sort of major issues in mental health in general and academic mental health specifically, which is about stigma, right? So the kind of difficulty that many people experience accessing mental health services. So I think the question is, how do we sort of combat stigma? And I think, and this is sort of what all the different research studies that if you read, they sort of start talking about this once they get to the paper about interventions. It's really about three things. It's really about normalizing, encouraging, and rewarding. So I just want to briefly sort of go through and talk about what each one of these might look like. So normalizing. We need to let students know that it's not just them. This entails, people who are further along in their careers or maybe even in their programs, those who have a little bit more security and power, speaking out about their own experiences. When students can see that other students and maybe even faculty are making the time, whether it's at a conference like this or during individual advising meetings or departmental meetings, sort of saying that, it's not just you, you're not alone, it's not your fault, that can have a really big effect. Think of a time when you maybe were facing a challenge in your research and you weren't really sure what to do, and a mentor or a peer said, hey, I've been through something similar, why don't you try this out? It worked for me. We do this all the time in academia. Why not when it comes to mental health? We can say that it's normal, it happens, you're not alone, it's not your fault. Encouraging. Encouraging means actually inviting students to reach out and seek support, whether it's from you, another advisor, or a counselor or a psychiatrist, letting them know that this is a supportive environment and relationship, and that if they're struggling, you want to hear about it. Of course, you're not a therapist, you're not a psychiatrist, you may not be able to help them in exactly the way that they need to be helped, but even if you don't know, that doesn't mean that you don't care. And maybe you know somebody that they can reach out to, somebody like me, for example. So let your students and your peers know that you're there to listen, and which is, oftentimes more than enough. And if it's desired, you can sort of problem solve together. Finally, this idea of rewarding. Can we imagine a scenario in which students and faculty were actually rewarded for talking about their challenging experiences, both in the past and in the present? What would this do to the culture of a department? We might say something like, hey, I'm glad you said something. It shows maturity, courage, and your commitment to science. I imagine in the future, when you have your own mentees, you'll care about how they're doing, not just as researchers, but as whole people. This step of rewarding is perhaps the toughest one because we have to ask hard questions about institutional policies and how they often take a punitive approach to people who need help, because it seems to go against things like productivity and output, even though I think we can all sort of agree they're not necessarily opposed. If we take a slightly larger view, if you're having trouble with things like retention, how is that really helping your productivity? So just a few parting thoughts. Ultimately, this is going to look different for each institution, each department, each faculty and student relationship. There isn't a one-size-fits-all solution, and I think that's actually a good thing, because then whatever solutions end up being designed in collaboration with faculty, students, and administrators, those are solutions that are tailored and specific to the particular academic and cultural environment of that program. So I just want to end on a note of invitation and collaboration. Again, thanks to Avi for inviting me to speak today at this conference. It's this kind of collaborative and interdisciplinary spirit that I think ultimately translates into improved mental health for students and faculty alike across departments and institutions. And I know that my colleagues at Student Mental Health and Counseling are eager to partner with departmental advisors and faculty, as are the wonderful deans who work at Student Support Services and the Office of Graduate Education. Finally, never worry alone is something that was oftentimes told to me during my training, and it certainly sort of had an impact on my own sort of ability to make it through some pretty grueling training experiences. But we're all responsible, we're all invested and committed to creating a more inclusive and caring academic environment that supports and cultivates the flourishing of whole scientists and whole people. Thank you.
I'm going for the seat. I'll sit here. Yep. So in the time we have remaining, we'll have a few questions, and these are somewhat random, not in a specific order. Or I did not see your slides before a few hours ago, so I didn't tailor them specifically. Are there any specific symptoms that if I experience, those will be a sign, a clear sign, like I need to get some help, like now?
Some of the backstory is that Avi sent me these questions a few days ago or so I had a second to sort of process it. So, but this is an interesting question, right? Because I think in some cases, or sort of if we were to translate that to sort of physical sort of health issues, right? This question of like, what are some signs that mean that you should really definitely get some help? It's like, well, if you're having a heart attack, it's probably a good idea to like go talk to somebody, right? But it's interesting that in the case of mental health, we're sort of like, what is like the last possible step in which like there's a clear sign in which I like really need to get some help? And so I really want to sort of like reframe that, right? And think about it more in terms of, can we think about this idea of like a mental health yearly checkup even? Like, why does that sound like such a bizarre idea? But I don't know, it kind of makes sense in some ways. Like, can we do more to sort of be plugged in earlier? So, things like feeling sad, having trouble with relationships, having trouble sleeping, difficulty with, your appetite, having trouble getting your work done, feeling unmotivated to go to lab. Like, these are all actually things that I talk to students about all the time. And, I think we're used to operating in this sort of ambiguous space of like, it's not like a catastrophe right now, but I'm glad that you're here kind of thing. So, yeah.
Another question. I have a friend, someone I know, someone I care about, and they're clearly struggling. What do I mean by struggling? They do say they're feeling stress. They say it, and it shows. And they say that last night they had problem falling asleep, lying awake for an hour and sleep does not come. Eventually they do fall asleep. They feel a little bit less hungry than they used to. And I want to help my friend, but I can't just tell them, okay, you need to go see someone. I can't go brute force or just openly, because that would push them away. I know my friend, I know how they would react. So what should I do?
Yeah, for me, this connects back to the slide that, with the positive and the negative factors and the sort of different ways in which the positive factors attenuate the sort of negative ones. So it seems to me that if you can sort of sit with your friend and sort of actually be a source of social support for them, that could have a really significant effect actually on how they experience the stress, assuming that it's sort of coming in part from, their work and sort of academic work. So I think first, I think the sort of easy answer would be like, how do I get them to come to sort of, to come see me or something like that in student mental health counseling. But I think the more nuanced answer is, how can I listen to this person in a way that makes them feel supported? And then actually listening to them in terms of, what do they feel like would be helpful? What, maybe that's, I'm scared to go into MIT Health, but it'd be great if you could come with me or something like that. Or they're more resistant to that, and sort of, can you imagine what that looks like to actually be a source of social support?
You mentioned that many of the studies were focused on grad students. I'm guessing it's a very organic population. You can easily get them.
Vulnerable.
The age range is not that wide. But what about other, like, broader age range? Is the mental health issues, are there any mental health issues that are unique to a specific age range, or can it be also at older age or more senior positions?
Yeah, I think there's two parts to this question. One is that, has to do with this question of sort of, faculty mental health, or sort of not just looking at graduate students. And I think the answer to that is definitely mental health issues are an equal opportunity employer. They affect all of us, cutting across, age, gender, race, sex, socioeconomic status, whatever it is. It has a way of finding, everybody. At the same time, graduate students are a uniquely sort of vulnerable population because of, as mentioned, sort of where they sit within the sort of structures and systems. But also that I think it's important to mention that a lot of mental health disorders present oftentimes in what we call the transitional age youth sort of age range, so 18 to 26. So something like bipolar disorder or schizophrenia, that's actually when some of those things show up.
So that's the age where those syndromes or conditions will appear for the first time.
Yes, and so you might have a student who has never experienced something like this before, and it can be really sort of kind of disorganizing or a little disruptive. And I think that's where, we come in, and also community members, faculty, staff, who may be the first ones to notice something that's kind of going wrong. And so I think knowing how to, one, support that student and sort of like, sit with them and listen, but also knowing that you can always give me a call, give our department and clinic a call if you have any sort of concerns about students.
I have a different question. What is a panic attack?
Yeah, it's a very specific question. I like it. A panic attack, any sort of psychiatric mental health sort of symptom can look very different for each person. I think that's an important thing to say, right? Is that mental health issues are specific and unique to the sort of individual in the individual's life. A panic attack is most oftentimes defined as a discrete unit of heightened anxiety that peaks within minutes and comes with both sort of physical symptoms as well as sort of psychological symptoms. You might get something like palpitations, shortness of breath, dizziness, lightheadedness, even like a sense of doom or a sense of sort of things closing in. But one of the things that's also important to mention with panic attacks is that after a panic attack, you might sort of fear getting another panic attack. And these are reasons to come talk to us.
Yeah, and I can say a panic attack is probably one of the worst feelings you can have.
Yeah.
Maybe the last question, we're coming up on the hour, and broadly and as briefly as you can, what are the kind of medications that you usually prescribe to people with mild issues? There are the slow acting, long term, and there are the things that you take right now because I'm having a panic attack right now. So you can describe briefly those kind of medications.
Yeah, I think you're, that's a good place to start. Is that we have a sort of range that we work with the sort of individual student, patient, client to sort of decide like what would be sort of best, sort of something that is fast acting versus something that sort of gets at more of like an underlying issue. But I think it's also important to mention that psychiatry is not just about medication, and there are many students that I see for whom I do not prescribe medications. And I think, that's how we all practice in here as well as in general. Psychiatry is about the individual sort of sitting in front of us. And, just as we can sort of think about stress or anxiety or depression in a sort of multidimensional, multifaceted way, treatment is the same. It's not just about medication, but medications can help sort of, help you help yourself is sometimes what we oftentimes say.
So if it's not medication, what else is there?
So many different things. Therapy is a big one, but even things like lifestyle changes, even things like, one of my colleagues, Mia Gore, talks about how the most common thing she talks to students about is sleep. That's like most of her work is just talking about how important sleep is. So, there's so much that we do that goes beyond medications, because I think we all recognize that it's complicated, right? It's complex, these issues, these feelings, and so we have to approach it in a sort of complex way too.
Going to the gym,
dietary stuff is really important as well. But also finding joy in what you do. And,
going for a walk,
talking to your advisor in a different way. I don't know, all kinds of things. So
yeah. Any last words you want to add?
Well, maybe, Avi, if you don't mind just saying a few words about, maybe I could turn it back on you a little bit. This is, as far as I'm concerned, a really different sort of thing for you as well as for me, for us. Yeah. And so I don't know if there's anything else you wanted to say just about sort of the intention or what you hope some of the audience members might take away from some of this.
So yeah, I think like I said before, mental health is something that is not talked about enough, not necessarily in academia, but broadly in the population. And yet it is something that I think, I'm not a professional, but I think it's something that most people will suffer, maybe suffer is a strong word, be impacted by or be affected by some point in their life. But again, yet it's not something talked about. And I think one of the healthy approaches is to say mental health is health. Just like you have a fever that hasn't gone away for a couple of days, you go to the doctor. It's not a problem, you go to the doctor. So mental health should be also something like that. You have something that interferes with your everyday life, like you haven't been able to fall asleep last night, it makes you tired the next day, then it interferes with your everyday life. So go see a doctor, even your regular doctor, and take it from there.
Yeah.
Or like I had a shoulder pain like a couple of years back. So eventually I couldn't lift the grocery bags without feeling pain. I'm like, okay, that's it. I have to go to the doctor. And I went and they fixed me. But the same thing with mental health. Like think about it in the same way. Mental health is health. And something you feel it's affecting your everyday life. Do something about it. Right. Reach out to friends, family, professionals, and so on. And like you said earlier, you had it up here. Don't suffer alone. Don't worry alone.
Don't suffer alone. Never worry alone.
That's the most important thing. We are social creatures.
Yeah.
And that, for a reason, that also helps with mental health. Once you reach out to a friend, everything becomes better.
Yeah.
So. Okay. Thank you.
Thank you.
You can.